Let's begin with the first topic, that is error analysis. So before starting with the questions, we will first revise it with our revision X notes, and then we will start off with the questions. Okay, so we will go like one by one. Like I will go through it in a fast manner. If you want to do a comprehensive study, if you want to comprehensively revise, you feel free. You can download the revision X notes and you can revise on your own. Okay. So if you want to revise with me, you can watch along with me. Maybe I will say a few extra pointers that might be helpful, or you can just revise on your own, directly jump into the questions part. So yeah, first is the scale. Basically, any measuring instrument will have a scale. A scale is said to be linear if the relation between the deflecting torque, right, the torque that is responsible for the movement of the pointer and the angle, right, by which it has moved, are proportional to each other, linearly proportional. If they share a linear relation, that means we have a linear scale. Non-linear scale, where the markings are not linearly spaced. The example can be this, that if my torque is proportional to theta square, right, or my theta, the deflection is proportional to deflecting torque square. So it is non-linear relationship. And of course, for few measuring instruments like moving iron instruments, dynamometer type instruments, the scale is not linear. It is not linear. For PMMC, it is linear. We will see that obviously in the second chapter. So there are few characteristics, static characteristics and dynamic characteristics. Static characteristics are those whose behavior uh, does not change with time. So if I am observing at now, and if I am observing the characteristics 10 minutes after, right, that those behavior will not change. Dynamic, as from the name you can understand that it will change with respect to time. So 10 minutes before I checked the accuracy and 10 minutes after I checked the accuracy, it changed. So it will be considered a dynamic characteristics, but accuracy is generally called as a static characteristics. Dynamic characteristics is not in our GATE syllabus. So all these, accuracy, precision, sensitivity, all these are static characteristics. Accuracy, the closeness of the measured value to the true or actual value of a quantity. Let's say my actual value is 5 volts, right, and I am measuring 5 volt, 4.9 volt, 5.1 volt, 4.8 volt. So the accuracy here would be 0.1 volt. Here it would be like almost 100% accuracy, right, whatever is the difference. Okay, how far I am, or how close I am to my true value, how close I am to my true value, that is called as accuracy. Precision is the ability of the instrument to consistently provide the same measurement under the same conditions. Now these two things are different. Precision does not talk regarding the information that how close I am to my true value. No, it does not tell me the information how close I am to my true value. All it tells me that if I'm repeating my experiment 100 times, my expectation is if my instrument is precise, then it will give me almost the same measured value. This has no relation with accuracy. So please keep this in mind. These two things are quite different. Accuracy is the closeness to the true value, actual value. Precision tells me if I am repeating my experiment multiple times, if I am repeating my measurement multiple times, how how many times it is providing me almost similar measured values. Sensitivity is the ratio of change in output signal to the change in input signal. Okay, higher sensitivity means the instrument responds more significantly. Basically, sensitivity basically means that for what small change in the input signal, that is a measured quantity, the output needle will move, right. Let's say I have this scale, right, and I have scale, one small scale deviation is 0.1 volt. So for is what amount of measured quantity that will trigger this 0.1 volt of deflection, right. If my scale was previously here, it will deflect to here. So what is the smallest quantity of input that will change my pointer deflection to one small scale division? That is what sensitivity mean. It is actually the ratio of the one small scale division of the output divided by the change in the input. Okay, so there are few questions that we can see. Just give me 1 second. Let me bring my water. Yeah, sorry. So if you see the example here, we have an instrument this 3.6 ampere, 3.65 ampere, 3.55, 3.5 ampere, right? Now what is the true value? So so this is the actual circuit, right? This is the actual circuit. This is the instrument A. Do you know what is the true value? We can obviously calculate. The ammeter true value should be 5 ampere, right? Equal current division. But here I am saying I am very far off my actual value, but whatever values the instrument is measuring, it is very close, right? I am measuring it 4 times, it is very close. Certainly the instrument would be precise, it will not be accurate. Here instrument would be both precise and accurate because it is close to my true value and it is measuring almost similar values on repeating the experiment. Here if you see, it is neither accurate neither precise. Okay, so one thing certainly you can say is that if a instrument is precise, right, it can be accurate. Okay, but if it is not precise, as you can see here, there is no possibility of accuracy. If it is not even precise, right, it will measure different values every time, so how can it be accurate? So this kind of MSQ questions can be framed. Okay, so one more thing is there regarding resolution, right? What is resolution? So resolution is if you see, hold on a second, compute the resolution in volts of the following measuring device that has a range of 0 to 100 volt over 100 divisions. Okay, 1/10 of the division is the minimum readability of the by this voltmeter. So minimum readability would be my resolution basically, right? So I have total 100 divisions, so and the range is from 0 to 100, so each division, right, will be 1 volt, right? Each division will be 1 volt and the minimum readability of this voltmeter is 1/10th of a division. That, so resolution is nothing but the minimum readability of my measuring instrument, right? So one division is 1 volt, so 1/10th division would be 0.1 volt, so resolution would be 0.1 volt. Okay, now your sensitivity, as I mentioned, and this can be asked in a question, that it is the ratio of change in output over change in input. Basically small change in input over small change in output, whatever is the small change that the measuring instrument can detect. So delta y upon delta x, right? So if previously the input was x, I change it to delta x, now my output previously was y, it got changed to delta y. So sensitivity is the change ratio of delta y upon delta x. Okay, there are a few questions that you can read and do on your own. I will not go through everything because constraint of time. Now error, so that is the main topic and mostly from here questions are asked, so please listen to me here carefully. So we have absolute error, relative error. So what is absolute error? Absolute error is this, right? So basically whatever is the measured value minus the true value. Very simple definition of error, I think you already know this. So absolute error will have the same unit dimensions of the measured quantity. Absolute error will have same dimensions of the measured quantity. Absolute error is very simple, right? Simple measured value minus true value. Relative error is if I want to see my error in terms of percentage relative to the what? True value. Okay, so relative error would be absolute error by true value into 100%. That will be my relative error. So, and this is what mostly is used because we don't want to refer to our error with respect to a value, we want to relatively refer to our error. So next time if the true value changes, I can just use this formula, right, to compute the absolute error. Okay, but here if the true value changes, right, your absolute error will be something else. You will again need the information regarding the measured value, right, but here you won't need the information. Okay, that's why relative error is very useful and it is a unitless quantity, does not have any unit because numerator has a unit of same and denominator also same unit, right? So units will be cancelled. So this will be a unit, this will be an unitless quantity. Very, very important part here, you will have to listen to me very, very, very carefully. Okay, so if there is some slash difference of two quantities, let's say x1 and x2 are two measured quantities. Let's say I have this circuit, right, and I am measuring both the resistors. So x1 is the measurement of the resistor 1 and x2 is the measurement of the resistor 2, and of course they will have some errors, right? So if I'm either adding, so if I'm computing the overall addition of the two values, addition of the two measured values, right, x1 plus x2 or x1 minus x2, then what will be the overall absolute error? So overall absolute errors also will be added. Okay, you will, so let's say I have this quantity, let's say x1 I measured, let's say I have this series circuit R1 R2, right, and x1 is R1 plus delta R1 and x2 is R2 plus delta R2, correct. So let's say if I want to compute the whole measurement, right, R1 plus R2, so what will be R1 plus R2, what will be the whole overall R equivalent? R equivalent will be, of course, it will be x1 plus x2, right. But how do I write my R equivalent in terms of the error as well? So this will be equals to R1 plus R2. Now this absolute error, right, this can be positive or negative. Okay, this absolute error can be positive or negative, right? If this is positive or negative, we don't know. So what we will do, we will add a plus minus sign here and we will add the absolute value. So we will write the worst case values. So in the worst case scenario, what is the measured value? Basically this, right, if I do this, that basically means what? I am assuming that there is maximum error in the instrument 1 and maximum error in the instrument 2, and I am computing the worst case value. So my measured value, right, addition of these two, my measured value cannot deviate more than this. Certainly it will deviate less than this because delta 1 can be negative, delta 2 can be negative, right. Ultimately if you add the errors, one will be positive, one will be negative, so errors, overall error can reduce. But I am computing for the worst case scenario. So for the worst case scenario, you will take the absolute value, make it positive, then add this. This will be the worst case error scenario. Okay, so that is my overall R equivalent, right. Now so that, remember, I am discussing about absolute error here. We will certainly discuss about relative error. So please keep this in mind. I don't think you will have to remember this. Just write the values. You can derive by yourself. Now, if I am doing product of two quantities, let's say I want to calculate the power. I measure the voltage. I measure the current. So what will happen? You can derive this, right? So your P plus delta P will be equals to V into I plus delta Vi plus delta IV plus delta V into delta I. Now what should happen, what you can do is you can divide by Vi on both sides. So P is Vi, right? So this will be 1. If I divide by Vi, this is delta P by P. This is 1 plus delta V by V plus delta V by I plus delta V delta I into Vi. Now as the errors, right, will be very small, delta V will be some 0.05 volts, delta I will be some 0. Like I'm just giving you some rough numbers, they will be very small. So ultimately this product, right, will be very small. So we can ignore this. So ultimately your error, right, comes out to be this: delta P upon P is equals to delta V upon V plus delta I upon I. So you can derive this in the exam hall. It's not like you will have to remember all these results. No, I'm just telling you a method to derive this in the exam hall. What about division of two quantities? If I'm dividing these two quantities, it is a bit tricky. So this will be R plus delta R will be equals to voltage by current, right? So V plus delta V, I plus delta I, right? So what we did, I took the I common, I took the V common, right? So this will be V by I equals to 1 plus delta V by V, 1 plus delta I by I, right? So now what we have done, we have again taken this V by I on the left hand side. If I take this V by I on the left hand side, this will be 1 plus delta R by R equals to 1 plus delta V by V, right? Yeah, this term. And we can make a bit of approximation here. What kind of approximation? So I hope you know this, right? So you know this property. So if I have 1 plus x of minus inverse, this will be 1 minus x square minus x cube and so on, correct? And as in our case, this delta I by I will be any very small quantity. If I square it, right, this will be even smaller quantity. So I can do the first order approximation. So this particular term can be converted like this, and ultimately your delta R by R will be equals to this. Okay. So simply your error will be, now this I am deriving with respect to relative error. Okay, this is relative error. So whenever there is product, right, product of quantities or division of quantities, you will try to solve in terms of relative error. Whenever it is sum or difference, you will try to solve in terms of absolute error. Will you have this in mind? Because whenever there is sum, it is very easy for us to solve in terms of absolute quantities, because we are simply adding the two values or subtracting the two values. But whenever there is product, right, we will take help of relative. So this delta V by V is what? Nothing but the relative error, right? V is the true value, delta V is the error, right? So these are all relative errors. Got it? Cool. Now these are all relative errors without percentage, right? So they don't have any percentage. Okay, so there are a few questions which of course we'll solve today's lecture only, so we don't have to worry about these things. Yeah, again the next topic, very important topic, the standard deviation or uncertainty, right? So basically the error, right? We want to compute the standard deviation of the error. It is a statistical parameter. We want to compare how much will we deviate from the mean in case of error, right? So if I have any function x, right, that is a function of many measured quantities x1, x2, x3, and all are independent of each other. This thing you will have to remember. Just remember this, because from here 100% question will come and you will be able to solve it also if you remember the formula. That's it. Okay, so if my x is a function of x1, x2, x3, x4 and so on till xn, which all of them are independent of each other, then the standard deviation of the whole function sigma x will be equals to bracket sigma x1 whole square, that is standard deviation, variance of the first function x1 into del x upon del x1. So your x will be function of x1, right? So let's take an example. X is equals to 2x1 plus 3x1 plus 2x2 whole square, right? So what is del x upon del x1? That is 3. So here 3 will come. That's it. Then similarly here also the same formula will be repeated, and overall of course you will at the end take the under root. So ultimately this will be your standard deviation. Okay, this you will remember anyhow. This will be asked, and the unit will be same as the measured quantity. Okay, so yeah, these are the things that we need to revise, like that you need to keep in mind for the first chapter. Let's certainly solve let's certainly start with the questions, right? So this is the first question. So as you can see, this was a BM question. So I'm taking almost all branches, BM, IN, and obviously our EE branches, so that we can get good questions, good collection of questions. As shown in the circuit below, a constant voltage source is connected to two ideal resistors. The voltage drop across the resistor is measured using two different voltmeters, V1 and V2, at different instances. It's not like both of them are connected at the same instant. They are connected in different instances, and their readings were recorded as you can see. Which of the following is true? V1 is less accurate, V2 is more precise. So what is the true value of the voltage? True value of the voltage is, like, it is simply a voltage divider circuit, that is 2.5 volts, right? So I see in the first case I am much closer to 2.5 volts than the second case, because if you see this particular reading, it is almost 0.35 volts, 0.035 volts away, right? And here I see I'm always, the maximum deviation is 0.21 volts, right? So certainly V1 is more accurate. V1 is certainly more accurate, right? So V1 is certainly more accurate. V1 less accurate is not correct, right? But what is happening, if you see that the deviation in the readings are very large, right, in V1. So sometimes it is 2.479, sometimes it is 2.511. If you see the deviations of V2, right, it is within 0.01, right? 4.67, 4.65, sorry, 2.465 to 2.475. So the range is between 0.01. So the readings of V2 are more precise because the range is much smaller. Here, if you see, this is 2.479, this is 2.511. The range is much larger. It is like 0.03 something, right? So V2 is more precise, but V1 is more accurate. Okay, so option A is option B is correct for this particular question. Like these kind of simple questions only will come. Okay, and if you skip this particular subject, then you will just skip out on scoring easy marks. Okay, so don't, make sure you don't skip this subject. Let's solve the next question. This is the next question, right? A non-ideal silicon based PN junction diode is tested by sweeping the bias applied across its terminal -5 volt to +5 volts. The effective terminal voltage Vt for the diode is measured to be 29 plus minus 2 millivolts. Okay, the effective thermal voltage Vt for the diode is measured to be 29 plus minus 2 millivolts. The resolution of the, okay, just give me a second. The non-ideal is tested by sweeping across terminal voltage plus -5 to +5 volts. The effective thermal voltage, okay, Vt is 29 plus minus 2 millivolts. Okay, the resolution of the voltage source, the resolution of the like smallest measured value that the voltage source can change is 1 millivolt, right? Okay, the percentage uncertainty in the measured current at a bias voltage of 0.02 volts. Okay, so they're asking me the percentage uncertainty at the measured voltage. So okay, they're asking me what is the percentage uncertainty in the measured current, not the measured voltage, measured current. So uncertainty, right, has, so uncertainty has another formula. So uncertainty with respect to what? With respect to the bias voltage. So do you know what is the diode current equation? Diode current equation ID is equals to I naught 1, sorry, e raised to power eta Vt upon, sorry, it will be Vd upon eta Vt minus 1. So now they are asking me what is the percentage of uncertainty in the measured current, right? How do I calculate the percentage of uncertainty? So I told you that deviation, what was the deviation formula in current, right? That I know. So if I am able to calculate that deviation in current upon the current ID into 100, this will be the, actually I forgot to mention this during the revision, that this will be my percentage of uncertainty, percentage uncertainty in diode current, correct? Now how do I find out ID and sigma D? You might have a question on that, right? So that is simply equals to this, right? So I know this, what is my sigma I. So this is also called as percentage uncertainty. This is also equals to my this value, sigma I, that is equals to under root. Now what is my current depending on? My current is depending on two values, right? One is this value, so one is Vd, one is Vt. My current is depending on two values, one is Vd, one is Vt, correct? So if I differentiate, so basically the formula is sigma I is equals to del Id upon del Vd, the forward bias voltage, upon sigma into Vd whole square, right? This whole thing will be squared, plus again del Id upon del Vt. It is also depending on the thermal voltage because your thermal voltage also is changing. Vt into Vt whole square. Okay. So yeah, how do I calculate ID? I will talk about that. Don't worry. I will talk about that. So what is del ID upon del Vd? So del ID upon del Vd, this can be approximated if I am in the forward bias, right? I naught is very small value, right? So this can be approximated like this, I naught into e raised to power Vd upon eta Vt. Okay, I naught is a very small number. Okay, we can, it does depend on I naught, but they have not mentioned anything regarding I naught. They should properly provide the equations actually, to be honest, but they have not mentioned anything regarding the I naught, so I will keep I naught just as a constant. Okay, don't worry about it. They have given me the value of Vt, and they have certainly given me the uh, measurement range of voltage source is 0.1 millivolt. Okay, at bias voltage of 0.02 volts, when the bias voltage is 0.02 volts, and this is the smallest range, right? So basically this is the deviation of my volt. So basically what is the circuit? The circuit is somewhat this is my voltage source, right? And this is my silicon based diode, and with the silicon based diode we will have a ammeter connected, not ammeter actually, we will have a voltmeter connected to the thermal voltage to measure the thermal voltage, also to measure the voltage across the silicon diode. This is the circuit, right? And the smallest change of the input, right? This is my source. Smallest resolution of the voltage source is 1 millivolt, right? So it is 0.001 volt. That is the sigma Vd, smallest change in the diode bias voltage that I can give. That is a deviation. Okay. And what about the change in the thermal voltage? Change in the thermal voltage sigma Vt is basically 2 millivolts. As you can see, it is 2 millivolts, and it is like the actual value is 29 millivolts. So sigma Vt is 0.002 volts. Okay, we will use all this. And if the bias voltage is 0.02 volts, right, assuming it to be an ideal silicon diode rectifier, silicon diode junction, we will assume that it is in forward bias. If it is in forward bias, approximately this will be the current. Why? Because we will have to make this approximation, otherwise you will not be able to solve this question. Why? Because we will have to differentiate our diode current with respect to the diode voltage. So if I differentiate our diode current with respect to the diode voltage, this would be equals to what? I naught will be as it is, I naught into I'm differentiating with respect to diode voltage, this will be eta Vt. Now again nothing is mentioned, so you will assume your eta to be 1. Okay, you will assume your eta to be 1 because nothing is mentioned, so we have to assume our eta to be 1, otherwise we will not be able to solve this question. So this will be I naught upon Vt into e raised to power Vd upon eta, e raised to power Vd upon Vt, right? Now what is this? This is nothing but my diode current itself. So basically this will be Id upon Vt. Vt I already know, right? Vt I already know, that is 29 millivolts. Cool. What about the second differentiation? So that's why we have to make this approximation, otherwise you will not be able to solve it. Now you will say, sir, how will I know I will have to make this approximation? You will not know. You are seeing me solve it, now you know, right? That's the point. You are seeing me solve it, so now you know, now you will use this. So delta Id upon delta Vt. So with respect to thermal voltage, again if I differentiate with respect to thermal voltage, this will be I naught, and Vd eta is 1, so this will be only, okay, this will be minus of Vd upon Vt square into I naught e raised to power Vd by Vt. Again this particular value is nothing but my current Id. So this is minus Id, this is minus Vd into Id divided by Vt square. Okay. So now we can solve it. So we actually need this value. So this is actually called as the percentage of uncertainty with respect to current Id. Okay. And this is called as a standard deviation in current Id, sigma I. Now if I replace these values, now remember all these are in, let's assume that everything is in millivolts. Okay. So what will happen if everything is in millivolts? This is also in millivolts, this is also in millivolts, right? Then everything will be cancelled simply, right? Don't worry, if everything is in millivolts, units will be proper. So this is equals to I will keep everything in millivolts. You can keep everything in volts if you want to, but you will get the same answer. This will be 2 millivolts, right? And what is your VD? It is actually 20 millivolts, right? Not 2 millivolts, 20 millivolts. Okay, and your VT is 29 millivolts. Okay, so we'll replace everything in this equation. So your del ID upon del VD would be IO, so ID upon VT whole square. ID square upon VT whole square. VT whole square is 29 square, right? So let me keep it here. So it is 29, and del sigma VD. Sigma VD is 1 millivolt. So again, milli will be cancelled. Don't worry about it. Milli will be cancelled. Plus delta ID upon delta VT, right? Delta ID upon delta VT. So this is this value, right? So again, your VD upon VT square. I can keep the ID outside, right? I can keep the ID outside. This will be outside ID square, and this will be minus of VD. VD is, what is VD? VD is 20 millivolt, right? Upon VT square. VT square is 29 millivolt. This is squared into, certainly into sigma VT. Sigma VT is 2 millivolt. This will be 2 whole square. Now if you see, I can take this ID common, right? Take this outside the root and take this in ratio. So basically, we, whatever they are asking, we can get that without even knowing the value of ID. So sigma I upon ID shall be equals to 1 by 29. Obviously your sigma VD was 1 millivolt only, so no changes here. So 1 by 29 whole square plus this value, right? So this is 40 square simply. So that would be equals to 40 square. So actually this is very small value compared to this one, right? So approximately it will be what, 40 upon 29, that's it. Sorry, 40 upon 29 whole square. So 40 upon 29 whole square into 100, right? So that would be around 4.7 percentage. If I, hold on, am I doing everything correctly? 20 into 2, yes, let me compute this, hold on. So 20 into 29, oh sorry, no, this is actually large, right? This is actually, so here there is 29. Oh, we cannot do it, so let's do it properly. So so 1 by 29 square plus 40 upon 29 square whole square, this whole under root is 0.589, and in percentage this will be 5. Basically in percentage you can compute this value. This will be 5.875 percentage. Okay, so 5.875, they have asked us to round off to 2 decimal places, so this will be 5.87 percentage. This will be your answer. This was a good question, right? So this is your standard deviation. Sometimes this also is called as percentage of uncertainty, but your actual definition of percentage of uncertainty is this one. Okay, I hope now with the question it is totally clear what do we mean by percentage of uncertainty. Let's solve this question. Two resistors 100 ohms having tolerance 3%, 4% are connected in series. The effective tolerance of the series combination, we know in percentage, right? So we know when two resistors are connected in series, we will just simply add their absolute errors, correct? So if I have a 100 ohm resistor and if it has a 3% tolerance, basically 3% error rate, that means in absolute terms it is 3 ohms, right? That is the first one. And in second term, if I have 100 ohm resistor, I am adding them in series, of course they will be added, both of the resistors will be added. Again it has 4% tolerance, that means plus minus 4 ohms, right? 4% of 100 is 4 ohms. Now if I add them, what will happen? This will be 200 plus minus, I will add the errors, so it will be 3 plus 4. Everything is in ohms here, there is no percentage term, right? Everything is in ohms. So this is 200 plus minus 7 ohms. Okay, now they are asking me what is the effective tolerance of the series combination in percentage. So if they are asking me in percentage, how do I calculate the relative error? Tolerance essentially is the relative error only. So it is error, maximum error upon the true value, that is 200 into 100%. So this will be equals to 3.3. 5 percentage. So 3.5 percentage is your answer for the question. Okay, yeah, let's solve the next question. This is the next question. In an AC main, the RMS voltage VAC and IAC and the power are measured as such. Okay, so these are all relative errors that is given. The percentage error in calculating the power factor would be, what is the percentage error in calculating the power factor? So do you know what is your power factor? Do you know what is your power factor? So we know that P is equals to, whenever I discuss P is equals to V into I in today's lecture, that was for DC instruments, right? For AC instruments, P is equals to VI cos phi, correct? So your power factor cos phi is actually equals to P upon VI, right? So how do you compute your relative error? So again, if you want to do few approximations, so your P is simply WAC. So this you can write as WAC plus delta WAC, right, upon V plus delta V. This is just the error into I plus delta I, correct? If I take all this common, WAC, V and I, correct, and this is my cos phi measured value, right? Measured value. So cos phi, this is the measured power factor. So this will also be power factor measured. So power factor 2 value plus delta PF, correct? One plus delta V by V, 1 plus delta I by I. Okay. Now what I can do, this is nothing but the true power factor value, right? This is PF true value. Okay, so I can divide this on both sides. So this will become 1 plus the relative error in the power factor. Okay, right? Because this is the true value and this is also the true value. This will be 1 and this will be delta PF upon the true value. So this is will be delta PF, del delta PF, and this will be 1 plus del delta WAC. Now here what is happening, if you see this, if I go take it into the numerator, right, this is nothing but 1 this is nothing but 1 plus del V by V inverse. So that essentially basically means this will be equals to 1 minus delta V upon V. Why? Because again I can take the first order approximation as I mentioned previously. So this will be simply converted into this value, 1 minus delta V by V into 1 minus delta I by I. Again we can make few approximations, right? Again if this 1 will be 1 only, right? Then if I am multiplying these two numbers, it will be 0, because this delta, if you see, okay, this is nothing but del delta V relative error in voltage and relative error in current. Okay, so actually we don't need to provide delta, right? So this will be just the relative error. Yeah, 1 second now. This will be just the relative error. We don't need to provide even the delta symbol. Yep. So yeah, you will see, right, as this is very small number, 1% is 0.01, 0.01 into again 0.01, that will be very small number. So you can simply neglect that. Ultimately what will be your number? So you will multiply these number, this into delta WAC. So whenever there is multiplication of two deltas, right, that will be approximately 0, because that is a very small number. So this will be delta WAC minus delta V minus delta E. Other numbers can be ignored. So ultimately your relative error in power factor will be delta PF would be delta WAC minus delta V minus delta I. This will be your change or relative error in power factor. So what is WAC? That is 2%, right? Okay, just one small change. Uh, yeah, here this is plus minus 2%, right? This is plus minus 2%, plus minus 1%, plus minus 1%. Now what you'll do, you will choose your delta PC, not PC, sorry, choose your delta PF such that it is maximum, right? So both delta, there can be positive and negative error. So I will choose the value such that it is maximum. So basically, right, ultimately your answer would be delta PF would be equals to absolute value of WAC plus absolute value of delta V plus absolute value of delta E. Why do we do it? Because we want to compute for the worst possible scenario. Because you can see, right, it can be both positive and negative. Now I don't know when this is positive whether this will be negative or positive, right? So we will have to compute for the worst case scenario. So I will compute for the maximum error, right? Maximum error. So maximum error will be this. Now I can write the maximum value here, maximum value here, maximum value here. This formula is safe. So this will be maximum value of delta AC is 2%, right? Maximum value of delta V is 1%, maximum value of delta I is again 1%. So overall the error in the power factor would be 4%, right? It will be 4%. So make sure you at the end write the absolute values. Okay, make sure at the end you write the absolute values, not with the same sign. Why? Because your delta V and delta I, if you see, they are changing, their signs are changing. So it's not like when this wattmeter will give me negative error, this will give me positive error. You don't know it, right? We don't know it, right? So certainly we will calculate for the worst possible scenario. So that's why this will be 4%. Let's solve this question, right? Okay, the temperature of the coolant oil bath for a transformer is monitored using circuit shown. It contains a thermistor with a temperature dependent resistance. Okay, thermistor, so which has a temperature dependent resistance. Thermistor resistance is given by this formula. RT is equals to 2 into 1 plus alpha capital T kilo ohms, where T is the temperature in degree centigrade. The temperature coefficient alpha is this value. Okay, this also has some percentage change, okay, in percentage, and units is per degree centigrade. Okay, this is in percentage per degree centigrade, percentage per degree centigrade. Okay, the circuit parameters are this. The error in the output signal V out would be equals to what in volts. Okay, they have asked in volts. Okay, so they are asking me the absolute error in the output signal at 150 degrees centigrade. Okay, how do I compute the absolute error? So R2, R3, these values are given to me. If all the values are given to me. So essentially this is an ideal op amp. So if it is an ideal op amp, no current is flowing through here. No current is flowing through here, right? So what is the voltage here, right? If I apply superposition, right? If I apply superposition, assume this source is not active, then this voltage will be VO into R2 upon R2 plus R3. And if I assume superposition, if I assume this source is not there, this is grounded, and this source is there, right? Then this voltage would be 0.1 upon into R3 upon R3 plus R1, right? So these are the voltages if we apply the superposition theorem properly. Okay, voltage at this node, at the non-inverting node, right? And this voltage shall be equals to the voltage at the inverting node because it is in negative feedback. So basically the non-inverting voltage, sorry, this is the voltage at the inverting node, and the voltage at the non-inverting node should be same as the voltage at the inverting node, right? So what is the voltage at the non-inverting node? This will be 3 into R1 divided by R1 plus RT, right? So your V out would be simply 3 into R1 over R1 plus RT minus 0.1 R3 over R3 over R1 into R3 plus R1 divided by R2. So R3 plus R2 divided by R1. Okay, this is your V naught. Now we will have to calculate the error in V out, that is delta V out in absolute terms, right? Basically, how do I calculate that? It will be basically V out 1 minus V out 2. What is that? So it basically means the output voltage when my alphas, because what is varying here? Only my alpha is varying. So when my alpha is equals to alpha 1, whatever was the output voltage, when my alpha is equals to alpha 2, whatever was my output voltage, the difference would give me the error, right? Because ultimately what is changing? My alpha. So whenever there is a delta of alpha, what is a delta in V? That is what they are asking me, correct? So let us calculate that. Let's take for the case when my alpha is alpha 1, that is this is how much? Minus of 4 plus 0.25 percentage. Remember, this is percentage, not absolute value, not like unitless, right? So this will be minus 4.25 percentage, that is minus 4.25 by 100 per degree centigrade, correct? This is my alpha value. Now what is the output voltage in this particular case? So what is the, so for this I will calculate what is my RT1. RT1 would be 2 into 1 plus alpha, that is minus 4.25 upon 100 into the temperature. Temperature is they told me that they are working in 150 degrees centigrade. 150 degree centigrade, right? So units will be cancelled, don't worry about that. So this shall be equals to, just give me 1 second, 150 upon 100 into 4.25, okay, which is quite large. How is this coming negative? 13 to 150 alpha into T, right? Okay, this is per degree centigrade. Yeah, 100. Temperature is 150 degrees centigrade. Okay, so yeah, it is coming out to be negative, so I think that is fine. So the resistance is coming out to be negative. I don't know thermistor resistance, can it be negative? If it has to be negative, it has to be, I don't know, like I think there is some discrepancy in the question, but okay, whatever is coming we will solve that according to that. Minus then plus 1 into 2. So yeah, just give me 1 second. 150 by 100 into 4.25 minus plus 1 into 2. So it is minus 10.75 kilo ohms. Okay, it is coming out to be negative, but I don't know, it can be negative Thermal resistance, how can be negative? I don't know. Something is wrong in the form. I think this should be 1 minus alpha t. I don't know. Something is wrong, but let's not get into that right now. So if it is coming out to be negative, and what is my R1? R1 is 1 kilo ohm. I think they have made some mess up. This should be negative here. This should not be positive. That is what I'm assuming. I don't know. So yeah. So what will be the voltage in this case? V naught 1. V naught 1 would be 3 into R1. R1 is 1 kilo ohm upon R1 plus RT. So 1 minus 0. Everything is in kilo ohm, so you don't need to worry about it. Minus 0.1 R3. R3 is 2.6 upon R3 plus R1. R3 plus R1, that is 2.6 plus 1 into R3 plus R2. R3 plus R2. So R3 is 2.6, R2 is 1, R2 is 1.3. So 2.6 plus 1.3, that is 3.9 upon R2. R2 is 1.3. So let me solve this. This plus 1 into 3, then that will be difficult for me to solve. So this is minus 0.307 minus, what is this value? 0.1 into 2.6 upon 3.6, that is minus 0.0722 into 3. So this minus 0.307 into 3, so minus 1.137 volts. Okay, so yeah, VO2, what will be VO2? VO2 will be when my alpha is 4 minus so when it is negative, right? So alpha 2, basically it will be minus 4 minus 0.25 percentage per degree centigrade. So this will be 3 minus 3.75 by 100 per degree centigrade. Okay, so VO2, if I solve for VO2, what will be the answer? Yeah, let me solve it. So what will be RT2? RT2 would be equals to 2 into 1 plus alpha T, right? Alpha is basically 3.75 by 100. Temperature is 150, right? In kilo ohms. Everything is in kilo ohms. So this would be 3.75 upon 100 into 150 plus 1 into 2. So minus 9.25 kilo ohms. Okay. Now 3 into R1, right? R1 is 1. 1 minus RT2 9.25 minus 0.1 into 2. So this value is same, right? This value will be same. This value will not change. Minus 0.0722 into 3. This value also will be same, right? This will not change. So this plus 1 into 3 minus 0.0722 into 3. So it approximately comes out to be minus 1.307. Okay. So that is the approximate value. So what will be your delta V? delta VO2, delta VO1 minus delta VO2, like the absolute value. So this minus 1.137, which is approximately 0. Yeah, 0.170 volts. Okay, so this is your delta VO. What have there was the error in the output signal. What is the error, absolute error in the output signal? Now we got two values, right? Now what is the okay, I told you the okay, hold on, sorry, this statement is actually kind of wrong. This is not your error, right? So I'm sorry, what I was doing. So okay, we computed two values, right? We computed two values. So our error, this definition was wrong actually, sorry. Our error would be, what would be our error? Basically our error would be mod of maximum mod of maximum between the difference between the true value of the first case and between the difference of the true value of the second case. I'm sorry, I was like, I was referring to this formula. I was just had a bit of brain fade at that point of time. So whatever is the maximum value, that I will report, and then I will take the absolute value, right? So true value error will always be, sorry, this will be with respect to true value. So true value minus VO1, that is a measure value, right? That will give me the error, how much far off I am from the error, right? So sorry, this will be measured value minus the true value, that is my error, right? Yes, measured value minus the true value. So if whichever one is maximum, I will choose that. Whichever one is the highest value, I will choose that. Sorry, not, don't choose this. Let's take the mod here and let's decide whichever one is the highest value, that will be my actual error. Okay, because I will compute for the worst possible scenario. Okay, so yeah, I do agree, bit difficult. This question is bit difficult, but yeah, let's solve it. So what is the true value? This is not delta V. So this is just the, so I got my VO1 and VO2. I'm sorry, I just had a brain fade at that point of time. So my VO true value, right, would be equals to, these values will be same, right? These values will not change. Ultimately, we'll just have to compute the RT, right? That is what we are concerned about, the true value of RT. What is the true value of RT? True value of RT would be basically, according to the true value of alpha, alpha will be 4, right? Minus 4 upon 100 degree per centigrade. So true value of RT shall be equals to 2 into 1 minus 4 upon 100 into 150, okay, in kilo ohms. So this will be 4 into 150 upon 100 and minus plus 1, 5 into 2, basically minus 10, right? So true value is minus 10 plus 1, so this is minus 10, okay, kilo ohms. Now this will be minus 10 into 3 minus 0.077222 into 3. So minus minus 1.12167 volts. Now we will compute the error actually. Let me keep it, let me use few other decimal places, 6. So what is the difference in the first case? So let's say delta VO in the first case, right? Difference in the first case, it will be, I will take the absolute value, correct? Absolute value of the measured quantity, that is minus 1.137 minus of 1.2166, right? This shall be equals to this minus 1.137, the mod, this is actually equals to 0.07966 volts. What is the error in the second case? Delta VO2, this will be equals to, actually I think there is easier way to solve this actually, but today is not the day. I am guessing today is not the day. This will be 1, so this is the mod, right? Remember, this is the mod, this is the modulus function. So modulus of the measured quantity here is 1 minus 1.307 minus 1.307 minus of the actual quantity, that is minus 1.2166. So this will be 0.0934 volts. Okay, so your maximum error would be, basically your delta V maximum error would be 0.09 volts. This will be your answer, because they have asked in, I think, 2 decimal places, right? 2 decimal places, so 0.09 should be your answer. Now I'm thinking, is there a easier way to solve this? So what do I observe? All these values all are constant, only this is in the denominator, right? So can I write in terms of my relative error? Can I solve this in a easier method? Can I write this in terms of my relative error? Okay, just hold on a second. Screen got, give me 1 second. Yeah, now I think we are back. Yes. So let's write this in terms of our relative error. So we know that our delta V, right, would be equals to, because it is in fraction, right, it is in division, I can say it will be equals to delta R. Why? Because nothing else is changing, right? All we are doing is, what is happening, this is in fraction, right? If it is in fraction, we know that whenever there is division or addition, we know that, so let's say I have division of 2 quantities, right, V by I. So let's say this is my R. So what is delta R? Delta R is basically absolute value of delta V plus absolute value of delta I. So let's say if I have only one quantity I, so it will be equals to absolute value of delta I, right? So that is what we are doing, because only one term is there in the division, we are doing absolute value of delta R. Let's see if it works out or not, right? So this is absolute value, remember, not delta R, sorry, yeah, absolute delta R, which is actually what? Delta R again is dependent on alpha, which is again coming in the product, right, which is proportional. So this will be absolute value of alpha. So what is the absolute error of alpha? Remember, this is percentage per degree centigrade, right? This is percentage per degree centigrade. Okay. So yeah, percentage per degree centigrade. So this would be equals to what? Yeah, percentage per degree centigrade, right? So what is the relative error? It will be the error upon the true value, that is 4, right? So it is actually equals to 1 by 16. Okay, error upon the actual value, right? 1 by 16. So 1 by 16 is the relative error, right? So basically your delta V also will be 1 by 16. Now what is my true value? So this is my delta V, right? So now what is your delta V? Delta V is actually equals to your error in V upon the V true value, correct? So V true value is what? V true value is this, right? Minus 2.11. Okay, so your error in V would be, I will take the modulus because we want to compute the absolute value upon 1 by 16. So just let me check, like I'm just checking whether this will work or not. This may or may not work. This is approximately equal, not exactly, but I think this will work. So this is 0.076 volts. Okay, so roughly your answer would be similar to this. As we can see, like, yeah, we are a bit far off, but as they have told us to round off to 2 decimal places, we are not that far off. If they give enough range, we will be near to our answer. Okay, if they give enough range, and I think they will give enough range. So shortcut is to solve using this relative error concept, or otherwise you can solve it using the long method, that also will work. Just there was a bit of brain fade from my end here, right? I was thinking about something else, then I discussed, no, that is not the correct way to compute the error. This is the correct way to compute the error. Okay, let's finally solve the next question. Independent voltage measurements, mu plus minus sigma, right? So mu is the mean, sigma is the standard deviation of three sensors, where mu and sigma are the mean and standard deviation, are as follows. The measured uncertainty v1 plus v2 plus v3 shall be equals to what? Okay, so measured uncertainty basically will be, they are asking me what is the sigma in v. Very simple, sigma in v would be delta v upon delta v1, that is 1, into sigma v1, that is this. Is this the correct one? No, sigma v1 would be the, it should be yeah, that is correct. Sigma v1 is, units is 0.02 volts, that is correct. Yeah, this should not be unitless, this is correct. So this 0.02 volts whole square, correct, plus delta v upon delta v2, that is again 1, into sigma v2, that is 0.2 whole square, plus delta v upon delta v3, that is again 1, right? I am differentiating this function with respect to v3, that will be 1, into sigma v3 whole square, that is this. Then I take the, sorry, this will be whole square, then I take the under root. So what will be this? That will give me the whole degree of uncertainty, measurement uncertainty of the whole quantity, right? v1 plus v2 plus v3. So this will be 0.2 square plus 0.2 square plus 0.15 square under root. Okay, just give me 1 second. 0.02 square plus 0.2 square standard deviation, right? Yes, plus 0.15 square and root. Yeah, this comes out to be 0.25 volts. So your measurement uncertainty is in 0.25 volts. This is the answer. Now you might have a doubt, sir, what if they have asked this particular quantity? This is also defined as measurement uncertainty, right, in percentage. So whenever this particular quantity will be asked, you will see the units will be unitless, it will be dimensionless, right? They have asked in volts, that means they are talking about this quantity, the standard deviation. If you see here previously, the thing that we calculated here, this was in percentage, right? In percentage, the percentage uncertainty. If they are asking about the percentage uncertainty, then that is the unit, that is how you compute the percentage uncertainty. And if they are talking about just uncertainty, then they are talking about the deviation, that's all. Okay, that's how you understand that what formula do they want to use. Okay, let's solve the next question. This is the next question. 5 measurements are made using weighing machine. Readings are 80, 79, this is this. The sample standard deviation of the measurement is. So they are simply asking you what is the standard deviation of the sample. So how do you calculate the standard deviation? Do you remember? It is not even a question of measurement, it is question of statistics. So if you know that our standard deviation, right, variance square, right, sigma x square is actually equals to summation of xi minus mean whole square upon n. This is the standard deviation whole square formula, right? So yeah, that is how we will calculate here as well. So what is the mean here? Mean would be sum of all the elements, that is 80 plus 79 sum of xi upon n, that is equals to 80 plus 79, that is 79 plus 81, 79 plus 81, it is nothing but 80 plus 160 and 160, that is 320, that is 400. So it is 400 upon 5. I have taken 5 measurements, so it will be 80. 80 will be my mean. Okay, so it will be 80 minus first measurement, right, is 80 itself. So 80 minus 80 is 0. So 0 square plus minus 1 whole square plus 1 square plus minus 1 whole square plus 1 square upon mean, right? That is my sigma x whole square. So this would be equals to 4 by 5, that is 0.8. So your sigma x whole square is 0.8. So your sigma x, the standard deviation, would be 0.8 under root, that is 0.89. Okay, so it will be 0.9 kgs. So your answer would be 0.9 kgs. That would be your standard deviation of the measurement. Okay, let's solve the next question. The resistance of a 20 kilo ohm resistor is measured in 6 consecutive times using an LCR meter. These are the readings. The mean of the measurement and the true value are equal. The last reading is equals to what? Okay, so I'm 1, 2, 3, 4, 5. They have given me the 5 readings. They have not given me the last reading, but they are telling me that mean of these all recordings will be same as the true value. True value is 20 kilo ohms. So 20 should be equals to the mean of the readings. So it is 19 plus 18 plus 23 plus 21 plus 17 plus x. X is the last reading upon the mean, that is 6, right? That will give me the mean. So let me do this. So 19, so there is not even a question of measurement, right? These are questions of statistics. Plus 18 plus 23 plus 21 plus 17, okay, this will be subtracted from 120. So the last measurement would be 22 kilo ohm. Okay, last measurement x would be equal to 22 kilo ohm. This would be your answer for the question. Okay, let's now move on to the next question. This is the next question. The measured value from a flow instrument whose range is between 0 to 2, okay, is given. These are the measured values basically, and this is the true value. We are very far off our true value, so it is certainly not accurate, but seems it is precise. The systematic error bias and the maximum error is, okay, they are asking me what is the systematic error. So how do you compute the systematic error here? So systematic error would be, actually this I have not told you because I guess they will not ask in doubly, so that's why I am not explaining what is systematic error, what is the absolute error. So systematic error will be the like mean of your measured value, right? Not the exact formula. I'm not saying you here the exact formula, but approximately it will be mean of the measured value minus the true value. Okay, so you see the mean of the measured value is 0.37, right? Like highest frequency wherever this measured value is coming, 0.37 minus the true value. True value is 0.25, right? So your answer would be 0.12. Okay, that is your systematic error that is present in option A. And the maximum error in flow units. What is the maximum error? Maximum error would be this, right? If you see, maximum error is happening here, like the highest value, wherever there is the maximum deviation. So it is 0.39 minus 0.25, that is 0.14. So anyways, you can see the maximum error is only present in these two options, right? These are not even correct. So anyways, you can eliminate these two options. So ultimately you are left with these two. Now you will have to take a guess. So if we write systematic error to be 0.1, that will be something wrong, right? Because here I am saying these are the frequencies, right? The number of occurrences of the reading. This is very low. 0.35, I am reading 0.35 very low amount of times. So this is not correct for systematic error. It will be whenever I am getting the highest values, like wherever I am getting the highest number of occurrences. Okay. So yeah, option A is correct for this particular question. So yeah, let's now move on to the next question. This is the next question. The measured current through a device is 5 ampere. Okay. The voltage measured across the device is 20 volts. The ammeter and the voltmeter used for this measurement have an uncertainty of 1% each. The maximum error in estimation of the impedance of the device in milliohms would be. So we are estimating the impedance, right? So Z is equals to what? V upon I. So if Z is equals to V upon I, we know the maximum error in impedance will be delta V, absolute value of delta V plus absolute value of delta I, right? We know this, we have derived this. So it will be basically 2%. Okay, because each has 1% of uncertainty. So what is your delta V? Delta Z? Delta Z would be the error in Z upon the true value of Z. True value of Z would be voltage upon current, that is 4 ohms equals to 2%, right? Equals to 100. So your error, they have asked in milliohms, right? Milliohms. So if they are asked in milliohms, this will be in ohms. So I can multiply this by 1000. So this will be cancelled, right? This will become 20 into 4, that is 80 milliohms. Okay, 80 milliohms. So 80 milliohms would be your answer for the question. Let's solve this question. Like there are a lot of questions that were asking like gate, INN stuff. That's why I'm taking these questions. So this is a good question actually. Here that asking me the maximum percentage error in the equivalent resistance of two parallel connected resistors of 100 ohms. Okay, this and this, right? With each having maximum error of 5%, right? What is the maximum percentage error? So what is R equivalent? R equivalent is simply R1 R2 upon R1 plus R2. So I know if these two are in product, right? I certainly know the error in R equivalent would be delta R1 absolute value of delta R2 absolute value. This will certainly be true. But what about this one? How do I compute the absolute error of R1 plus R2? So for that I will how do I calculate the relative error of R1 plus R2, right? This is in division, so what will come here? This will be the relative error of R1 plus R2. So for that, let me first compute the absolute error of R1 plus R2. So R1 plus R2 shall be equals to 100 plus 5% is its error, right? So 5% of 100 is 100 and is 5 plus 900, and 5% of 900 would be 45. Correct? So this will be 1000 plus minus, so this can be plus minus plus minus plus minus 50. These are all absolute units. So this actually is equals to what? 1000 plus minus 5%. So R1 plus R2 also has a relative error of 5%. So what will happen? This will be 5% plus 5% plus 5%. And here you will be actually wrong, because previously when I derived that formula, right, when we take these absolute values, there I was talking about when all these quantities are independent. This quantity, all of these are independent. But are these independent over here? No, they are not independent, right? These two quantities are certainly independent, R1 and R2, but this quantity certainly is not independent. Okay, this quantity certainly is not independent, right? This particular quantity is dependent on the previous values, right? R1 and R2, it is certainly dependent. R1 and R2 is R1 plus R2, sorry, like it is dependent on R1 and R2. So here, how to solve this? How to solve this? So here you will not actually, like, first of all, you can solve with basics. So whenever these kind of question comes, if anywhere you are in doubt, okay, if you have enough time, solve with basics. Okay, so first method I will solve with basics, right? What is with basics? Basics would be just choose the maximum value and the minimum value, that's all. The highest error and the lowest error. Okay, so when both of them are highest values, okay, right, and both of them are minimum values. So case 1, both high, and case 2 both low, right? So case 1 when both are high, okay, both are high, case 1 uh 1 both are high, right? Case 1 both are high. So when R1, so what can be the highest value of R1? Highest value of R1 would be 100 ohm plus 5% of this, that is 105, right? So R1 is 105 and R2 is 945. What is the equivalent? That is equals to 105 into 945 upon this will be 1050. Okay, so I will recommend you use this formula when they are independent. If they are dependent, right, if these values are dependent, then you solve with basics. Okay, use that formula when they are independent, then there is no problems. But when they are dependent, don't use this. That is my recommendation. Don't use this. When they're independent, you can safely use that. You will not have any issues, no problems. Okay, so yeah, this value, if I compute this value, so this would be 105 into 945 1050, so 94.5 ohms. So 94.5 ohms. Okay, that is your R equivalent in the case 1. What is the R equivalent in the case 2? Case 2 R equivalent would be when your R1 is minimum, that is 95, and your R2 is also minimum, that is 5% of that, right? So it will be 855, okay, ohms. So then what is your R equivalent? R equivalent would be 95 into 855 upon, so 95, 5 is 60, so 860, 40 and 50, that is yeah, 950. So it is 85.5 85.5 ohms. Okay, 85.5 ohms. That is my R equivalent. Now what is the true value of my R equivalent, right? True value of my R equivalent. True value of my R equivalent shall be 90 into 900 upon 1090. Am I correct? Sorry, what I'm doing? Sorry. Yeah, 90, 100. Sorry, this will be 100, right? 100 into 900 upon 1000. So this will be basically 90 ohms, correct? 90 ohms. So what is the maximum error? I can see the maximum error here. It is 4.5 ohms. Here it is 5.5. Here it also it is 4.5 ohms, right? So the maximum error that you can observe is basically 90 plus minus 4.5 ohms. In ohms, absolute values, in percentage, this will be 90 plus minus 5%. So what is happening? Simply, right, previously whatever I derived, whatever formulas I derived previously, this was, so let me derive this formula again. If they are dependent, then you cannot actually use this formula, right? Then you cannot use this formula. So I will recommend don't use this formula if they are dependent. If they're independent, certainly you can use it, no problems. If they're dependent, you will face problems. So solve with basics. Okay, solve with basics, don't use this formula. That is my recommendation. Okay, so yeah, with that the answer would be 5%. That is the maximum error that we will see. So it will not be 15%. Okay, so just be careful while using that formula. So I'm telling you why you cannot use that formula as well, right? So this is the next question. A series RLC circuit resonates at 7500 radian per second for inductance L equals to 20 millihenry, resistance R equals to 10 ohms. The uncertainties in the measurement of L and R are this, right, respectively. The percentage uncertainty in the measurement of the quality factor is what percentage? Okay, the percentage uncertainty in the measurement of the quality factor is what? So what is quality factor for a coil? It is omega naught L upon R, right? Now again, this time I can safely use my formula. Why? Because resonant frequency is constant. Only L and R there are uncertainties, correct? L and R there are uncertainties. So if I know, okay, if I know L and R values, so what will be the percentage uncertainty here? It's very simple, right? So now you can use this formula, the percentage uncertainty. Okay, they have asked the percentage uncertainty, right? So there are multiple formulas that you can use. Okay, no, we don't need to calculate the error, right? We need to calculate the percentage uncertainty. So percentage uncertainty would be this: sigma q upon q into 100 percentage, right? So this equals to delta uh, delta q upon delta L into sigma L. Okay, so this is what I have to calculate. So for that, first let us calculate sigma q, right? And then I will multiply, I will divide by q and multiply by 100. Okay, plus delta q upon delta R into sigma R, right? All these are squared, obviously, don't forget these are all squared. So what is delta q upon delta L? Delta q upon delta L, right? So this will be basically omega naught by R. Okay, so that is my delta q upon delta L. So what I can do, if I multiply both sides by L, right, this is nothing but q. Okay, this is nothing but q. I want to write everything in terms of q. So my delta q by delta L can be written as q by L. Okay, that will help me, don't worry. And what about if I differentiate with respect to R? If I differentiate with respect to R, this will be minus omega naught L by R square. Okay, minus omega naught L by R square. Now again, I can take one of the R on the other side and negative sign also on the, okay, let me keep. So this is essentially equals to what? Minus q upon R. Am I correct? Yeah, omega naught L by R. Yeah, minus q upon R. That is my delta q. How are both coming to be same? I'm curious. So what I'm doing here, I'm differentiating this L, multiplying by L. Okay, both are coming to the same. That's good. Yeah, this is minus q by R, right? So actually I can now rewrite these values. So it will be sigma q equals to under root q by L into sigma L. Sigma L, what is sigma L? Sigma L is given to me, right? That is 0.8 millihenry. Okay, and your L is also 20 millihenry. So don't worry if you are writing millihenry here, your L also is in millihenry. So automatically the units will be cancelled. Correct? So this will be squared plus q upon R. Again your R is in ohms and this is also in ohms. So this will be 0.3 whole square. Now what I can do, I can take this q common, right? I can take this q square common. So ultimately I am directly computing sigma q upon q, that is equals to 0.8 by L. L is 20, right? So 0.8 by 20 whole square plus 0.3 by 0.3 by 10 whole square. Point 0.8 by whole 0.8 by 20 whole square plus this is 0.03 whole square whole under root. So this comes out to be 0.05, right, sigma q upon q. So we will have to compute the percentage, that would be equals to or 5%, and your 5 is the answer for this particular question. Now we will start off with the measuring instruments. Let's start with measuring instruments. So we will discuss about analog meters. There are multiple kinds of instruments: indicating instruments, recording instruments, integrating type instruments, and null deflection type, right? So first we will discuss about indicating type instruments, where we have ammeter, multimeter, voltmeter, sorry, and wattmeter. Okay. Then these are the instruments that we will discuss later. So we will mainly discuss about analog instruments here. So ammeter, voltmeter, wattmeter, and energy meter. CRO will be discussed later on. Potentiometer also will be discussed later on. Okay. So these are the basic forces involved in the measuring instrument, indicating type instruments. What deflecting torque is the force. Deflecting force is the force responsible for creating the deflection, right, of the pointer. Basically, it is the fundamental quantity that which we are trying to measure. So let's say voltage, if I am trying to measure in a voltmeter, so the voltage signal will produce the deflecting force, and with help of deflecting force, of course, we can generate the deflecting torque, right? Torque is nothing but force into distance from the center, right? Then we have controlling force, then damping force. Okay, so controlling force is the opposing force that will control the pointer, because if you, so there is my pointer, right, and if I always have this constant force to the pointer, what will happen? This will only keep on rotating, right? That is what we don't want. We want this particular thing to stop at steady state at a certain angle, right? So of course, whatever force I'm applying or whatever torque I'm applying with deflecting torque, a similar opposing force must be there, that is called as controlling torque, that will control and keep the pointer in a steady state position, that is at theta equals to theta, whatever the value, and at that pointer it will point me to the correct voltage value. Okay, that is what controlling torque does. It is generally equals to, the controlling torque generally is used by the help of spring, which is equals to K into theta. Okay, so basically whatever is the deflection, it will provide the same amount of opposing torque. That is my controlling torque equation. And damping torque is something that happens when, let's say, you have this pointer, right, and you are providing some deflecting torque, due to which it is going on the clockwise direction, and as soon as the pointer will rotate, there will be some controlling torque opposing force that will be somewhat less than the deflecting torque. What will happen near its steady state position? This will just keep on oscillating. So this particular pointer, the displacement of this pointer will behave as a second order system. If you have studied control system, you will know this will behave as a second order system, where it will revolve around its steady state. This will be its steady state, right? Revolve around a steady state. So certainly, to reduce this dampings, we will have a additional force, that is damping force, damping torque. So if I want to get to my correct measurements in a short amount of time, so I want to have damping pretty high, so that the pointer correctly goes to the proper angle, right, and represents the proper value that we want to measure. It does not oscillate in the steady state value. So to reduce oscillations, we need damping force. So these are the three forces. So we see this is the deflecting torque. Now there is this very important formula for a permanent magnet moving coil. There is this derivation, but of course don't have to understand the derivation for now. This equation is very important. Deflecting torque for a permanent magnet moving coil, PMMC, right? Okay, PMMC instrument. Any PMMC instrument, if you have, the deflecting torque will be BNA, where B is the flux density, I is the current through the coil, N is the number of turns of the coil, and A is the area, cross-sectional area of the coil. Basically, whatever area that the coil is covering, that this cross-sectional area. All these values will be given. All you need to do is remember the formula. Deflecting torque is equals to BNA. And controlling torque, as I told you, we control it with the help of spring. So spring controlling torque is simply equals to Kc into theta, where Kc is a spring constant, theta is the amount of deflection. So at steady state, your deflecting torque and your controlling torque both will be equal. If both of them are equal, your BNA will be equals to Kc into theta, right? Theta will be equals to BNA by Kc. That's it. So from here we can see that our theta is directly proportional to I. If all the remaining values are constant, then it is directly proportional to the current through the coil. So the deflection is directly proportional to the current through the coil. So we can use it as an ammeter. Certainly we can use it as an ammeter. Also we can use it as a voltmeter as well. How to use it as a voltmeter? So let's say I am measuring the voltage across this resistor Rx. Measuring the voltage across this resistor Rx, right? So yeah, if it is Rx, what will happen? This will be, and how do I measure the voltage across this resistor? So what will I do is I will connect a voltmeter. So generally voltmeter has very high resistance, and this is my voltmeter, this is my meter actually. So if this has a very high resistance, right, approximately the current through this will be equals to what? It will be basically, if you see what is the current through this, the current through this, if let's say this is the voltage, right, V across the resistor Rx, current will be equals to V by RV, where my RV is constant, right? So my current is proportional to voltage. So that is what we do basically. We connect a resistor of very high resistance along with the voltmeter. Essentially this is an ammeter only internally, okay? But if I connect a very high resistance with an ammeter, what happens? It is converted to a voltmeter because it will not cause any loading effect to this particular resistor, okay? So if the voltage is V, what will happen? The current will be proportional to the voltage across the resistor, and we know current is proportional to the deflection. Hence we will be able to, hence our deflection will be proportional to voltage. So the same PMMC instrument I can use as a voltmeter, as an ammeter as well, okay? So these are the applications. Now PMMC instruments will always be used to compute the average values, okay, DC values. They will not be able to measure the AC values. Why? Because if you see, our theta is directly proportional to I. So what is I? Let's say I is a sinusoidal quantity. So what is the average deflection theta over a cycle? If you compute the average deflection theta over a cycle, if you connect a AC signal to a PMMC instrument, what will happen? It will just oscillate, right, from right to left. Why? Because your current varies from minus Im to plus Im. So it will just oscillate. If the omega is very low, it will just oscillate around 0, okay? And if omega is very high, your pointer will not even move. So your PMMC instrument is only used for DC measurement. Then there are few ways with which we can connect a parallel shunt resistor to extend the range. You can see the mathematics. I will not explain here. Simply what we do, if I want to extend the range of my meter, right? So let's say my meter can support 10 amps of current, but let's say the circuit has 20 amps of current. So what I will do, I will connect a shunt resistor such that the extra 10 amps of current will flow through here, and the maximum current that the pointer can support, that is 10 amps, will flow through the meter itself. So although I am able to measure the proper current, because we know that this current and this current, all these will be proportional to each other. So ultimately you will be able to get to a reading, but there will be a multiplication factor. That means if your meter reads 10 ampere, that means actually in the circuit it has 20 amperes. Similarly, if your meter reads some other value, 5 ampere, your actual reading would be some other value, m multiplied by the whatever reading that you are receiving, okay? All that depends on the circuit connection. So don't worry about all this. Simple KCL KVL. Remember your concept that we will connect a shunt resistor, and with that I will use simple KVL KCL to calculate the actual current in the circuit. If the meter has some amount of current, I will use my concept of KVL KCL to calculate the actual current in the circuit. That is what you need to understand. If you are worrying about multiplication factor, don't worry about it, okay? You will solve few questions, you will realize it. Similarly for voltmeter as well, you can simply connect a series resistor with the voltmeter and the range will be further extended. Don't have to worry about this. Now this part is pretty important, that is the sensitivity, okay, that we discussed, right? So the change in the output with respect to change in input. So in this case we know that theta upon I is equals to B in a KC, and this particular term is actually called as my sensitivity. the minimum change in the output with respect to input. So if these quantities are given, then you can say what is the sensitivity of my DMMC instrument. Now sensitivity is sometimes also called as figure of merit. Okay, so it is basically equals to 1 by IF full scale. So basically what happens is your sensitivity, right? Your sensitivity is sometimes measured in this unit, and this again I will tell you to just remember this part. Okay, your sensitivity will be inverse of your full scale current. Sensitivity of your measuring instrument will be inverse of for a PMMC instrument. The sensitivity of an instrument will be 1 by full scale value. There is a derivation, but currently let's not go into that. Just remember this for a PMMC instrument. This will be the sensitivity, and it's not that hard for you to remember. Okay, so if the full scale value, if the full scale current, right, per division, full scale value per division, if it reduces, then your sensitivity increases. Okay, so this is how you can intuitively make it sense, but don't worry if you are not able to figure out this. In the exam hall we will be able to solve questions even if you don't know this formula. Even if you don't know it, right, you will be able to solve questions. Once you see 1-2 questions, you will realize it. Now we will come back to our moving iron instruments. So in moving iron instruments, the deflecting torque is simply half I square dl by d theta. Okay, so it is proportional to current whole square. It is also proportional to dl by d theta, right, which is non-linear, right, which is non-linear. Okay, so if my dl by d theta is constant, it is not changing, my deflecting torque is simply proportional to I square. So if it is proportional to I square, then we can say that now there will not be any problem of averaging. If I compute the average of theta, what is the average value over a cycle of theta, it will not be 0, it will be proportional to IRMS. Okay, you can compute, it will be proportional to IRMS. So basically in moving iron instruments we can measure both AC and DC. Of course we can measure DC, no problems, but the scale is not proper. As we said, right, scale can be of two types. One will be linear, one will be non-linear. So in a moving iron instrument, the scale is non-linear. Why is it non-linear? Because if we see that, let's say when my current is 0.1, so 0.1 square is 0.01, current is 0.123, 0.123 square is 0.0156, right? So these are very close to each other, right? Because we are squaring the current, our scale initially for values less than 1, values are very close to each other, right? Because we are squaring it, they are becoming more and more closer. So the scale is getting cramped for current less than 1 ampere, and for current greater than 1 ampere the scale will be spacious. So this range is the one that is the ideal range where the scale will be somewhat linear. So the scale is not linear in moving iron instrument, so there needs to have proper calibration for this. So that is the disadvantage. Although you can measure DC, but it is always preferred that you use PMMC type instruments to measure DC quantities, and you use MI moving iron type instruments to measure AC quantities. Okay, that's it. Again, here also we can extend the range. So in moving iron instruments, all you have to do is you have to consider the inductance as well, and then you will solve using the impedance formula. Okay, so don't worry about all this. What will happen, again the same concept. Some current, it can take maximum of 10 amperes of current. So, and circuit has 20 amperes of current. So I will connect a impedance in parallel such that in shunt, such that the remaining 10 amperes can flow through the shunt impedance. So all these formulas that you are seeing, we are doing nothing but the impedance formulas. We are doing some ratio, we are doing some KVL, KCL, and we are solving it. So don't worry about all this formula. Okay, just one thing you will need to remember: if I want to make my current division extension independent of frequency, okay, they, like once you calculate the impedances, you will see that whatever current division is happening, that is dependent on the frequency as well. Okay, you will see impedance is dependent on frequency. Previously we used only DC quantities, so there was only resistance, now there is frequency as well. So if the frequency changes, this division also will change. We don't like that, right? So if you want it to be independent of frequency, your time constant of the shunt circuit impedance and the time constant of the meter circuit, both of them must be same. Okay, so this is LSH upon RSH and LM upon RM. Both these time constants must be same, okay, to make the frequency independent, right? So yeah, that's how you can extend the range for a for current, and again for voltage as well you can extend the range with connecting a impedance in series. So in this case, again, one thing you will have to remember, that due to this inductance in the meter, right, there will be some problems. Okay, to compensate that, we connect a capacitor in parallel with the series resistance, right, to compensate the effect of inductance, because it will have a phase difference, right, to totally cancel this out. So there is this formula that has been found out, that of course we will not derive it, but you will have to, for instrumentation students, I will say you will have to remember this formula, that your capacitance value for compensating the frequency error due to the inductance, right, basically to totally eliminate the effect of the inductance, the capacitance value must be 0.41 Lm by RAC. Okay, whatever will be the series resistance formula, this is the time 0.4 into the time constant, right. Lm is a inductance of the meter, but RAC is the resistance of the series impedance. So this thing you will have to remember. Okay, you will have to remember this one for instrumentation students. AA students, if they don't want to, they can ignore this part, but it's good to remember, right? Now we will come to dynamometer. In dynamometer, my deflecting torque is basically proportional to I1 I2 dm by d theta. Okay, in this case we use the concept of mutual inductance. So your deflecting torque is I1 I2 d theta. So your I1 current, in case of AC, I will provide the I1 current as Im1 sin omega t, and I2 current as Im2 sin omega t. So ultimately, if you compare the average deflecting torque, it will be proportional to Im1 Im2 sin phi. So not sin phi, sorry, cos phi. Okay, and of course dm by d theta is there, the mutual inductance between the two coils. So here there will be two coils. Previously here I had only one coil. Now there will be two coils and they will be interacting with each other. If I assume my dm by d theta to be constant, basically my deflecting torque will be proportional to the current in the first coil, current in the second coil, and the angular difference between the two coils. So essentially, right, if your current in the coil 1 is proportional to the voltage, current in the coil 2 is proportional to the current of the load, and the phase difference between the voltage and current, that is cos phi. So actually your deflecting torque is actually proportional to the power. So that's why dynamometer type instruments are used to measure power. That's all. Okay, there are two connections, so there are two coils, right? One is the current coil, one is the potential coil. Now I hope you know why there are two coils. So one coil through which the current is proportional, another coil through which the voltage is proportional. So this RPC, the resistance value will be very high, so that I told you, right, how to measure the voltage. So this will measure the voltage, this will measure the current, and the phase difference between the voltage and current will give you the power. Now there are two kinds of connections. So this is called as main side connections, where the potential coil terminal, right, the common point between the potential and the current coil are connected to the main side. So hence it is called as main side. And if the common point between the current coil and the potential coil is connected to the load side, it is called as load side connected. Okay, now there will be errors. There will be errors in this case, right? Why there will be errors? Because certainly your voltage will not be totally proportional, right? In this case, you see your voltage is not directly connected across the load, it is connected here. So there will be some drop in the current coil, correct? There will be some drop in the current coil. So to reduce all those errors, right, we have few formulas that you must remember. So in the first case, right, main side connection, we know there is a error in the current coil. Okay, error in the power in the current coil, sorry. So basically due to the current coil we are facing some error, because the voltage that we are measuring, it is not the voltage across the load, it is the voltage across the load plus the voltage drop across the current coil. So what we do, if I have a true power, right, then I add the losses that we saw in the current coil, and that will be my measured power, that will be your measured value. Okay, so basically your measured value in the main side connection will be the true value, that is the power across the load, plus the IC square, where IC is the current across the current coil, into RC, where RC is the resistance of the current coil. So the error in the first case, in the main side connection, will be IC square into RC, where IC is the current across the current coil, which is same as the current across the load. Hence, we can change this formula to IL square RC. This is very, very important. This will be asked. Okay. So the error in the main side connection, how will you remember it? Very simple. So if I observe that the current across the current coil and the current across the load is same. What is the problem? The voltage across the potential coil is different, right? It includes the drop across the current coil. Certainly, then I will have to include the losses observed in the current coil. Hence, simply your error would be IL square into RC. Okay. Similarly, in the load side connection, now the potential coil is measuring the voltage correctly, but the current coil is not measuring the current properly. Current is getting divided. Some current is going into the potential coil, some current is going into the IL, right? So now your error will be what? What is the voltage across the RPC? V. So it is V square upon RPC, right? V square upon RPC, that's all. VL square upon RPC. So how to remember? Again, the error will be of course due to the potential coil, because the potential coil is connected across it. Some current is flowing it, right? Some current is flowing through it. So what is the voltage across the potential coil? It is VP, right? That is VL basically, because it is directly connected across the load. So if I know the voltage, if I know the resistors, I certainly know what is the loss. The loss is Vp square upon Rp. So hence this is the error, right? And of course, you can again calculate the percentage error, that will be error upon the actual true value, P load. Okay. So these are the things that you must remember. Now again, another formula that you must remember. Okay. This is the formula that you must remember. You will have to remember. Unfortunately, there is no escape from this. So there is an error due to what? Due to the inductance present in the potential coil. Okay. What is that error? Where is that angle calculated? That angle is not shown here, right? Okay. So basically there will be a phase angle error due to the inductance connected in the due to the inductance of the potential coil, which will be of very high value. Due to that, the phase shift will not be properly measured. Okay. So this is called as the percentage error, that is the true value upon the measured value. Okay. That is equals to 1 by tan phi plus tan beta. So your measured value will be equals to what? Your measured value will be true value plus okay, this true value upon measured value, this, yeah, true value plus true value into tan phi tan beta. Tan phi, I hope you know, phi is the power factor angle of the load, and beta is the angle of this circuit, power factor angle of this particular circuit, that is the beta. Okay. That, what is tan beta? Tan beta would be XPC upon RPC, okay, of this series circuit. So tan beta is equals to XPC upon RPC. Tan beta will be equals to XPC upon RPC. Okay, that is what my tan beta is equals to, right? So I hope you got the point. So so this thing you will have to remember. True value upon measured value will be equals to 1 divided by 1 plus tan phi tan beta. This is the error due to the potential coil inductance, also called as phase error. Okay, this you will have to remember. So from this you can derive the percentage error. All these things you can do, but this thing you will have to remember. 1 divided by 1 plus tan phi tan beta. What is tan beta? That also I have explained. Okay, cool. So yeah, these are the few things that you need to remember. Now let's come to three-phase power measurement. In three-phase power measurement, all you need to remember is basically, sometimes you might need to remember the circuit. How is the circuit connected? So the potential coils, they will have a common point here. Okay, the potential coil here, they will have a common point. They will have a common point, and the okay, current coils will be connected oppositely. Okay, so basically what is 2 wattmeter method? 2 wattmeter method is a way to compute the power, compute the 3-phase power of any kind of load. Like even if the load is unbalanced, then also we can measure the 3-phase power with this particular scenario, okay, with this connection. And so we can measure 3-phase power with 2 wattmeters. That is the speciality, and this is the connection diagram. So you can remember the connection diagram, that you know the current coils will be connected to 2 phases, and the potential coil, right, all of them will be shorted, right. The potential coil will be connected between these 2 phases, and another potential coil will be connected between the other 2 phases, okay. So not the other 2, sorry, between these and this phase, and then these and this phase. So basically ultimate point is your measured power formula will come out to be this. Your measured active power formula will be this you will have to remember, okay. Your active power, active 3-phase power, your active 3-phase power formula will be coming out to be this. So this is the measured power by wattmeter W1, and this is the measured power by wattmeter W2. This is derived from the phasor diagram and all, but of course we don't have to know that. Ultimately you will have to remember this equation, very important. So wattmeter W1 will read this value, and wattmeter W2 will read this value. So one wattmeter will read 30 minus 5, other wattmeter will read 30 plus 5, and obviously VL IL will be multiplied. And if you see, this is nothing but the formula of 3-phase power, okay. So if I add the powers of the 2 wattmeter, I am getting 3-phase power. Cool. Now reactive power. Reactive power is basically if I subtract the wattmeter readings of the 2 wattmeters, then I will get my reactive power. Not exactly, I will have to multiply √3 with it, right. So this will be VLIL sin phi. So previously if I add the 2 powers, I was getting √3 VLIL cos phi, right. That is exactly equals to my 3-phase power. But if I subtract the 2 wattmeter readings, I will get VLIL sin phi. Now this is not exactly equals to my reactive power. My reactive power is √3 into VLIL sin phi, okay. My reactive power is actually equals to √3 into VLIL sin phi, right. So so what you have to do, after subtracting the 2 wattmeters, you will have to multiply √3. After subtracting the 2 wattmeters, you will have to multiply √3 with it, and you will get your reactive power, okay. So from this you can obviously compute your power factor angle as well, tan phi. That will be the reactive power ratio upon the active power ratio, that is √3 into W1 minus W2 divided by W1 plus W2. So what do you need to remember? You need to remember this part, you need to remember this part, okay. If you know the reactive and active power, certainly you can derive the power factor angle expression with these two, okay. So these are the important parts that you must remember. So it happens same for delta connected loads as well. The formulas will be same, nothing will be changed, okay. So please remember it. What is W1? W1 is VLIL cos 30 minus 5, W2 is VLIL cos 30 plus 5. This you have to remember anyhow, very important, right. Here this table just states that at various power factors what will be the wattmeter readings of W1 and W2, what will be the 3-phase power, okay. This was the summary for 2 wattmeter method. Now there is energy meter. So in energy meter, what we do, it is an integrating type instruments, because we are measuring energy. Energy is nothing but the integration of power, right. So this actually measures power over time. So there are certain things, many things that are there. So we don't have to worry about most of these things. Ultimately what we have to worry about is this equation, okay. So your net torque in an energy meter will be equals to the voltage across the potential coil, the current across the potential coil, into the sine of the angle between delta and phi, okay. Now what is delta? So delta is the angle at the potential coil, okay, and phi is the angle across the current coil. Now in most cases the potential coil will have an angle of 90, because your potential coil mostly will be purely inductive, okay, mostly it will be purely inductive. But for certain cases this delta value is not exactly equals to 90, it is somewhat less than 90. Then your net torque is not proportional to VPC IPC cos phi, it deviates. So we receive an error there, right. And like that you can derive the expression for error if your potential coil angle, right, is not exactly equals to 90. So in energy meter, this is the part that you must remember. Okay, you must remember this part. So there are like the explanations given of the working of the potential coil. We don't need to go into it. Okay, now this is the most important part that you must remember. Okay, so it is called as meter constant. Meter constant of an energy meter is simply equals to the number of revolutions in time t upon the energy consumed by the load in the same time period t. Okay, so it is simply revolutions upon kilowatt hour. This is a constant value. This will not change. Okay, so this is the relation between the rotation. So we have a disk, relation between the rotation, number of rotations of the disk upon the total amount of power consumed. That is known as meter constant. Very important relation that you will have to remember. This you will have to remember. Now, what is the percentage error? As I told you, if you remember this expression, you know we are supposed to get VPC IPC cos phi, but we are getting VPC ICC sin delta minus phi, where delta is not equal to 90, right? So the error is simply measured value minus the true value upon the true value. That is what doing. Measured value minus the true value upon the true value. VPC IPC is common, so it is getting cancelled. So ultimately your percentage error would be sine of delta minus phi minus cos phi divided by cos phi into 100%. So that is the percentage error. So these are the few things that you must remember. Now there is another concept of phantom loading, where what we do is, so here what happens, a single source is energizing both the potential coil and the current coil, right? The same source. But in phantom loading, we have separate sources. The potential coil is excited with 230 volts by a separate source. The current coil is excited by another source, okay, that is producing the current. So with phantom loading, we can actually see how my instrument is behaving when connected to higher loads. So what is the advantage? Advantage is we are not actually connecting a very high load. That is not happening because the sources are independent. We don't have to waste that much amount of power. So the voltage across it might be very low. Current although is very high, voltage will be low, very low. So the overall power consumed will be low. Here the voltage is very high, current might be low. So overall power consumed with phantom loading, that's why the name phantom, because we are not actually connecting that much high load. We are in a phantom stage, that we are actually not connecting the high load, we are connecting a low load, but still we are able to simulate our instrument at higher loads. Okay, these are the purposes. You can go through this. So in phantom load, what you will have to consider is like what are the different losses. Okay, so that you can easily calculate. What will be the losses in phantom loading, that you can easily calculate. You don't have to worry about it. Simply, let's say if some 50 amperes of current is flowing through the load, right? So what will be the loss across the 0.5 ohm, or what will be the you will have to calculate the current. So it's very simple. If you know what is the source connected to the current coil and you know what is the load resistance, you can calculate the current, right? Similarly here as well, if you know the resistance here, you can calculate the current. So simple, use KVL KCL, that's it. You don't have to worry about anything else. Simply use KVL KCL. Okay, now there are few more instruments like electrostatic voltmeter. Just remember how does their torque vary. So for electrostatic voltmeter, the torque varies with voltage square into dc upon d theta. Okay, remember. So for a moving iron instrument, their torque varies current square, current through the coil, I square into dl upon d theta. For dynamometer type instrument, it is I1 into I2 into dm upon d theta. That is written over here. Here, if I1 and I2 are same, it will be I square. And for yeah, I think that's it. And for electrostatic voltmeter, it is V square into dc upon d theta, where c is the capacitance of the electrostatic voltmeter. Okay, these things you have to remember. If they ask some questions, they might ask questions from this. Okay, so make sure you remember this box. And for like some instruments like take use of the heating effect, where it uses the power consumed due to heat, right? That is I square RT. So simply there also in heating type instruments, the torque is proportional to square of the current. Okay, again you can extend the range in an electrostatic voltmeter. We can extend the range by connecting capacitors. Okay, they will follow the same voltage division. You can see whatever division they follow in capacitive circuit. So we can connect this capacitance in series to increase the voltmeter range. So I hope you know how the voltage division happens when the capacitor is connected in series. You see they will have opposite relation. Okay, simple KVL, that's it, simple KVL, nothing else. Okay, so now till now we have discussed about spring control. In spring control the torque is like this. Now there is another type of control, that is gravity control. In gravity control, it basically uses gravity to control the pointer. Okay, so let's say if the pointer is somewhere here, so now if the pointer has a mass m, right, so it will have two forces, one will be connecting it to the downward, another one will be taking it to the left, right. So this downward force is nothing but the gravitational force, correct. So what is the, like, you guys, I hope you know physics. So if this is theta, this will be what, this will be cos theta, right. So weight here is mg into cos theta. So the force applied by the gravitational force, so this is theta. If this is theta, this is also theta. So what is happening, the pointer is moving in this direction, correct. So gravitational force will try to take it in this direction. So actually the gravity is happening, gravitational force is here, right, that is mg. Okay, so mg is the gravitational force, correct, and this particular thing is theta. So this is 90 minus theta. So what is the opposing gravitational force? So gravitational force will have two components, one will be along this component, another one will be along the right hand side, right, that will oppose the deflecting torque. So this value will be equals to what, mg sin theta. Basic physics, basic physics. So the torque that is opposing the deflecting torque, that is mg sin theta, that will be acting as my controlling torque. Okay, so in gravity control the torque is, controlling torque is equals to mg sin theta. It is not directly proportional to your angle theta, it is proportional to the sine of the angle. The controlling torque is proportional to the sine of the angle. Okay, sine of the deflecting angle. Now Megger, for a Megger the deflection is inversely proportional to the resistance. Again you will have to remember this thing. So for a Megger, if the theta is 0, if the pointer is pointing towards 0 degree, that basically means that you have infinite resistance connected across the Megger terminals. If the pointer is pointing towards full scale deflection, that means your resistance connected to the Megger terminals is 0. Okay, and then we have power factor meter. I don't think much, I don't have much to say here. Power factor also is similar to the working principle of the dynamometer instruments, where my currents are basically same. Okay, we use the principle of dynamometer instruments where currents are same, so we only measure the power factor with the deflection. So with that we are done with the analog instruments. Now we will solve few questions. So let's begin with the first question. 2 wattmeter method is used for a measurement of power in a balanced 3-phase load supplied from a balanced 3-phase system. Okay, if one of the wattmeter reads half of the other, both positive, then the power factor of the load is what? So W1 is equals to 1 by 2 of W2. One of the wattmeter is reading half of the other one, right? So what is the power factor? So if W1 is 1 by 2 of W2, what is the active power? It is W1 plus W2 for a 3-phase load. So it will be 3 by 2 W2. What about the reactive power? It is root 3 into W1 minus W2. So this will be equal to root 3. W1 is W. Okay. Yeah, let me assume, because both are positive, power factor. Okay, if both are positive, right? So let me assume this. Otherwise, you will get negative angle, which is not correct. Okay, so this will be W1 by 2, and your W2 is also W1 by 2, right? So this will be root 3 by 2 into W1. Now we know your ratio tan phi of the load will be Q upon P, that is equals to root 3 by 2 W1 divided by 3 by 2 of W1. So this will be equals to uh, root 3. One by root 3 basically, right? So your tan phi is 1 by root 3. So your phi is 60 degree, right? Phi is 60, and what is cos? So sorry, phi is 30, right? So if your phi is 30, so what is power factor? Power factor is cos phi. So cos 30 is root 3 by 2. 0.866. So this will be your answer for the question. Pretty straightforward question. Let's move on to the next one. Right, this is the next question. A 0 to 1 ampere moving iron ammeter has an internal resistance of 50 milli ohm. Okay, so the ammeter has an internal resistance of 50 milli ohm. Okay, and inductance of 0.1. So the coil has an inductance of 0.1 millihenry. A shunt coil is connected to extend the range to 0 to 10 amperes. Okay, so a shunt coil is connected to extend the range to 0 to 10 ampere. The time constant in milliseconds and the resistance of the shunt coil respectively are. So basically, I've told you, right, if I want to keep it independent of frequency, then the time constant of this circuit and the time constant of this circuit must be same. There is a derivation, okay, but you can directly use the result. So what is the time constant of my actual current coil? That is equals to L by R, that is 0.1 by 50, right, that is 1 by 500. Okay, seconds, they have asked in milliseconds, right? In milliseconds I can multiply by 1000, so this will be 2 milliseconds. So time constant would be 2 milliseconds, that I can see option A and B. So option C and D are gone. Now what about the resistance? So now we will use this property. So if I want to extend my maximum range from 1 ampere to 10 ampere, so 1 ampere current will flow from here, right, and other remaining, so 10 ampere current is coming here, remaining 9 amperes will flow from the shunt coil, right? So this is RSH. Now if that current division is independent of frequency, I can simply equate the voltages between the two resistors, okay, because it is independent of frequency, so I can neglect the inductance. So this will be 50 millihenry into 1 should be equals to whatever is the voltage across the top resistor, same voltage should be across this bottom resistor as well, because they are in parallel. So this will be RSH into 9. So your RSH is equals to, remember this is in milli, right? This is in milli, and they have asked me in millihenry only, sorry, milli ohms only. So this will be 50 by 9 basically, 50 by 9. So 100 by 9 is 11.1, 50 by 9 would be 5.55, something like that. 5.55 milliohm, that is present in option A. So option A would be your correct answer for this question. I told you, right? We will use basic KVL KCL, that's it. We will not use any formula, nothing. We will use basic KVL KCL. Okay, let's solve the next question. A moving coil instrument having a resistance of 10 ohm gives a full scale deflection when the current is 10 milliamperes. Okay, so moving coil instrument have a resistance of 10 ohm. Okay, so moving coil instrument has a resistance of 10 ohm and gives a full scale deflection when the current across that ammeter is 10 ampere, 10 milliampere. What should be the series resistance so that the voltage it can measure, it can be used as a voltmeter for measuring potential difference up to 10 volt, so 100 volts, right? So what is the amount of series resistance that we will connect, right? RAC. So currently what is the voltage that my instrument can measure? If a full scale current of 10 milliamperes is flowing, it can measure a voltage of 100 millivolts, right? So now, but I want to measure how much volts? 100 volts, right? So the coil can provide a drop of 100 millivolts, that is the maximum allowable drop that the coil can provide. So the additional approximately 100 volts only has to be provided by the series resistance, that is equals to 99.9 volt has to be provided by the series resistor. Okay, right. So basically the drop across the series resistor has to be 99.99 volts, right? Because 100 millivolts will be dropped across this resistor and the remaining will be dropped across the series resistor. Okay, so it will be 100 milliampere into RAC, that is equals to 99, right? So 99 divided by 10 raised to the power of -3. So this will be basically, they have asked me in ohms, right? So this will be 99. So okay, 10 to the power -2, right? 10 to the power 2 actually, 99. So 9990. Okay, this is the amount of resistance that you need to connect in series. So all we are doing is we are using KVL KCL. I am not doing anything, right? I'm just simply, what is the maximum voltage drop across the measuring instrument? 100 millivolt. So I want to use this instrument as a voltmeter, right? So it needs to measure 100 volts. Out of that, the maximum like drop that this coil can take is 100 millivolts. So remaining drop must be taken by the series resistance. So we know the maximum current that will flow through this resistor. So we can simply solve it. No formula, nothing. Let's solve the next question. Assuming that the op-amp used in the circuit shown is ideal, reading of the 1 Hz bandwidth PMMC type voltmeter in volts is. Okay, so don't worry about this bandwidth wala thing. They are simply asking you what is the reading of the PMMC type voltmeter. Okay, it has, if it has a bandwidth of 1 Hz, I don't care, but the thing is that you are providing a sinusoidal input. Okay, if you are providing a sinusoidal input, what will happen to the output? We'll have to see if there is a rectifier connected or not, right? Because output I see it is through diodes. So although the input is AC, the output may not be AC. It can be pulsating DC, right? And the pulsating DC can have an average value, right? So although the AC has an average value of 0, but this pulsating DC may not have the average value 0, right? So let us first see the behavior of the output voltage. Okay, so if we see that there is if I assume that this diode is on, right? Let's for a second, let's assume that this diode is on. If this diode is on, that means that virtual short will be applicable, because either this will be negative feedback due to this diode, or this diode will be negative feedback, right? Diodes are ideal. If diodes are ideal, then either there will be a closed path here or there will be a closed path here. One of the diodes will be on. Okay, let's assume that let's say this diode is on. Okay, or if you even don't want to assume that this diode is on, right? So let's say there is no virtual ground concept. Okay, then let's say this voltage is maximum. When this voltage is maximum, there is no current that is flowing into it. So both of the diodes are on. Voltmeter has very high impedance, so this whole thing also has 0 amperes of current. So this point I have plus voltage and this point I have minus voltage. So as op-amp is working in negative feedback, right? Sorry, as it is an open loop, right? Op-amp is working in open loop because both the diodes are open. So this will be plus, this will be minus. So ultimately I will get minus Vsat. Okay, if I get minus Vsat, now this is higher potential, this is negative potential, right? So certainly this diode will be off, but certainly this diode will be on, because sorry, hold on a second. So sorry, certainly this diode will be on. Why? Because its N side has lower potential connected and its P side has higher potential connected. So suddenly it will turn this diode on. So when this potential is high, right, then diode D1 is on. So basically the thing is, when my input voltage Vi is greater than 0, D1 is on. Okay. Now when my Vi is negative, so let's analyze the same thing for negative, right? So if it is negative, this point is negative, right? Again, it is in, let's assume that both of them are off. This voltmeter has infinite impedance. So if it is negative, this will provide, this is 0 volt, right? So open loop configuration. So this will be plus Vsat. Now if this is plus Vsat, this will be turned on. Okay, this point, this diode will be turned on, and this diode of course will be turned off, because this has negative potential P side and N side has higher potential. So diode D2 will turn on, D2 will be on. Okay, so basically this is the conclusion, right? When my input voltage is positive, D1 will be on, D2 will be off, and when my input voltage is negative, D1 will be on and D2 will be off. Okay, so yeah, that's the case over here, right? So yeah, now let's analyze the circuit for positive half cycle, basically when Vi is greater than 0. So when Vi is greater than 0, I have already told you that this is my input, right? I have my Vi, I have this resistance, this 20k minus plus, this is grounded. So this will be on. Okay, and yeah, and sorry here, okay, this diode will be on, right? So the connection will be here, right? And this diode will be off. So if this diode is off and this voltmeter, ideal voltmeter has infinite impedance, so technically here there is zero current, right? And voltmeter also will not take any current, so technically this current also will be zero. So when your Vi is greater than 0, your output voltage, right, the output voltage is simply 0. It is 0, right? Yeah, it is 0, because this point is connected. Your voltmeter reading will be 0 because there will be no current flowing through it. Okay, okay. Now when it is negative, then what will happen? We will see. When it is negative, in the negative half cycle, right, circuit is similar, but the difference would be now the voltmeter will be in action. So now what will happen? This diode will be in action, right? This diode will be on, this diode will be off. So this connection will be there intact. So now the voltmeter, right, will read the potential at this point. So that is nothing but the output of the op amp. Okay, previously the output of the op amp was not connected to the voltmeter, hence no current was flowing, hence it was 0 volts, right? Now the output of the op amp is directly connected to the voltmeter. So this will be the connection. This is my voltmeter, correct? And this is simply 10k. So I think you are very expert in solving this analog circuits. This will be equals to, so VO. So virtual ground concept will be valid here because proper negative feedback is there. So 0 minus VO divided by 10 plus 0 minus Vi divided by 20 equal to 0. So your VO is equals to minus 1 by 2 of Vi. Okay, VO is equals to minus 1 by 2 of Vi. So your voltage is negative of input, and what is my input right now? My input right now, if you see, this is the sinusoid. Okay, this is the sinusoid, and whose peak value, if you see, is 2 pi, and whose frequency is very high, so we don't have to worry about the frequency, right? So this would be 2 pi. As the frequency is very high, assuming this will be like voltmeter, will assume this to be almost DC, but okay, let's not consider that. Yeah, so it is 2 pi, right? It is 2 pi and minus 2 pi. Okay, and we are analyzing in this region. So my voltage is negative of half. So what is the output voltage? Output voltage would be equals to, it is 0 initially from 0 to pi. Okay, just talking about the angle, just talking about one cycle, right? Let's say 0 to t by 2, and again in the next half cycle it is half, negative half of voltage, right, of the input. So negative half of input. So this peak value would be pi, not 2 pi. Okay, negative, that's why I have flipped it around the time axis. Okay, so what is the average value of this lobe? Do you remember what is the average value? You can calculate, right? You can use the formula, everything you can do. It is simply 2 Vm upon pi. Yeah, that's it. 2 Vm upon pi, right? 2 Vm upon pi, that is the average value. Sorry, not, this is not the average value. It is a Vm upon the pulse width, or Vm upon pi. So average value of a half wave, like rectified sine wave, is Vm upon pi. You can use formulas, you can derive this, all those are there, right? So Vm is pi, so pi upon pi is 1, and so your average value is 1, and your PMMC instrument always measures the average value, right? So your answer would be 1. Very beautiful question. Answer would be 1 volts. This was a very, very beautiful question. Okay, so 1 volt will be your answer for the question. Let's solve this question. The real power drawn by a balanced load connected to a 400 volt 50 hertz balanced symmetrical 3-phase 3-wire system. Okay, W1 is connected to R phase, W2 is connected to B line. The current measured, the line current measured is 1 by root 3. If the wattmeter W1 reads 0, what is the reading of wattmeter W2? So they have already told me what is the line current. If I know the line current, I can certainly tell what is the power consumed by the load, because it is a balanced 3-phase load. So power consumed by the load would be equals to root 3 VL IL cos of phi. Okay, root 3 VL IL cos of phi. Now you know that this will be equals to root 3 into the voltage 400 into the line current, that is 1 by root 3 into cos of phi. Now you just need the information regarding cos phi, then you will be able to comment what is the total power, and that will help you out. Okay, but how can I calculate the cos phi? So one thing you know, that your W, right, is equals to W1 plus W2, that is equals to VL IL cos 30 minus phi plus VL IL cos 30 plus phi. Okay, now they are telling me one of the wattmeter here reads 0. When does the wattmeter read 0? When this angle, overall angle, right, cos of 90 will be 0, right, when this overall angle is 90. So either this angle is 90 or this angle is 90. Which one will you choose? Here comes a very important point. Please listen to me very carefully, that my power factor angle, right, will always lie between plus 90 to minus 90. Power factor angle is will always lie between plus 90 to minus 90, right? That is my power factor angle. Okay, so if I make this to be 0, right, 30 minus 5 equals, so not 0, sorry, 30 minus 5 will be equals to 90. So phi comes out to be 120, which is not possible, because if you have a passive load connected, your angle will vary from minus 90 to plus 90, right? 90 being the maximum highest inductive load and minus 90 being the highest capacitive load. So this going to 90 or this being 0 is not possible. So certainly this term will be 0. So certainly if this term is 0, that means 30 plus phi is 90. So from here I get the value of phi, that will be 60. So I got the power factor angle 60. Now it's very simple. What is the overall power? Overall power is 400 cos 60, that is 400 into half, that is 200, right? So 200 watt is your overall power. Okay, 200 watt is your overall power. Now if 200 watt is your overall power, they are asking me what is the power rated by wattmeter W2. So we know the overall power would be equal to W1 plus W2, and W1 is, so basically they have interchanged their names, right? Don't get confused, W1 and W2. Okay, in my case this is my W1 and this is my W2, but don't worry, ultimately they are simply asking me if one of the wattmeter reads 0, that is if this one reads 0, then what is the reading of the other wattmeter, right? That is what they're asking me. So actually this wattmeter reads 0, right? So my overall power will be equals to W1 only, that is equals to overall power is what, 200. So W1 also will be 200, right? So W1, one of the wattmeter will read all of the power, other will read 0. Okay, so basically they ask me what is the reading by the other wattmeter, that is 200 watts. Don't get confused by W1 W2, right? Just the names that I have put, because they have done according to their phase RB, but we are not going into the connections. That will take us huge amount of time. We are ignoring the connections. Yes, you can solve it properly. If you solve it properly and derive properly, your W1 will come out to be this and W2 will come out to be this, but we are not getting into that. You are just understanding a trick so that I can solve my question in a faster manner. Let's solve the next question. This is the next question. A 300 volt 5 ampere low power factor. So LPF basically means low power factor. Wattmeter has a full scale reading of 300 watts. Okay. The wattmeter can be used for loads by supplied by 300 volts AC means, with a maximum power factor of what? Okay. What is the maximum power factor that the wattmeter can read? It is very simple, right? So the rated P rated would be equals to V rated. It's a single phase load, nothing is mentioned. We will assume it to be single phase load. V rated into I rated into cos phi rated, right? So this will be equals to V rated, that is 300, into I rated, that is 5, into cos phi rated, that is what we have to calculate, right? Rated power factor, maximum power factor. Okay, and P rated is 300 watts. So PF rated, the maximum power factor the wattmeter can read, is equals to 0.2, right? So of course if the power factor, so that's why it is called low power factor, right? Low power factor has some like special construction features that we use to measure the power in low power factor, because in low power factor the phase angle error that we discussed, right, that is 1 plus tan phi into tan beta, that is very huge. So in that case we have to use low power factor wattmeter to reduce that phase angle error or the compensating error, right, due to the inductance in the potential coil. So this is the maximum amount of power factor, right? If let's say your power factor is 0.1, then your overall power, right, will be what, 300 into 5, that is 150 watts, into 0.1 is 150 watts, which is within my limits, right? So if my power factor is more than 0.2, then we are going out of our limits. That is a problem, right? So 0.2 is our correct answer for this question. Let's move on to the next one. So this is the next question, where the power in a 400 volt RMS line to line 3 phase 3 wire RYB sequence system is measured using 2 wattmeters. As you can see, 2 wattmeters. The R line current is 5 ampere 60 degrees. The wattmeter W1 in R line will read what? So my R phase is the reference phase, right? So what will be the reading of the wattmeter W1? So you see the reading of that wattmeter W1 would be the voltage in the potential coil across the wattmeter W1, that is VRY. Is it? No, it is not VRY. It is VRB, right? So because the potential coil is connected across R and B phase, correct? If you see the dot here, so it is VRB into IRB. IRB is already given to me, that is 5 angle 60, right? 5 angle 60 degree into cos of angle between the voltage minus the angle of the current. So W1 is this. Okay. So what is the voltage angle? So this angle of the current is nothing but the angle with respect to the reference. What is VRB? So my phase sequence is RYB. So it will be VRB would be VR minus VB, right? So it is RYB, right? So R is here, then I will have B. Sorry, it is, then I will have Y, then I will have B, correct? So VR is nothing but V angle 0 degree minus V angle. What is VB? VB is V angle from the R phase, it leads. So it will be V angle plus 120. Okay. So what is the difference between these two? So three phase basics I have already taught previously in one of the core videos, right? I am not explaining over here. So it is VR minus VB. So minus VB would be coming where? It will be coming here, right? So what is the angle difference between these two? It is 60 degrees. This is my minus VB, right? So whenever there is 60 degrees difference and I have magnitudes of the vectors to be same, then the addition, so minus VB plus VR, minus VB plus VR would be equals to, sorry, minus VB plus VR shall be equals to this, right? So the resultant will be bisector of these two, and its magnitude would be root 3 times V, and its angle would be lagging from the previous one, so it will be bisector, so it will be minus 30. Okay, so the angle of VRB, right, VRB would be root 3 into V. Now V is given to me, okay, root 3 into V, that is nothing but the line voltage, right? Root 3 into V is nothing but the line voltage, where V is my phase voltage, and line voltage is 400 volt RMS line to line, so it is simply 400. Okay, magnitude I already knew. The information that I was required was the phase, so the phase is minus 30. Okay, phase is minus 30, so phase is minus 30, so the phase of voltage is minus 30, the phase of current is 60, right? So what is the phase difference? So current is voltage is 400 into 5 into cos of the phase difference between the voltage and the current. So voltage has a phase of minus 30 and current has a phase of, so phase difference would be minus 30 minus 60, theta V minus theta I. So theta V is minus 30 minus theta I, that is minus 60. So this will be cos of 90, that is 0. So the wattmeter actually will read 0. Okay, wattmeter will actually read 0 degrees. Pretty interesting, right? So this you will not be able to use formulas. This you will have to solve with basics. So you will need good knowledge of phasors. Okay, let's solve the next question. This one. In a balanced three-phase circuit, C0 is given and the line-to-line RMS voltage is given at 50 Hz. Correct. The reading of the wattmeter would be what? Okay. What will be the reading of the wattmeter W1? Interesting. Okay. The balanced three-phase circuit is shown. C0 is this. Okay. And this is the voltage across the load, right? Okay. They're asking me what is the reading of the wattmeter W1. So reading of the wattmeter W1 would be IR VRY into cos of angle between voltage and current. Correct. So how do I solve it? So what is my VRY? So VRY, I know it is the line voltage, but what is the angle? So if I have VR that has an angle of 0 degree, right? And it follows a phase sequence of RYB, nothing is mentioned, we will assume it follows a phase sequence of RYB. So VRY, VR minus VY, right? VY is like VR is V angle 0 degree, the phase voltage minus VY. VY would be V angle minus 120. Okay. And so if I again use the phasors, this is my VR, this is my VY, and this is my VB. I'm just doing this approximately, I think you will be able to figure it out. So your V R minus Vy, right, would be, this will be root 3 into V angle plus 30. Okay, because the negative will, the resultant will lie somewhere here, right, because I will do Vr plus minus Vy. Okay, so to lie somewhere here. So this is my Vry, so it will be plus 30. So basically it will be VL line voltage into IL line current into the cos theta V is 30 degrees, and theta I is basically what? What is theta I? Theta I, if the voltage, let's say if the phase voltage, let's say across this R phase is V angle 0, right? What is the current? Because remember, it is, what is the reactance? It is 1 by j omega c naught, right? So the current would be V upon impedance or the reactance, that is j omega c naught into V angle 0. So the angle of the current, right, leads the voltage by 90. So this will be actually theta I would be plus 90. Okay. So your answer would be VL into IL into cos of minus 60, that is half. So this will be 1 by 2. Okay. So what is VL? VL I already know. What is IL? IL would be simply V, that is VL by root 3. VL by root 3 upon the reactance, right? Not the reactance, into j omega c, or if I want to just calculate the magnitude, into omega into c naught, right? So VL is simply 440 volt, right? VL is simply 440 volt divided by root 3 into 2 pi f, that is 50, into c naught. C naught is 8.2 microfarad. So this will be equals to 440 divided by root 3 into 2 into pi into 50 into 8.2 into 10, hold on a second, just divided by 8.2 into, hold on, I am doing something wrong, so let me redo the calculation. Into 8.2, no, this was correct only, into 10 raised to power minus 6, right, that is 0.654 amperes, right? So your line current is 0.654 amperes. So yeah, so this will be VL. VL is 440, right? VL is 440 into 0.654 divided by 2, right? That is 143.88. So the wattmeter reading would be 143.88 watts. Now you might have a doubt, sir, how is this circuit consuming some power, active power? Because you will say that, sir, like it is completely reactive load connected, right? Imaginary load. How is it consuming power? So actually this is the reading of W1. The reading of W2 would be what? Exactly the magnitude, this will be same. This will be theta V will change. Theta V will change there. It will be 30 plus 5. So 30 plus 5 is 120, right? That is minus 0.5. So your W2 reading will be exactly the same, but negative. It will be negative. If it is negative, they will cancel out. So overall power is 0, that is correct. But W1 will read certain value, W2 will read negative of that. So overall power certainly will be 0, and actually overall power is 0. Okay. So I hope that doubt is cleared. Now let's solve the next question. This is the next question, where we have basically a moving coil voltmeter has an internal resistance of 50 ohm. The scale of the meter is divided into 100 equal divisions. The scale of the meter is divided into 100 equal divisions. When a potential of 1 volt is applied to terminals of voltmeter, a deflection of 100 divisions is obtained. What? So a moving coil voltmeter has an internal resistance of 50 ohms Okay, the moving coil voltmeter has an internal resistance of 50 ohms. The scale of the meter is divided into 100 equal divisions. So I have total of 100 divisions, right? 100 divisions. When a potential of 1 volt is applied to the terminals, the deflection is 100 divisions. So basically, the full scale voltage measured is 1 volt. Okay, so each division, one division would be what? 1 by 100, because for 100 divisions I am measuring 1 volt. So one division would be 1 by 100 volts, that is 10 millivolts. However, it is desired that when a potential of 500 volts is applied to the terminals, the deflection of 100 divisions should be obtained. So what is the amount of series resistance that needs to be connected in ohms? Okay, so basically, simply what we want to do, we want to increase our range from 1 volt to 500 volts, right? So currently, what is the full scale current? I full scale, because that is the maximum current that the coil can support, that is equals to voltage, full scale voltage upon the resistance, that is 1 by 50. Now what I will do is I will connect another resistance RAC in series. So currently, what is the drop here? The drop across, full scale drop across the coil is 1 volt. So I need to measure 500 volts, so the remaining 499 volts will be coming across the series resistor. So 499 volt divided by the full scale current, that is 1 by 50, that will be equals to my series resistance value. So 499 into 50 would be your series resistance value. So let me calculate that. 499 into 50, that is equals to 24950 volts. Okay, that is the, so not volt, sorry, 24950 ohms, right? That is the series resistance value, 24950 ohms. Cool. Let's solve the next question. This is the next question. A three-phase star connected balanced load is supplied from a three-phase 400 volt balanced voltage source. Okay, with phase sequence R-YB. So if you see, the connections are not proper here. We are not doing a 2 watt meter connection. We are doing 1 watt meter connection. But with 1 watt meter as well, we can actually measure the three phase power if given that the load is balanced. If the load is balanced, I can calculate the line current, I can calculate the line voltage, and if I know the line current and line voltage, I will be able to comment on the power, because as the load is balanced, right, certainly I can measure the single phase power and I can multiply that by 3. That should be enough. Correct? I hope you got the point. So what they're telling me, that 3 phase 400 volt is the voltage source and RYB is the sequence, wattmeter reading is minus 400, that is fine, and the line current reading is 2 ampere. The power factor of the load shall be what? What shall be the power factor of the load? Okay. So what will be the wattmeter reading here? If you see, the wattmeter reading will be VYB into IR into cos of theta YB minus basically the voltage and the current, right? Okay, but do I need this? I will be able to calculate the, I know voltage, I know everything, right? I know voltage, I know current. I need to compute the power factor. What will be the power factor? Okay. Yeah, I don't know what is theta I, right? Theta I will help me compute the power factor. Theta I is nothing but phi, right? Basically, it is the current angle of the current IR, right? And if I know IR current angle, I know VR is angle 0, so that will give me the power factor. So ultimately, my target would be to calculate theta I. So what is theta V? Theta V would be basically, so I have to compute what is VYB. VYB is VY minus VB, right? So again, RYB phase sequence. So this is my Y, this is my, sorry, this is my R, this is my Y, this is my V. RYB phase sequence, right? So this is Vy, this is Vb. Okay, so if I subtract this then the resultant will be lying somewhere here, right? 30 degrees from here, that is exactly at minus 90. Okay, minus 90 from the reference phase, that is R. So your theta V, right, is 90, not 90, minus 90. Okay, make sure your theta V is minus 90. And your like magnitude of VYB is what? Magnitude of VYB is simply 400. Okay, so your wattmeter reading is 400. Your magnitude of VYB line voltage, right, is sorry minus 400. This is 400 into IR. IR current is 2 ampere, right? And this is cos of theta V, that is minus 90 minus 5. Okay, so basically your cos of minus 90 minus 5 is equals to 1 by 2. Okay, minus 1 by 2 to be precise. So we know minus 1 by 2 is basically when it is equals to 120 degrees, right? 0.5, it is equals to minus 0.5 when it is 120 degrees. If I choose this 120, then your phi comes out to be minus 210. Obviously not possible. Your power factor angle will be between minus 90 and plus 90, right? Okay, this is not possible. What is another angle? Am I doing anything incorrectly here? So your theta V must be minus 90, correct? Because this is my reference, right? VR is my reference. So minus of VB. So and this is 60 degrees. So this will be 30 degrees, correct? So hold on. So this is whole 120 degrees, right? Yeah, this is 90 only. And this is minus 90 only. RYB. This is supposed to be minus 90. This minus 90. Okay. This is plus, this is minus, right? So it is correct only. Okay. What am I doing wrong? So this is negative. So what is cos of minus 120? Yeah, cos of minus 120 also will work, right? So I can assume this to be minus 120, but yeah. So this can be minus 120 as well, right? So this will be simply equals to minus 120 degree will be equals to 90 minus 5. So your phi will be equals to 30 degrees. So your phi comes out to be 30 degrees. The power factor angle will be cos of phi, that is 0.866. So 0.866, it comes out to be plus. Okay, but here they're telling me that it is coming out to be minus. I'm somehow doing something wrong, I don't know. Okay, this is the clockwise direction, right? So VR is my reference. I don't know. So with respect to reference, this has an angle of, I don't know, whatever is the theta I. What is the angle here? This angle should be somewhere. I'm making some silly error. Okay, I don't know, but I feel this should be lagging. This should be lagging. They have given leading, I don't know, but I feel somewhere I'm making a silly error. But yeah, option C was the correct answer, but maybe you guys can let me know where I'm going wrong, but it feels like somewhere there is some discrepancy. Let's solve this question. So the full scale range of the voltmeter shown in the circuit is wattmeter is 100 watts. Okay, the range of the wattmeter is 100 watts. The turns ratio of the individual transformers are indicated. The RMS value of the AC voltage source is this. The wattmeter reading shall be equals to what? What is the wattmeter reading? Okay. So if I'm connecting a voltage source Vs like this, then what is the voltage here? It will be 1 by 2 of Vs, right? So it will be Vs by 2. Vs by 2. What will be the current here? It will be Vs by 200. Okay, and this voltage also will be Vs, right? So this will be Vs, right? Okay, so potential coil has a voltage of, this will be Vs by 2, right? Because the potential here is Vs by 2. So the potential coil has a voltage Vpc is equals to Vs by 2. What is the current across the current coil? How do I compute the current across the current coil? I'm trying to figure out here. So I know this current, right? That is Vs by 200, and that current, because you see that this is my potential coil, and potential coil has a very high impedance connected, so this will have zero amount of current, right? So if this has zero amount of current, this also will have zero amount of current, simple turns ratio. Now whatever current is flowing, that is Vs by 200, right, that same amount of current will be flowing from here. And if I follow the turns ratio, here the current will be Vs by 400 according to the currents ratio, right, amperes. This is the current that is flowing through this particular coil, right? What is the current flowing through here? Because here also Vs by 2 is flowing, so here Vs by 2 is flowing, right? Here Vs by 2 current is flowing, so here 0 ampere of current is flowing, so here also Vs by 2 current will flow. So through your current coil actually no current is flowing, so your wattmeter will simply read 0. Okay, this was a trick question. Okay, no current is flowing through the current coil, this was a trick question, your wattmeter will read 0. Okay, your IPC is 0, right? So your wattmeter will be 0. Okay, now let's solve the next question. This is the next question. So yeah, this question is pretty interesting. In the circuit in the figure shown below, SW is a switch whose position changes from 1 to 0 when VC changes from logic high to low. Okay, and vice versa. Okay, VC, when VC is high, this switch will be 1. When VC will be low, this switch will be 0. The PMMC has a bandwidth of this, and if V sense is this, right, then the, and Vref is this, the voltmeter reading would be equals to what? Okay, so this is just acting as a comparator, right? So basically in the positive half cycle, Vc will be 1. So when Vref is greater than 0, Vc will be 1, that is basically switch will be in position 1, and when Vref is less than 0, your Vc would be 0 and your switch will be in position 0. Okay, now when your switch is connected to 1, what is your V out? V out is equals to V sense. Right, and when your switch is connected to 0, right, your V out is, because I have a negative 1 amplifier, this is open circuit, right, so V out will be minus of V sense. So at first glance it feels like what is happening when your voltage is negative, when your voltage is positive it is plus V sense, when it is negative it is minus. So it seems like it is a behavior of a full wave rectifier, right, and your Vm will be according to V sense. Vm is, V sense is 2, right, so this will be 2, and you will say your answer basically average value, your VO average, right, because your PMMC reads the average value, that will be equals to Vm upon pi, 2 Vm upon pi, so 2 Vm upon pi, that is 4 by pi, and you will be wrong, because we also have to check the frequency of the reference. So these things we have to check, they are different. Okay, they are not in the same frequency. So what is happening? So let me plot the switch timing diagram position, and then I will plot the output diagram. So what is happening if I plot the switch timing diagram, right, this is T, this is, let's say, switch position, right? So at T equals to, so switch will move according to the timing set by V reference, right, according to the frequency of the V reference, that is what, that is actually 1000 hertz. Okay, if our bandwidth, right, whatever bandwidth they have provided is much smaller than the frequencies of the signals, so you don't have to worry about anything, right? All you will do, you will just do your normal analysis. You will just do your normal analysis. If this frequency of the signals are much higher compared to the bandwidth given, then you don't have to worry anything. You will just measure the DC values. That's it, right? That is point 1. Now point 2 is the switch will be controlled according to this frequency, that is 1000 hertz. Okay, 1000 hertz. So one relation I know, that the frequency here is 2 pi, that is 2000 radian per second, right? And the so what is the time period? Time period would be not 2000 radian per second, sorry, 2000 hertz, right? This is the time period of the sense line, and the reference line has a time period, sorry, this is the frequency of the sense line, and the reference line has a frequency of 1000 hertz. Okay, reference line has a frequency of 1000 hertz, right? So what I can say, what is the relation between time period? So your f reference is equals to f sense divided by 2, or I can say, if I take the inverse relation, your t sense would be equals to t reference divided by 2. Okay, t sense would be equals to t reference divided by 2, that's it, right? So let us assume our t reference to be t. Okay, so our t sense would be half of that, half of the time period. Okay, so I am assuming our reference time period to be t, right? So my switch timing diagram will follow the reference time period. So for half the time period, I see that Vref will be positive. So in that case, switch will be 1. Switch will be 1. Now for the next half time period, Vref would be negative. So switch will be 0, and this waveform will be repeated. Okay, this will be 3t by 2 and so on. Correct. Now this is my V out. Now V out is pretty interesting, right? So let me plot the V sense actually first. Vs, that is V sense, right? Now V sense has a time period half of the reference time period. So in the half time period, my V sense will complete a whole time period. What do I mean by it? So V sense will complete a whole cycle in half the time period. So it will be like this. Okay, not, this is not proper to scale, but you get the point, right? Now what is your V out? So whenever your switch is at position 1, your V out is actually equals to V sense. Whenever your switch is at position 1, your V out is actually equals to V sense. So it is this value. And whenever your switch is at position 2, it is actually equals to minus of V sense, right? And minus of V sense would be here. And this cycle will repeat. Okay. Can you, so what is the average value of this waveform? It is 0, right? It is 0. It is not actually this. So it is not actually rectified waveform. This waveform will be cancelled. So average value would be simply 0. So V average will be 0. So 0 would be your answer. Very good question. This was a very good question that was asked in 2024. Let's solve this question. Instrument required to synchronize an alternator to the grid is what? So we certainly need a synchronoscope and we certainly need a voltmeter. Okay, these are the instruments that are required. Voltmeter, why? To, if I am connecting to the grid, the voltages must be same, and synchronoscope basically to sync the phase angle and the what do you call, phase angle and the frequency. Okay, these two things we have to sync, so that's why synchronoscope are used. Frequency basically means the speed of the alternator, right? So yeah, this was in the, this was came in 2025 in GATE. So just if you know, like you will be able to answer, otherwise you will not be able to answer it. Let's now solve this particular question, right? This is the next question. Power consumed by a 3-phase balanced load is measured using 2 wattmeter method. The per phase average power drawn by the load is 30 kilowatt. At root 3 by 2 lagging power factor, the readings of the wattmeter would be. So we know the readings of the wattmeter W1 is equals to root 3 VLIL minus 5 and W2 root 3 VLIL cos 30 plus 5. Okay, so average power down is then, right? Okay, average power down by the load is 30 kilowatt. So certainly we can eliminate these two options, right? So anyways, we see that adding these two up, it is giving me 90 watts and 90 watts. That is not possible, right? Average power down is 30 kilowatts. So either this will be my correct answer or this will be my correct answer. So I can calculate actually the ratio. Okay, hold on, no, not this. This will not work. So if I know the power factor, right? Power factor is root 3 by 2 lagging. So what is the power factor angle? Phi. So it is 0.866, right? 0.866 is basically cos 30. So power factor angle is plus 30 degree. So if it is plus 30, right, the ratio of W1 over W2 when my power factor angle is 30, this will be cos 0. That will be root 3 into VL into IL. And this will be 0.5, right? Root 3 into VL IL into 0.5. So one will read the half of the other. Okay, this will be 2. So the ratio between them will be 2. They will not be, certainly not be equal. They will be, okay, hold on. One will read the half of the other, right? W1 by W2 must be 1 by 2. Am I correct? Cos 60 is half. This is 0. 30. That is correct only. 60 is half. One will read half the other. Okay. 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 Although I eliminated these two options, right? These also can be true. Okay. Why? Because the wattmeter can read negative values. Okay. The wattmeter can read negative values. So here, although I told you that the addition of these two is coming out to be not equal to 30, so certainly we can eliminate this. But here I missed a point that the wattmeter values can be negative as well, right? The wattmeter values can be negative. Okay. So wattmeter values can come out to be negative, that we discussed previously. Okay. So one wattmeter reading can be minus 60, minus 30, and other wattmeter reading can be 60, right? So addition of these two will again come out to be 30 only, because I see the ratio between the two wattmeter readings must be 2. Okay. Hence, it is not possible that this will be my correct answer, right? The ratio is not 2. Although the addition is coming out to be 30, but ratio is not 2. Here I see only in this option the ratio is coming out to be 2, right? Otherwise, all the other option ratio is not coming out to be 2. That can be verified with our formulas as well, right? Ratio must follow these two formulas. So ratio must be 2. Although the signs can be different, okay, depending on the power factor angle, but ratio must be 2. Okay. So yeah, option C is correct for this question. Okay, so one can read the negative angle as well. So now we will begin with bridges. So let's start with bridges. So these are my bridges. Okay, so in bridges we have DC bridges, Wheatstone bridge, Kelvin's double bridge, and we have AC bridges. Okay, so mostly my expectation is they will ask from Wheatstone bridge, or they can ask from these kind of bridges, but we will use again our basic bridge principle. What is the basic bridge principle? If the bridge is under balanced condition, the multiplication of the opposite impedances will be equal. Okay, so basically R1 into Rx will be equals to R2 into R3 under balanced condition. Balance means if the galvanometer is connected in the diagonal of the bridge, it will have zero current. Okay, this is for the resistive load, DC load. For impedance as well, Z1 into Z4 will be equals to Z2 into Z3. This is the main concept of bridge. That's it, right? There are multiple things involved in it that certainly we will discuss, but this is the main concept. So basic thing regarding Wheatstone bridge, I don't need to explain much here. Okay, now one thing is there, if you assume you have a galvanometer connected here, what is the voltage that will be developed across it when it is not in the balanced condition? When it is in the balanced condition, this will be 0. But when it is not in the balanced condition, this will be the voltage developed across the bridge. How have I derived it? Simply assuming that the impedance of the galvanometer is infinity. right? If it is infinity, no current will flow here. Simple voltage division rule, we can compute the voltage difference between point B and D. Okay, point B and D. So V bridge is equals to VBD. Now certain things are there, that if let's say all these resistors are R, and let's say I put a small change in this resistor R plus delta R, what will happen? If I have a small change in this resistor R plus delta R, what will happen? So if we again equate, what will be the voltage developed? If let's say when all of these resistors were R, right, then the voltage was simply 0. If all of these resistors will be R, bridge will be in the balance condition, the voltage will be 0. If I change one of the resistor from R to R plus delta R, then the voltage will be this. This will be the voltage, that is delta R by 4R. Okay, Vs into delta R by 4R. Now this is called as the sensitivity of the Wheatstone bridge. So if I change one of the resistor from R to R plus delta R, so basically what is the voltage that is developed in the bridge with respect to the supply voltage, okay, with respect to Vs. This is called as the sensitivity of a full bridge. Okay, now there are multiple formulas for sensitivity. One is the current sensitivity, one is the voltage sensitivity, right? Simply whatever is the minimum amount of current that I am sending, for which whatever is the deflection that I am receiving, that is called my current sensitivity. It is measured in mm per milliampere, or you can measure in degree per milliampere, that also is fine. Voltage, simply the denominator will be in the voltage, that's all. Okay, so bridge sensitivity, it is theta, the change in the angle of the galvanometer upon the change in the voltage, right? What is the change in the voltage? That is simply delta R by R. No, sorry, not in the voltage, it is change in the resistor. So basically what sensitivity I want to measure? I want to measure the sensitivity of a bridge. What is the task of a bridge? Task of a bridge is to tell me whether the bridge is balanced or not, to calculate the unknown resistor, okay, resistance. So this is called as the bridge sensitivity, that measures in terms of resistance. So if there is a small change of delta R from the previous resistance, that is R, what will be the sensitivity of the bridge? So it will be theta upon delta R by R. Theta R upon delta R by R, okay. This is the sensitivity of the bridge, right? So we can derive few values here because I know this, that my theta can also be written as, theta will be equals to sensitivity of the voltage sensitivity into V bridge, right? So here I am replacing voltage sensitivity into V bridge, and this is same delta R upon R. Now this is nothing but this formula, right? Delta R upon R, this can come here, that will be equals to Vs by 4. So ultimately this will be replaced by Vs by 4. So you can make few manipulations here. I'm just telling you, you can make few manipulations to compute the bridge sensitivity, but your actual bridge sensitivity formula is this one. That's all right. But if voltage sensitivity is given, then you can actually use your voltage sensitivity to calculate the bridge sensitivity using these kind of manipulations. So whatever we discussed, that was so whatever we discussed here, right? Sorry, this was not a full bridge. Whatever we discussed, this was for a quarter bridge. Basically, if I'm changing quarter of a bridge, right, only I am changing one of the resistors. If I change half the bridge, that is called as half bridge. So then the voltage will be, if it is quarter, right, the ratio of V bridge, that is this voltage upon the source voltage, is delta R upon 4R. Okay, V bridge upon Vs, that is delta R upon 4R. Now if I make it half the bridge, okay, if I make it half bridge, right, it will be changed to, like, your voltage in the half bridge, right, basically the deflection across these 2 points will become Vs by 2, it will not be 4, delta R by R. Okay, so sensitivity in quarter bridge, it will be 1 by 4 Vs by R. If you derive all these formulas, right, you will get this result. Okay, it's good if you are able to remember it, this will be used later on. So voltage developed across the quarter bridge will be Vs by 4 into delta R by R. Okay, and the sensitivity in a quarter bridge would be Vs by 4 R. Vs by 4R. Okay, that is the sensitivity of a quarter bridge. sensitive voltage developed across the half bridge would be exactly same carbon copy, just 2 will be there. And what does half bridge means? Half bridge basically means I'm changing 2 of the resistors. Previously I only changed 1 resistor, that's why quarter. Now I am changing 2, that's why it is half. If I change all of them, it will become full, all 4, right? It will become full bridge. So in case of full bridge, the voltage developed will be VFB by Vs, that is delta R by R. Okay, that's it. So that's how you remember it, right? Okay, so yeah, these are the few important things that you must know regarding Wheatstone bridge. For AC bridges, use this principle, right? Z1 into Z2, Z1 into Z4 will be equal to Z2 into Z3. What you need to do, there will be 2 variables now. One will be equating the magnitudes, right? You will equate the magnitudes as well. That is, magnitude of Z1 into Z2 must be equals to Z2 into Z3, as well as you will equate the phase term. So basically, you will equate the real part and the imaginary part both in case of AC bridges. That's all. Now quality factor, this is the formula for quality factor. Okay, this you must know. Okay, so it is basically the energy stored upon the energy dissipated. So it is the reactive power upon the active power, right? So it is nothing but equals to tan phi. This also can be asked. This also can be asked. Okay, quality factor in case of bridges will be equals to tan phi. Okay, if power factor is given, you will be able to comment on the quality factor. Also, dissipation factor is also equals to 1 over quality factor. So dissipation factor is actually equals to cot phi, which is also equals to tan of delta, where delta is the dissipation angle. These are the few terms that can be asked. You should know these terms. Okay, so simply I have given you the example what will be the quality factor for these following configurations. If R and L are in series, the quality factor will be simply XL by R, that is omega L by R, that we already know. If R and L are in parallel, so always remember it is the reactive power upon the active power. It is the reactive power upon the active power. Okay, quality factor is equals to reactive power upon the active power. Actually the definition is energy stored upon the energy dissipated, but we know if I integrate, if I if the power is constant throughout, then I can convert this energy into power. Okay, I can cancel out the time term. So your quality factor for a parallel circuit, right? What is the reactive power? V square by XL. What is the active power? V square by R. So quality factor would be R by omega L. That's how you remember it. Okay, quality factor in measuring instruments, you will remember it like this, that if the power is constant, then energy and power can be proportional. So you will say that it will be always reactive power upon the active power, ratio of reactive power upon active power. Okay, so in the first case, because the current is constant, so I will do, what is the reactive power? I square into XL. What is the active power? I square into R. What is the reactive power here? V square by XL. What is the active power? V square by R. What is the active power here? V square. What is the reactive power here? V square by XC. Okay, V square by XC. And what is 1 by XC? It is omega C. So it is simply omega C. And what is the active power? V square by R, right? So this R can go at the top. So your quality factor actually is equals to omega RC. And your dissipation factor will be nothing but the inverse of your quality factor, right? So make sure you remember this. This will be asked. This can be asked. Okay, very important thing. Okay, yeah, cool. Now there are few bridges that I although don't recommend you to remember exactly. Like you don't need to remember the circuits. Don't worry about the circuits. All you need to remember is which name corresponds to what. So Maxwell, wherever there is M, right? Maxwell, Maxwell, Hayes, Anderson. All these are used for measurement of, and Owens. All these are used for measurement of inductance. Okay. So M is for medium value of inductance. H is for high value of inductance. High value meaning high quality factor inductance, and A is for low, accurate, for low quality factor, accurate in inductance. So these are the bifurcations that can be asked from instrumentation. For electrical students, you don't need to remember it, but for instrumentation, they can ask a 1 mark question that Maxwell's inductance bridge is used to measure medium inductance, high inductance, or low inductance, right? Okay, so yeah, that is what Maxwell's inductance bridge is used for. And Owens bridge is this. Owens bridge is low, right? Anderson's bridge is this. right? Okay, so these are all used for inductance. Now D-shorty bridge, wherever there is D is used for dissipation factor, right? So the D-shorty bridge is used for capacitance measurement. Similarly, Shearing bridge is also used for capacitance measurement. Weighn bridge is used for frequency measurement. Weighn W omega, so it is used for frequency measurement. So these are the bifurcations that you should remember. That's it. Don't have to remember the circuits, don't worry. So there are a lot of things. I will not say you to remember these circuits and all. Okay, don't worry about this. And in Wehn's bridge, just remember this, the frequency measurement is like this. Okay, your frequency omega will be under root of R1, R2, C1, C2. So this R1, R2, C1, C2, whatever are the resistors connected under balance condition, the omega would be 1 by under root R1, R2, C1, C2. This is the thing that you need to remember for Wehn's bridge. Okay, that's all. Phasor diagram, don't worry, you will be able to solve it. Okay, now Kelvin's double bridge, again I hardly feel like they can ask a question from this, because this has a very dangerous formula. This is the formula, okay, for Kelvin's double bridge, that you can remember it. For instrumentation, I will say you must remember it. For W people, maybe you can assume that you don't need to remember. Okay, you don't need to remember. Okay, so you can avoid this. Yeah, medium resistance measurement, all these are there. So I think this you will be able to solve with basics. This voltmeter ammeter method also you will be able to solve with basics. You don't need to understand all this. Okay. Now here we have some a loss of charge method that essentially uses transient to measure the resistance. So this also you can solve with basics. So don't have to worry about this. We have ohm meter also, don't worry about these things. I hardly feel they can ask this. Potentiometer also, it like basically the resistance depends on length. So this also we don't need to worry much about this. We can solve this with basics. Okay, don't worry. So it also works on the principle of null deflection. Let's now start with the questions and we will see what we can do. So inductance is measured by what? Shearing bridge? No, shearing bridge is used for capacitance, right? It will be measured for Maxwell's bridge, and Kelvin bridge is used for low resistance measurement. Wein bridge is used for frequency measurement. So they do ask these kind of questions. Okay, so at least have a bit of idea. At least have a bit of idea, right? This question came in GATE EE. So option B will be correct certainly, because we have just studied, right? So let's solve the next question. This is the next question. The problem is like this is a very simple question, right? And it will take you hardly 10 seconds to solve this. So you are saving so much of time and gaining 1 marks. So that's a very good trait to do. Next question. In the bridge circuit shown, the voltmeter V showed 0 when the value of the resistors are R1 equals to 100 ohm, R2 equals to 110 ohm, right? So R1 is 100 ohm, R2 is 110 ohm, R3 is 90 ohm. Okay, they're asking me the voltmeter reads a value of 0. Okay, the voltmeter reads a value of 0. So basically this point and this point have the same potential. Okay, so now they're asking me what is the value of R4. This point and this point have same potential, right? R1 by R2 is equals to RA by RB. Okay, so basically R1 by R2 is equals to RA by RB. They basically use this formula. This is the formula for Kelvin's double bridge. This is nothing but a Kelvin's double bridge. Okay, so mostly if they ask you some question from Kelvin's double bridge, they will give you this condition, right? So basically the ratio P by Q, capital P by Q, that is this outside bridges, right, is equals to like small p by Q, this two resistance. If these are equal, okay, then certainly what will happen is basically this whole thing will be 0, right? So basically your unknown resistance will be just the previous Wheatstone bridge formula. So if these two resistance are same, right, these two RA by RB is equals to R1 by R2. So basically the outside arm ratio of the resistance and the inside arm ratio of the resistance, if these two are same, then you will just simply follow your normal Wheatstone bridge condition for balanced bridge, that is R1 into R4 will be equals to R3 into R2. Okay, you can follow it. Okay, so these things you need to kind of remember few things. In measurement, some things you need to remember, right? So we know what is our R1, that is 100. We know what is our R3, that is 90. We know what is our R2, that is 110. So our R4 would be equals to 99 ohms. So this will be your answer for the question. Let's move on to the next question. So this is the next question. A balanced Wheatstone bridge has the following arm resistances. This. RCD is the unknown resistance. The value of RCD and its accuracy would be, okay. So RCD, right, will be equals to, so I have a Wheatstone bridge, right. So ABCD, right. So RAB into RCD would be equals to RCD would be equals to RBC into RCD. So not RCD, sorry, RBC into RAD, right. That is the condition if the bridge is balanced. Now here is the galvanometer connected. Now what I will do, what is my RCD? RCD is simply equals to RBC RAD upon RAB. Now they are asking me what is the actual value of RCD and its accuracy, right? So what is the true value whenever all of them are exact? So basically RCD will be equals to RBC is 100 into RAD or RDA is 300 upon 1 kilo ohm, right? Basically 10 cube. So that would be equals to 30 ohm. That would be equals to 30 ohm. Okay. So that is what my RCD is equals to. That is a true value. Okay, these are certainly not correct. Now what is the percentage? So how do you compute the percentage? Here I can use my simple formula, right? So basically your delta RCD would be equals to magnitude absolute value of delta RBC. I can add all of them up. Why? Because all of them are independent. They are not dependent on each other. All the values are independent, right? So I can add all these up. ED. Okay. So I'm computing the percentage error, right? So percentage is 2.1%, 0.5% and 0.4%. Okay. So overall it would be 3%. 3%. That is the relative error percentage, right? 3%. So overall if it is 3%, so what is the 3%? So my answer would be 30 ohm plus minus 3%. I can do this only because all of these values are independent of each other. This has been discussed in the error analysis part. So this will be 30 plus minus 0.10% is 3 ohms, and yeah, 3% would be 0.9 ohms. So option B will be certainly correct for this question. Okay, let's solve the next question. So in the Wheatstone bridge shown, R1 is this, R2, R3, R4 are these values. Okay, now what they are doing is the switch is initially open. The voltage between the points C and D changes by an additional upon closing the voltage between the points C and D, VCD is VCD. Initial voltage across the point CD when the switch is open is VCD. Okay. Now what is happening? Upon closing the switch at t equal to 0, the resistance in the arm changes by delta R1. The voltage changes by VCD. What is the magnitude of delta VCD by delta R1? That is what they are asking. Okay. What is the delta VCD upon delta R1? So this, right, don't use any formulas here. If you're not able to figure out, don't use formulas, right? Use basics. So this is open circuit voltage, right? So when the switch is open, what is the voltage? VCD. VCD would be simply this 10. Simple, I can apply voltage division. What is the voltage across these resistor and this resistor, right? It is R4 upon R2 plus R4. R4 upon R2 plus R4 minus R3 upon R1 plus R3. Okay. So this would be equals to 10. R4 is basically 1, right? So 1 upon 1 plus 1, that is 2. And R3 is 1, R1 is actually 1.5. So it is actually 1 upon 2.5. So this value is actually 1 upon 2.5, that is 0.4 plus 0.5 into 10, that is equals to 1 volt, right? That is equals to 1 volt. Now what is your what happens when this is connected? When this is connected, what is my R1 dash? It will be 1.5 parallel with 30, so it will be 31.5. So this will be equals to 1.5 into 30 upon 31.5. So it is 1.43 kilo ohms, right? So now what will be my VCD dash? VCD dash would be the same formula only, right? Things will change a bit. So the first part will be same. It is 1 by 2 minus your R1 dash is 1.43. It is not 1.5 anymore. So it is 1 by 2.43. Correct. So this will be equals to this plus 1 plus 0.5 into 10. That is 0.88. This is 0.88, right? Volts. Now what are they asking? They are asking me delta VCD upon delta R1. So what is delta R1? Delta R1, right, would be the new minus old, R1 dash minus R1, that is basically equals to minus of 0.07 kilo ohms. Okay, this should be in volt per kilo ohm, so the bottom side should be in kilo ohm only. And what is your delta V or delta VCD? Delta VCD is basically equals to previously it was 1 volt, now it is 0.88. So it will be old minus new minus old, that is 0.12 volt. So simply all you have to remember, this is negative, right? New minus old, this is negative. So all you have to do is you have to calculate the absolute value of the ratio. So 0.12 upon 0.07. So what will be this? 07. This will be equals to 1.68. Okay, so 1.68 in volt per kilo ohm would be your answer for the question. 1.68 volt per kilo ohm would be your answer for the question. Okay, so yeah, that would be the answer of this question. Let's solve the next question. Which of the following is used is the balancing condition frequency independent, right? Which of the condition is frequency independent? Certainly your Wheatstone bridge is frequency independent. Okay, your sharing bridge is also not frequency, like frequency is measured in Wien bridge. So balancing condition is dependent on frequency in Wien bridge. In all the other bridges, it is frequency independent. Although you feel like in sharing bridge and Maxwell bridge, there are frequency dependent terms. No, whenever you equate the real and imaginary term, the frequency term is cancelled. So all these balance conditions are frequency independent. Only in wine bridge, because we measure the frequency there, the balance condition depends on the frequency. Only in wine bridge. Okay, let's solve the next question. So this is the next question. The bridge shown is balanced when R1 is this, R2 is this, right, and a sine wave generator is given. So it is balanced, right? If it is balanced, what will happen? So the opposite impedances multiplication must be same, correct? So basically your R1 into R4, right? R1 into R4 must be equals to your Z1, sorry, your Z3 into Z2. So what is your R1? R1 is R1 into R4, that is 50. Z3 into Z3 into Z4, right? Z3 to Z3 into Z2. So Z3 is omega into L3 plus R3 into Z4. Z4 is simply parallel combination. I will write that later. Let me first equate this. What do they want? They want me to calculate the value of L3, right? So what is Z3? Z3 shall be equals to, okay, we don't even need to, let me keep Z3 as yes, let me keep Z3 as Z3 only, and I will write Z2 in its polar format. So Z2 in polar format, this is actually R2 into 1 by j omega C2 upon R2 plus 1 by j omega C2. So this will be equals to R2 divided by 1 by j omega C2 plus 1. So this, if I convert this into proper format, two pi into 2.9 into R2 is 210, right, into 10 raised to the power of okay, omega 2 pi into omega, right? Omega is like frequency is 2 kilohertz, so 10 raised to the power of, okay, what am I doing? Hold on a second. 10 raised to the power of minus 6. Okay, just give me 1 second. So f omega is 2 pi f is 2 kilohertz, right? So 2 into 10 cube into pi, right? So this is my 2 pi f into C2, that is 2 C2, that is 2.9 into 10 raised to the power minus 6 into R2 is 210. Okay, so this value is actually 210 upon j 3.826. Plus 1. It is plus 1. Okay, now yeah, if I calculate this, this will be whole squared plus 1 whole square under root into 210. So this is actually equals to 53.1. And what about the angle? Angle is 3.826 upon 1 tan inverse 75. So this will be minus 75 degrees, 75.35 degrees, right? That is my Z2 in polar format. So this actually is 53.1 angle minus 75.35 degrees. So what I can do is technically I can take it on the other side. So I will be able to calculate my Z3. So it is 100 into 50 upon the magnitude, that is 53.1. So your magnitude of Z2, or sorry, Z3 is equals to 94.16. Angle would be plus 75.35. So we got the Z2 magnitude. Now we can use it to calculate omega, calculate L, right? So basically your tan of 75.35, right, would give me, would be equals to omega L upon R. Okay, simple ratio, because it is a simple RL circuit. I hope you get the point. Omega L3 divided by R3, right? So what is tan of 75.35? That is equals to 3.82, right? 3.8253. Okay, so this into R3. R3 is how much? R3 is R3. Okay, R3 is also not given. Oh, interesting. R3 is also not given. Okay, then you will have to use both these equations. So your R3 would be equals to, okay, so let me use the magnitude condition as well. So basically your omega L whole square, basically your XL whole square plus R3 whole square, right, would be equals to your magnitude whole square. Okay, so from this actually you will be able to directly, okay, I will not be able to directly calculate my, okay, so let me replace here my R3. So my R3 is equals to omega L 3 by 3.825. 2 pi into F. So yeah, so this is my R3. So we can actually compute this. So this I can replace here, right? That is my R3, right? So this will be equals to, XL is omega L whole square, right? So omega into L3 square omega square plus omega square L3 square divided by 3.8253 square. That is equals to 94.16 square. Okay, so I think this will help us out to calculate the values. Uh, so this squared plus 1, that is equals to 56.97 into omega square into L3 square divided by 3.8253 square equals to 94.16 square. I can take the under root on both sides. So this will be actually, if I take the under root on both sides, this will be 7.548 upon 3.8253 into omega into L3, that is equals to 94.16, right? So your L3 would be equals to what? So this divided by 3.8253, that is equals to 2. So this should be, yeah, it should be 2 almost, right? 1 plus this, yeah, it should be almost approximately equals to 2 only. So this will be 1.97. So 94.16 upon 1.97 into omega, that is 2 pi into 10 cube. Is it? It is 2 kilohertz, right? So not 10 cube, sorry. 2 into 10 cube. Okay, so this will be equals to this into 2 into pi into 2 into 10 cube into 94.16. So it is basically they have asked in millihenry, right? So in millihenry I will have to multiply this by 1000. Okay, so in millihenry it will be 3.8 millihenry. That is coming as my answer, 3.8 millihenry. This will be the answer for this question. I think, yeah, that's how you will solve this question basically. Okay, so this will be the answer of this question. Let's now solve the next question. So this is the next question where it is again a bridge question where it is r plus delta, r minus delta, r plus delta. So they are changing the resistances, and what are they asking? The potentiometer with total resistance Rv is connected as shown. Okay, here, okay, it is connected here. The minimum value of the resistance Rv required to balance the bridge. Okay, the minimum value of the resistance required to balance the bridge. Okay, R value is 100, delta R is 1. Okay, and they want to balance the bridge. So a potentiometer, right? For a potentiometer, the resistance totally depends on the length. Okay, so let's say if the length of this potentiometer is L, right? And if I only see L by 2, so the resistance would be, if the overall resistance was R, this resistance only till this point will be R by 2. Okay, so let's assume that the whole resistance of the potentiometer is L. Okay, whole length of the potentiometer is L, and we are connecting it at a distance of X. So we essentially we get two resistance. Okay, one is this R1, another one is this R2 on both the sides. So resistance from this point to this point will be R1, resistance from this point to this point will be R2. Okay, and my R1 plus R2 would be equals to my RV. Now if the bridge is in balanced condition, right? So basically this multiplied by this must be equals to this multiplied by this, right? So now what is the resistance in this particular arm? It is not R plus delta R, it is R plus delta R in plus R2. Okay, so basically the resistance in the top arm, that is RA is R plus delta R, right? Resistance in this arm, it is R plus delta R. What is the resistance here? It is R2 plus R plus delta R. R2 plus R, sorry, R plus delta R plus R2. Yeah, same thing only. Okay, and resistance, multiplication of the resistance in these two lines. Okay, so this would be equals to R minus delta R into R minus delta R plus R1. R minus delta R plus R1. Okay, now R and R increase by R and R decrease. The potential of correlation is delta R. So what is R? R is 100 and delta R is 1, right? So this will be 101 into 101 plus R2, that is equals to 99 into 99 plus R1. Okay, so this will be equals to if I solve this, this will be 101 plus R2 will be equals to Okay, one more relation is there. Okay, what is that relation? So the strain gauge resistance, right, it depends on the point of contact. Have they told us what is the point of contact? I see they have not told us what is the point of contact, right? So what happens is, there is one more thing I told you, right? So the strain gauge resistance, right, R1 by RV will be dependent on the length. Basically, this, let's say this is length at length x, right, upon the overall length capital L. So if the overall length is L, and for that if I have resistance RB, then for R1 it will be x. If the distance from the 0 point reference point is x, so the ratio of the resistance will be equals to ratio of the lengths. But they told us anything regarding the length? Each with nominal distances, when the force is applied, RA and RD increase by delta R, and RC and RD decrease by delta R. A potentiometer with total resistance RV is connected as shown. Okay, if R is equals to 100 ohm and delta R is 1 ohm, the minimum value of the RV required to balance the bridge. What is the minimum value of RV required to balance the bridge? What is the minimum value? I have to calculate the minimum value. So I have to calculate the minimum value, right? So basically R1 plus R2 must be minimum. Okay, R1 plus R2 must be minimum. Okay, I can do that. So your this is 101 R2. So this is basically 101 square plus 101 R2 equals to 99 square. Or let me keep it like this. So this will be equals to 99. So this is equals to inverse 98 R1. This is equals to 101 plus R2. So your R2 is actually equals to 0.98 R1 minus 4. Okay, minus 4. So what is RV? RV is R1 plus R2. Correct. RV is R1 plus R2. So what is the minimum value that I can choose? So R1 is R1 only. So this will be 1.98 R1 minus 4. And I will need to minimize this function. How do I minimize this function? I don't see any condition. So certainly your R2 will be something positive, right? The lowest value of R2 can be 0. Okay, if I choose this value, if I assume R2 to be 0, that is the lowest value of R2, then what is the R1? R1 is equals to 4 by 0.98. Correct. So 4 divided by 0.98, that is approximately 4.0816, and this will be the lowest value actually. So R1 is this and R2 is 0. Okay, so if that is the case, then your RV comes out to be 4.0816 ohms, right? Because your R2 is 0, R1 is non-zero, and this is the lowest value, because the lowest value that R2 can take is 0, right? There I'm already subtracting something. The lowest value that R2 can take is 0. Same condition if you apply here as well. If you write your R1 in terms of R2, in terms of some R2, right? And then you assume that your lowest value of R1 can be 0, right? Then again you will find out the condition that R2 must be equal to this value, okay, and that will give you the lowest value that we can use. Like in this equation only you can put, let's put it, right? You put R1 equal to 0. If I put R1 equal to 0, your R2 will come out to be -4. That is not possible, right? So you cannot make your R1 equal to 0. If you make your R1 equal to 0, your R2 will come out to be -4. Negative resistance is not possible. So only one possibility is there. You make R2 equal to 0. If I make R2 equal to 0, then your R1 will be the lowest value. If I choose any value of R2 that is greater than 0, right, your R1 value also will increase, because your R2 and R1 are directly proportional to each other, correct? So I hope you get the point why your RV will be 4.0816 ohms. Okay, this was actually pretty conceptual question, not formula based but pretty conceptual question. Okay, yeah, let's solve this question. Solve the next question. Which cannot be used to measure inductance? Sharing bridge certainly cannot be used to measure inductance. It is used to measure capacitance. Maxwell bridge is used to measure inductance. Hay bridge again high quality factor. Series ON bridge is also used for accurate measurement, okay, or medium inductance measurement. So yeah, ON bridge can be used to measure inductance. Let's solve the next question. This is the next question. Consider the figure shown. The zero deflection in the galvanometer is required. The value of Rx would be what? If there is zero deflection in the galvanometer, that basically means there is no current that is flowing through this point, right? So this we can assume either to be short or open circuit. So if there is no current, I can assume this to be open circuit. So if this is open circuit, that basically means that this part is open circuit, right? But here I have connections, okay. So this is nothing but what kind of connection? This is not even star, not even delta. So this is star, right? So maybe I can convert this into delta. Yes, I can convert this into delta. Can I convert? Because this is anyways open circuit. Yeah. So let me convert this star into delta. Okay. Let me convert this star into delta. Then only we can calculate the value of Rx. So I have 40 over here. I have 60 over here. I have 60 over here, right? So converting from star to delta, right? Star to delta basically means summation. So it will be, let's say if I'm, so I all I need is this value of resistor and this value of resistor, right? So let's say this is RA and this is RB. So your RA would be equals to 40 plus 60 plus 40 into 60 divided by 40 plus 60, that is, sorry, 40 into 60 divided by the opposite resistance, that is 60. So 100 plus 40, that is 140 ohms. Okay. So yeah, similarly if RB you can compute, that would be 60 plus 60 plus 60 into 60 divided by 40. So this will be 15 into 6, that is 90, right? So 120 plus 90, that is 210. Now yeah, so this value is, that is connected in parallel, that is 210. This value is 90, sorry, 140, right? $140. So I don't care about this value because this is not even, like, the bridge is balanced, so I don't care about this part. Okay, so the opposite impedances must be same. So like multiplication must be same. So what is this equivalent impedance on this arm? This arm, right? So it is 60 parallel with 210. So this will be 9. This is 370. This is 3, right? 140 by 3, 140 by 3, 140 by 3. Okay, this is the resistance that is in this arm. What is the resistance in this arm? This would be 40 into 140 upon 180. Okay, so this is gone, this is 9, this is 2, so this would be equals to 280 upon 9. Okay, so 280 upon 9. Now we can use our simple bridge balance condition. So Rx into the opposite arm resistance, that is 140 by 3, must be equals to 90 into the opposite arm resistance. 90 into opposite arm resistance, that is 280 by 9. Okay, so here some 3 will be cancelled, this 3 will be 30, this will be simply 2, right? So your Rx comes out to be 60 ohms. Okay, good question. Just all you have to do is convert star into delta, that's it. So Rx will be 60 ohms. Let's solve this question. In the figure, okay, there are a lot of questions from bridges, right? Yes, a lot of questions from bridges. In iron only lot of questions came in bridges, so I'm solving as many questions as possible so that this video, the single video, is comprehensive for everything. Okay, so yeah, let's try to solve this question. Here in the figure shown, R is this value, delta R is this, instrumentation amplifier is assumed to be idle, the equivalent resistance seen between the points A and B. Okay, so they're asking me what is the equivalent impedance seen between the points A and B. So if we're calculating the equivalent impedance, right, so that means we can short the input voltage. So if I short the input, so essentially what happens is this point and this point are at same potential. So basically these two resistances are in parallel and these two resistances are in parallel, and after they became in parallel, what happened? Then essentially they are in series, right? So basically I will have this particular value, then I will have this particular value, and basically this point is directly here shorted, right? So what is happening? This point is connected A and B. So essentially, let's say this is some R dash, this is some R dash. So overall your RAB would be 2 R dash. That's all, right? So all we need to calculate is this R dash only. R dash is the parallel combination of R plus delta R and R minus delta R. So R dash would be basically R plus delta R into R minus delta R upon 2R, right? Because R plus delta R plus R minus delta R. So delta plus delta R minus delta R will be cancelled. It will be 2R. Okay. Now we know these values. We know what is R, that is 4.5 kilo ohm, and what is delta R, that is 1.5 kilo ohms, right? So this will be 4.5 plus 1.5 into 4.5 minus 1.5 divided by 2 into 1.5, right? So 2 into 4.5 basically. So this will be 6 into 3 upon 9. So this is 2. So R dash is 2 kilo ohms. So your RAB will be 2 into R dash, that is 4 kilo ohms. So it's not even a question of measurement, not even a question of bridge, right? Basic KVL KCL. So most of the questions will be solved with basic common sense KVL and KCL. Let's solve this question. In the bridge circuit under balanced condition, so 4 is your answer, okay? For the previous question, they have asked in kilo ohms, 4 is your answer. In the balanced circuit under balanced condition, in the bridge circuit under balanced condition, the values of R and C is what? Okay, this I am giving you as homework. Simply just equate, multiply the opposite impedances. Frequency is given. Okay, let me do it anyways. So it's not that difficult. I hope we can do it, right? So all you need to do is 500 plus j omega into L. Omega is 5000, L is 1, right? So this will be 500 plus 5000 into 1 by j omega c plus R is equals to multiplication of the opposite resistances if it is in the balanced condition. So this will be equals to 10 raised to the power of 6. So what I can see directly, I can directly see that the imaginary component is 0. If the imaginary component is 0, so multiplication of this, that is 5000 R plus multiplication of this particular term, right? Omega is 5000. So this will be 500 into 1 by 5000 C. This will be equals to 0. So from this you will get a condition. This 0 will be cancelled. This will be 10, right? So basically your C, okay, why is it coming out to be negative? It should not be negative, right? Hold on a second. Oh sorry, this will be minus, right? Why this will be minus? Because when I'm multiplying these two terms, the j, if I take it in the numerator, it is minus j, right? So of course you will have to take the sign, you'll have to consider the sign. This is minus j, and if I multiply these two terms, it is plus j, right? It is plus j. So make sure you consider the signs as well. So this is minus j, so your C will come out to be equals to 5 into 10 to the power 4 of R. Am I correct? That is what, sorry, C is equals to actually, sorry, your R is equals to, or let me write, yeah, your R is equals to 1 by 5 into 10 raised to the power of 4 into C. That is what your R is equals to, right? That is what your R is equals to. Cool. So yeah, you got your value of R. Now what do we need to do? What do we need to do? So we can compute the ratios here. So your R would be 1 by 50,000 into C, right? So either you can compute the ratios, or again you can equate the real part. If I equate the real part, what is the real part? So 500 into R, right? So 500 into R. Now J into J, right? J 5000 into 1 by J omega C, again it will be cancelled. 5000 will be cancelled. So this will be plus 1 by C. This shall be equals to 10 raised to the power of 6. Okay. And we know what is our R. R is 1 by this. So this will be equals to 5 into 10 square upon 5 into 10 raised to the power 4 into C plus 1 by C, that is 10 raised to the power 6. So this will be 1 by 100 C. So yeah, 1 by 100 C plus 1 by C, that is 101 C. Just give me 1 second. 101 by 100 C, that is equals to 10 raised to the power 6. So your C, right, your C would be equals to 1.01 microfarad. Okay, so 1.01 microfarad is only present in option C. So option C certainly will be your correct answer. You can verify, you can calculate the R value, you know C value, right? You can put here, your R value will come out to be 500, not 500, sorry, 19.802 ohms. So that's how you solve these kind of questions in a fast manner. Let's solve this next question. Again, what are they asking? They are asking Wheatstone bridge is shown the sensitivity of the bridge in terms of change in the balancing voltage E for unit change in resistance R. So if there is a unit change in resistance R, so they are asking me, okay, unit change. So if there is a unit change in resistance R, what is the change in the voltage E in millivolt per ohms? Okay, so when, so E is the open circuit voltage when there was no change, right? So this was initial E voltage when there was no change. What is the voltage across E? So if I assume this to be, they should actually properly shown what is the polarity, right? They should have shown the polarity. Okay, that's their fault. They should have shown the polarity. Okay. This will be equals to, EI will be equals to 10 simple voltage divider, because it is the open circuit voltage, right? So S, that is 5 upon, so that is 5000 actually, upon 5000 plus 50, that is 5050, minus, this is 10,000 upon 10,010. This is equals to So this, if I cancel, this will be 10,010 only. So what is happening? So initially it is balanced, this is 0. Okay, this is balanced actually. So okay, I think that's why they have not given you the sign. That may be the reason. Okay, initially it is balanced. Now in the final case, when there is a unit change in the resistance R, basically your R is now becoming, from 50 it is becoming 51. So now things will be a bit different. Okay, this will be same 5 into 10 cube. This will be actually 5051 because your R has become 51 ohms, not 50 ohms. So now what will be this value? Certainly I can calculate the values. So this will be 5 upon 5051 minus 1 upon 1010, okay, which is very low value, into 10 cube into 10. So in millivolts they have asked, so this will be minus of 1.96 millivolts. Okay, minus of 1.96 millivolts. Actually they should have given the like voltage signs. Okay, if they have not, I will assume the magnitude of change, right? That is my delta E, that is EF minus E initial, that will be equals to 1.96 millivolts for a unit change, right, in resistance 1 ohm. So basically your sensitivity would be delta E upon 1 ohm, that is equals to 1.96 millivolt per ohm. So 1.96 would be your answer for the question. Okay, that's it. Because they have not given us the sign, I will take the absolute value. Otherwise they have to give this question as empty. Okay, yeah, let's solve this question. In the circuit shown below, the internal resistance of the galvanometer is 100 ohms. The current of the galvanometer shall be equals to what? Okay, what shall be the current across the galvanometer in microamperes? So if I have to compute the current across this galvanometer, right, I can compute the Thevenin voltage and the Thevenin impedance across the galvanometer and then solve. So what is the Thevenin voltage here? Thevenin voltage VTH is the open circuit voltage, that is equals to again I can apply the simple voltage like voltage given. This is the this voltage minus this voltage, right? That is basically 4 bridge voltage, that is 4 into 1010 by 2010 minus 1000 by 2000. Okay, so this will be equals to 1010 divided by 2010 minus 0.5 into 4. So this is actually equals to 0.01. Okay, so or I can say, sorry, 0.01, right? That is basically 10 millivolt. 10 millivolt. What is the resistance RTH? The resistance RTH would be equals to, if I compute the resistance, right, this will be also shorted. So essentially these two points will be in parallel. So these two resistance will be in parallel, then these two also will be in parallel, then I will add them, right? I hope you understand how to calculate the RTH. Not explaining much because there is nothing much to explain. Okay, you already solved this in networks. So 1000 into 1010 upon 2010 plus these two are in series, that is 1000 into 1000 upon 2000, right? So this will be 1000 into 1010 upon 2010 plus basically plus this is 500, right, because there is a 50. So your RTH is actually 1002.5 ohms. So what is your IG current? Your IG current would be your VTH plus RTH plus RG, right? Now you will include the resistance of the galvanometer as well. So this will be equals to 10 millivolt upon RTH, that is 1002.5, plus RG, that is 100 ohms. So this is in milliamperes. I will multiply by 1000 to convert this into microamperes. That is the unit at which the question has asked us. So plus 100 inverse into 10. So into 10 raised to the power of 3. So 9 volts. So 9 microamperes. That is the answer of our question. 9 microamperes is the answer of our question. Let's move on to the next question. This is the next question where they have told us to consider the bridge and it is at balance condition. What is the frequency of the excitation voltage? So again, I hope you can solve it, but if you want me to solve it, I can solve it, no problems. This is LR, both are LR, right? Okay, R1 R2 is shown. So if it is at balance condition, I hope you can solve it, right? I will not solve it. So you will multiply these two impedances, you will multiply these two impedances, and you will find out the condition of omega. Okay, I will give you the answer. Answer will be 1.6 kilohertz. Okay, make sure you calculate in hertz, not in radians. Okay, make sure you do that. Your answer will be 1.6 kilohertz. Let's solve the next question. Okay, so this is the next question. So here the bridge circuit is shown and the figure A can be equivalently represented as figure B. Okay, the values of R1, R2 and Vc in the equivalent circuit are. Okay, okay, figure A can be equivalently shown here. This is not a balanced bridge. So what is my VH? So basically, okay, VC and all these things they are telling me. So what is my VH actually? VH actually is 18 into 6 upon 6 plus 3, that is 9. Right, that is my VH voltage, that is equals to 12 volts, correct? And what is my VL voltage? This would be 18 into 3.9, so that is 6 volts, right? So VH, so VH minus, if you see VH minus VL, right, is coming out to be 12 volts. Okay, so there is, if I assume there is some current here I1, but it is open circuited. If it is open circuit, how will hold on. These two are open circuit, that is fine. Let's see what is the value of R1, R2. So let's assume some current is flowing from here, that is going towards here. So VH potential, this potential is 12 volts, right? And this point potential would be what? This point potential would be the values of R1, R2 and VH they are asking me. What is the common voltage VC? How do you calculate the common voltage VC? This is 3 volt, this is 3 volt. The difference between them certainly is 6 volts. If I apply the KVL, okay. Let's assume that some current is flowing like this I1 and some current is flowing like this I2. Okay. So if I assume that, so I know certainly VH is 12 volt and VL is 6 volts, right? So if I apply a KVL in this loop, okay, so minus VH plus I1 into R1 plus 3 plus 3 plus this will be I2 into R2 plus VL equals to 0, right? And we know VH is 12 and VL is 6, so this will be 6 only. So what do we get? I get this relation, basically I1 into R1 plus I2 into R2 will be equals to 0. This is one relation that I get, right? Now what about the next relations? What about the next relations? So if I solve again, okay, if I apply a KVL in this loop, right, this would be equals to minus Vc minus 3 volt, that is V1, then this will be minus I1 into R1 and this will be plus VH, right? Now okay, this is becoming is I am not able to figure out what is my I1. That is what I am not able to figure out. The circuit is equivalently represented like this. Okay. Just thinking some stuff. Okay, one thing is there, if this VH and VL, right, is replaced by the circuit, so whatever is the Thevenin impedance here, the Thevenin same, I should see the same Thevenin resistance here as well. So let's solve it like that. So what is the Thevenin resistance seen here? It is simply, this will be grounded, these two will be in parallel, that is 2 ohms, 2 kilo ohms, and these two also will be in parallel, that is 2 kilo ohms, right? And ultimately the overall RTH would be what? Overall RTH would be 4 kilo ohms. Got it? Overall RTH should be 4 kilo ohms. Now what is the Thevenin impedance seen from these 2 points? So if I compute the Thevenin impedance seen from these 2 points, this is R1, this is short circuited, this is grounded, right, because Vc is 0 as well, this is short circuited, and I have R2 here, and I am computing the Thevenin impedance from here, right? So I am applying a test voltage source Vx and I am measuring the test current Ix. Okay, so what do I see? So simply whatever Ix current is coming out of this battery, same Ix current should come in here. So actually no current flows through here, right? So all of the current flows through this particular circuit. So your Vx by Ix is equals to R1 plus R2. Okay, that is equals to 4, right? That is equals to 4. So R1 plus R2 must be equals to 4. Only in these two cases R1 plus R2 is equals to 4, right? In these two cases. Now how do I compute the common voltage? So the what I can do is I can compute the open circuit voltage. So what is the open circuit voltage? Open circuit voltage, okay, open circuit voltage, will it help me? Let me compute the open circuit voltage here, right? So if I'm computing the open circuit voltage in this circuit VOC, right? So this will be 0 amperes of current, right? I'm computing the open circuit voltage. Here also there will be 0 amperes of current. I'm computing the open circuit voltage, and these will be replaced with a voltage source as they are shown. So this is simply plus minus 3 volt. This is plus minus 3 volt, right? Then the open circuit voltage certainly is coming out to be, this is Vc to ground, right? Vc, this is Vc only. This is coming out to be 6. Open circuit voltage is coming out to be 6, which is fine. This voltage VTH is coming out to be 6 volts. Okay, I was just thinking, how can I calculate the VH and like how can I calculate the VC? So we know this point, right? If I observe, what is my VH? VH is the potential with respect to ground, right? Vh is the potential with respect to ground, that is equals to 12 volts. So here in this equivalent circuit as well, the potential, the open circuit potential with respect to ground must also be equals to 12 volts. So that is how we will calculate, right? So open circuit potential with respect to ground, that is Vh, if it is open circuit potential, right, that means this point is open circuit, that is 0 ampere, with respect to ground must be 12 volts. Currently what is the voltage? It is 3 plus Vc with respect to ground, right? So from here my Vc would be 9 volts. Similarly, if I compute VL, the open circuit voltage VL with respect to ground, open circuit voltage VL with respect to ground shall be 6 volts. So this shall be equals to 6 volts. Currently what is VL equals to? So if I measure VL properly, right, so let's say this is plus minus VL with respect to ground. Okay, so if I apply KVL, minus VL, this has 0 drop, then again minus 3, then plus Vc equals to 0, right, ground to ground KVL. So my VL is equals to Vc minus 3 and VL is equals to 6 volts. Vc is Vc minus 3, so Vc comes out to be 9 volts. So both cases Vc is coming out to be 9 volts, absolutely correct. Hence Vc would be 9 volts and R1 R2 shall be 2 kilo ohms. So this should be your answer for the question. Now let's begin with CRO. Let's begin with CRO, cathode ray oscilloscope, right? So the very first formula of cathode ray oscilloscope is this one. So you will have to remember, CRO is nothing but it uses the principle of deflection of electrons. Of course, we will not learn the working principle right now because that's not the purpose of this video. The purpose of this video is to know what are the important points that you must keep in mind. So this is one of the important points, that the deflection, the vertical deflection of the electron beam on the screen measured from the y-axis, this deflection of any electron beam will be equals to L, where L is the distance from the midpoint of the deflecting plate to the screen. All this will be given to you in the question. Okay, into LD is the distance between the deflecting plates, into ED is the potential difference across the deflecting plates, divided by 2 into D is the distance between the deflecting plates, into EA is the voltage applied at the pre-accelerating anode plate. Now I do agree, very big formula, how will you remember it? Okay, I just gave a bit of idea how to remember. So you have to compute D, right, capital D. So you will, all the D terms will be coming at the numerator. So L will be anyways there, capital L, into, so because you have to calculate D, right, so it will be something LD into ED upon D into EA. These units will be cancelled, ultimately your D will have the same units as L. Okay, how to remember? If I have to compute D, so all the D terms should be at the numerator and the remaining terms should be at the denominator. L will be there in the front. That's how you can remember it, or if you have any other ways, you can also use that to remember this particular formula. Sensitivity is nothing but the deflection of the electron beam upon the voltage applied between the deflecting plate. So that is D upon ED, that will be basically L into LD upon 2D into EA. Okay, that is the sensitivity. What about the so there is a factor called as deflection factor, that is nothing but the inverse of sensitivity. So these are the few things that you can remember. Okay, now there are many modes of CRO. If we are using YT mode basically means your X axis will be just the time axis. Okay, X axis will be time axis and your Y axis will be any voltage that you are measuring. So I hope you know how to calculate one small scale division. So all this will be given to you in the question. Let's say once, if one division in the time axis, or let's say if the frequency of the waveform is, let's say, is 10 hertz. Okay, and you are able to observe how many cycles you are able to observe. Let's say only I am able to observe till this point. So I am able to observe 2 cycles. So in this frame, how many divisions I have? 1, 2, 3, 4, 5, 6, 7, 8. So 8 divisions will correspond to what time? 8 divisions will correspond to 2t time, because one capital T will be one cycle, another capital T will be another cycle. So from this you can calculate what is the value of one small division, right? Similarly for voltage as well, if you know the peak value, you can directly say what is the amount, or what is the scaling factor of one division in the y-axis. Okay, that's how you can calculate the value of one small scale division in both the y and the x axis. Okay, so that is what we mean by volts per division. That is how we calculate all these parameters. Okay, now one formula there is this, unfortunately I cannot derive it right now, but there is this proof, right? Basically the rise time of the output, right, would be equals to the rise time of the input whole square plus rise time of the CRO. CRO also will take some time to reflect that whole square, then whole under root will give me the rise time of the output. Okay, this is a formula that you should remember, because these kind of questions can be asked in the examination. Okay, so the error in the rise time of the, like, because what should ideally happen is the rise time of the output and the rise time of the input must be same, but because the CRO has some delays, due to that the rise time of the output is more, it is taking more time to rise. So the error would be rise time of the output minus rise time of the input upon rise time of the input, that is the reference. Okay, now if I'm using XY mode basically means I'm comparing two waveforms. My x axis is not time axis. Okay, I'm comparing two waveforms, then we use XY mode. So we compare using Lissajous patterns. Okay, so ultimately what you will have to remember, don't remember all these things, this is the summary that you have to remember. So if in the x axis you are applying a waveform, in the y axis as well you are applying a waveform, and if the CRO is showing you a straight line, that basically means both the waveforms are in same phase. If their magnitudes are same, right, if their magnitudes are same, then either you will get a 0 degree phase shift or like 360-degree phase shift if you are observing a straight line. Okay, sorry, hold on a second, give me 1 second. No, sorry. Even if their magnitudes are different, then also you will observe a straight line. Sorry, so you will observe a straight line. All this we are talking when their frequencies are same. Okay, so let's say I have two waveforms. One waveform I'm applying at X plate, another waveform I'm applying in the Y channel, X channel, Y channel. Okay, and I am observing the pattern that is forming. Now, condition whatever we are discussing over here, both of them must have same frequency, right? Both the waveforms must have same frequency. Now, if both the waveforms have same frequency and the pattern that I am observing in the CRO is a straight line, that means the phase difference between the waveforms will be 0 degrees. If I observe a ellipse shape and the ellipse is the major axis is either in the first quadrant or in the third quadrant, right? So there is a derivation. Then the angle would be between, and phase difference between the two waveforms would be 0 to 90, and if it is a circle, then the phase difference would be exactly equals to 90 or 270 depending on which axis it is, right? If it is ellipse in the other quadrant, then the angle would be 90 to 180, and if it is a straight line but the straight line is present in the second and the fourth quadrant. So basically this is my quadrant, right? You will see the Lissajous pattern. This is my first quadrant, second quadrant, third quadrant, fourth quadrant. So if the straight line is present in the first quadrant and the third quadrant, then no problems, right? If the straight line is present in the second quadrant and the fourth quadrant, then you can say that you do have a phase difference, but the phase difference is 180. It is negative because your y will be equals to minus of x, right? It will be negative. Similarly, if your ellipse, the major axis, right, major axis of the ellipse is like this, right, then certainly your phase difference between the two waveforms will be between 0 to 90 degrees. Okay, if your ellipse major axis, this is the major axis, right, that is the lengthier one, if it lies between quadrant 2 and quadrant 4, then we say that it has basically phase difference between 270 to 360, as you can see here. Sorry, not 360, sorry, phase difference between 90 to 180. okay, because it is in the other quadrant, phase difference would be between 90 to 180. Here the phase difference would be between 0 to 90. So this is more important for IN aspirants. W aspirants, not that important. What is important, I will tell you. So there is a derivation you can see, but one more thing you have to understand, how to calculate the exact phase difference, right? If you want to compute the exact phase difference, so what you will do, your Lissajous pattern will be formed. So your exact phase difference phi for ellipse, okay, for an ellipse would be equals to sine inverse x1 upon x2. What is x1? X1 is the intercept in the x-axis, okay, and x2 is what? X2 is the maximum value of the curve, right? So x1 is the intercept of the in the x-axis and x2 is the maximum value, right? So this ratio will give you the exact phase value. This ratio will give you the exact phase value. Now this, according to this x value as well, you can exactly calculate what is your phase, right? So if it is in first quadrant, your phi will be positive. If this particular, so this is the major axis, right? Major axis is in the first and the third quadrant. So if the ellipse was something like this, then what is happening? Then your again you can compute the x intercept. Your major axis is in the second quadrant and in the fourth quadrant. So if it is in the fourth quadrant and second quadrant, certainly you know your phi will be between this particular range. Certainly you know this, right? Now all you need to do is just compute the magnitude of phi. So this will help you computing the magnitude of phi, okay, and that's it. I think that's it. You don't have to worry about anything else. Like there is one more thing. If it is clockwise, then this will be your value. If it is anti-clockwise, then this will be your value. But don't worry about it. Don't worry about it. I think this much is enough. Okay. Yeah. There are a lot of things. I don't think you need to remember all those things. I think this is also you don't need to remember. Ultimately, this is the part that you must know. Okay, in what range your angle will lie in, if the major axis in its which quadrant. There are formulas, but it's fine. Okay, now this is the most important thing for electrical aspirants. Question will be asked from this part. If question is asked, question will be asked in this part only. Now whatever we have been discussing, that was if the waveforms had same frequencies. If the waveforms had different frequencies, then you can actually comment about the ratio of the frequencies by the number of tangencies. Okay, how? I will show you. So let's say the Lissajous pattern that I see is this one, right? So now what I will do, I will take a vertical line. Vertical line, how many times am I intersecting my pattern? 2 times. Then I will take a horizontal line. In horizontal line, what is the maximum number of times I am intersecting my pattern? 4 times, right? So the whatever I have applied in the vertical, right? Vertical. So what happens is, so if you know the number of intersections while a vertical line, that you will put here NV, let's say 2, and number of intersections in the horizontal line, that is 4. So this ratio will give you the frequency FH upon FV. What is FH? FH is nothing but the waveform, frequency of the waveform present in the horizontal plate. So in the like in the X plate horizontal, and frequency of the waveform present in the Y axis. Okay, so this will be inverse, this will be opposite. This you have to remember. This you will have to remember, right? So this ratio will give you the opposite ratio of the frequencies present in the different channels. Frequency present in the channel, horizontal channel, and frequency present in the vertical channel, the ratio would be NV upon NH. That's it. Okay, yeah. So these are the important points regarding CRO. Let's solve questions on this. So the slope and level detector circuit in CRO has a delay of 10 nanoseconds. The start to stop sweep generator has a response time of 15 nanoseconds. In order to display the correct delay line, in order to display the correct, right, a delay line of what has to be inserted in the Y channel. So basically they're telling me that the CRO in the X axis has a delay of 100 nanoseconds due to slope level detector, and also its response time has a delay of 15 nanoseconds. Okay, so basically the X axis has, X channel has a delay of 60 nanoseconds. So X channel has a delay of, sorry, not 60, 150 nanoseconds. 150 nanoseconds, right? So what will happen to the Y channel? So if they need to be in proper sync, right, the Y channel also need to have a delay line delay of 150 nanoseconds. So another additional delay of 150 nanoseconds delay has to be inserted in the Y channel. So option A will be correct. So few things are here that is not so much super conceptual, but just you have to know how to solve the question. That's it. Okay, let's solve the next question. This is the next question. A stationary closed Lissajous pattern on an oscilloscope has 3 horizontal tangencies and 2 vertical tangencies. Okay, so 3 horizontal tangencies and 2 vertical tangencies. For the horizontal input FH, the frequency is 3 kilohertz. What will be the frequency of the vertical input? So FV upon FH would be equals to opposite NH upon NV. So from this I can directly say what is my FV. FV would be equals to NH upon NV into FH. So this will be 6 by 9 by 2, that is 4.5 kilohertz. So option D would be my correct answer for this question. So we are done with the CRO questions. Only 2 questions came in W. Okay, I could not find any other questions. Now we will start with the instrument transformers and digital multimeters. So let us revise few things. So resolution, I hope you know, if I have a digital multimeter, right? So a digital multimeter can read a number between, a digit can read between 0 to 9. Okay, so I have 10 options. So the resolution will be 1 divided by 10 raised to power n, where n is the number of full digits. That will increase. 1 divided by 10 raised to power n into whatever is the small scale value, whatever is the one small scale value. That is how we compute the resolution. And your sensitivity would be, for digital multimeter, it will be resolution into the overall range. That is your sensitivity. Okay, sensitivity for digital multimeter is the minimum level that the multimeter can detect for a change. So basically resolution, basically this does not have any units. Okay, now sensitivity is the overall minimum change that the instrument can detect. So these are the definitions of resolution and range. Okay, and there is one more concept of half digit, right? So sometimes what happens, all these are called as full digits which can vary from 0 to 9. So there is a half digit that will only vary from 0 to 1. Okay, its number can only be 0 or 1, right? That is my half digit. Okay, so yeah, cool. So that is my half digit, right? So this can only vary from 0 to 1, this will be varying from 0 to 9 and all those things. Okay, so there is one more concept of error in reading. So error in reading, that will be basically how many counts are there. So there are 2 kinds of error, right? One is the reading error, that the user himself, he was reading from the digital multimeter, right? He can read it wrong. So that will be basically percentage error in reading into the amount read. Okay, that will be given to you in the question. Another one will be this error. This is the called as count error, that is dependent on the digital multimeter. That will be equals to number of count into the sensitivity. So by how many counts, right? Let's say if it was supposed to give output as 101, it gave 99. So there was an error of 2 counts, right? And what does each count represent? Each count is represented by sensitivity. That is the minimum value that each count is represented by. So it will be 2 times sensitivity. That's why the count error is simply equals to number of count into sensitivity. That is how we calculate the count error. Now that was about the DMM. Now Q meter is there. Again in Q meter, just I hope you know this, that the resonant frequency formula is 1 by 2 pi under root LC. Okay, from here you can actually compute the value of C and L. So yeah, that's what you need to remember in Q meter. Just one thing, sometimes they connect a self capacitance, or the capacitor itself has some self capacitance, then the frequency, right, changes, then the formula also changes, and you can actually compute the value of the capacitor with this condition. Okay, so that's the only thing. Sometimes we neglect this shunt capacitor, but if they consider the shunt capacitor, then your C actually becomes CD plus C1. That's it for a Q meter. Instrument transformer, it is just like a transformer only, but few things you have to remember, such as burden. Okay, burden is basically the load, power of the load connected, rating of the load connected on the secondary side. That is what my burden is. Okay, so it is simply secondary side burden. Burden basically means power, right? So there are a lot of things here, and I will, if you can, you can skip this topic. You can skip the instrument transformer, because there are a lot of things. Lot of things meaning you will have to simply write. Mostly they ask this formula, the current ratio error. Okay, the error between the CT. So mostly CT is the most important topic out of this. I know you already know basics of CT and PT, so I'm not explaining you all these things. The main point that I'm explaining is this part, the current ratio error and the phase angle error. Okay, you will have to, if you want, you can remember these two formulas. I am talking about for iron aspirants. Doubly, it's up to you, whatever you want to do. Okay, so in CT I will only say you remember these two formulas if you can. Otherwise, try to solve using basics. Don't study anything separately, that will be very difficult for you to solve. So I am only taking the question that came in doubly. Okay, recently this question only came. So mostly they will, if they are asking from doubly, they will ask very simple question. So the table lists two instrument transformers and their features, current transformer and potential transformer. So current transformer, you should know, you should never leave the secondary side open for a current transformer, right? Because it is a current, and if it is not able to measure the current, there will be huge flux developed, right? So for current transformer, the open circuit condition of the secondary side is not desirable. So X will be going with Q. And for potential transformer, primary is connected to parallel to the grid. Yes, for a potential transformer, certainly the primary side certainly will be connected in parallel to the grid, because we want to measure the voltage, right? So Y will be going to P, X will be going to Q. And now primary current is the line current. Certainly for a current transformer, primary current will be the line current, because we want to measure the line current itself. And of course, if you have matched X, only one is remaining, that is Y should go to S, right? Y will go to S, that is the secondary burden affects the primary current, because yes, it will affect the primary current because the voltage is constant. It will affect the current in case of potential transformer. So X will be going to Q and R, and Y will be going to P and S. So option C will be correct for this question, and this question came. So yeah, what we can do in doubly, I'm not solving the iron questions because that will become irrelevant and this will make the video lengthy. I don't want that. So now we will solve few questions in digital multimeters or digital instruments. So we have a 6.5 digit timer counter is set in the time period mode of operation with range set as ns. Okay, range is ns in nanoseconds. For an input signal, the time counter displays this. With the same input signal, the time counter is changed to frequency mode, the operation, and the range is set to hertz. The display will show what? Okay, so basically the 6.5 digit instrument shows me this is the amount of nanoseconds. Okay, time period. So it is in the time period mode. So basically this displays the time period of the waveform. So that is this much nanoseconds. How many zeros? 1, 2, 3, 4, 5, 6. So 10 raised to the power of 6 nanoseconds. Okay, now they're telling me that they keeping the input signal same, all they're doing, they're changing into frequency node. So now the multimeter will display the frequency in hertz. Range is set to hertz. So what is the frequency? If the waveform is same, it is 1 by time period. That is, what is this? This is 10 raised to the power minus 3 seconds, right? So this will be 1 by 10 raised to the power minus 3. So this will be 1000 hertz. So 1000, now the multimeter will display 1000. That's it. So that's how the simple questions are from digital multimeter. Okay, sometimes they ask very simple questions. Let's solve the next question. This is the next question. A 3.5 digit rectifier type digital meter is set to read in its 2000 volt range. Okay, it is set to read in its 2000 volt range. A symmetrical square wave 50 hertz and amplitude of plus minus 100 is measured using the meter. The meter will read what? Okay, the range is 2000 volts and it is set to read the voltage. Okay, symmetrical square wave frequency 50 hertz. So what will the voltmeter read? The meter will read what? Okay, it is a remember, it is a rectifier type digital meter, rectifier. So basically it will make whatever I have negative values, it will make it positive. So we are applying a symmetrical square wave of frequency 50 volts. Now for a rectifier type waveform, what we do, rectifier type waveform, right? So it is actually just give me once again. The meter will read what? So actually we are rectifying it, right? So actually if I'm, the input of the rectifier is a symmetrical square wave, but the output would be a simple DC value, that is simply 100 volts. Okay, now what will the meter read? So they are asking me what are the digits of the meter that the meter will read. So it's a 3.5 digit meter. So this will be 0 1, this will be going from 0 to 9, this will be going from 0 to 9, this will be going from 0 to 9, correct? Now what is the, so the range of the meter is 2000 into, I want to calculate the sensitivity, right? So that will be range into the resolution will give me the sensitivity, that is basically one small scale division. Okay, so what is the resolution? So how many different values can I measure? This is 2 into 2 into 10 into 10 into 10, right? So total I can measure 2 into 10 cube, 2000. So each digit represents 1 volt, correct? Am I correct? Each digit represents 1 volt. That is correct. So what will I read? If it's a rectifier type instrument, then the meter will read simply 100, right? Because each digit represent 1 volt, and we will measure this DC voltage, that is 100 volt only, so it will represent 100. Okay, so yeah, this will be the answer. Let's solve the next question. A 3.5 digit digital voltmeter has a specified accuracy of this much. Okay, if it is used to measure 10 volt DC voltage, the error in the measurement would be, where error is given as percentage of reading plus digit. Okay, it will have a 1 digit count of error, and of course this is the percentage of reading, whatever I am reading I will have this error as well. I will explain exactly what is the error. So if we are measuring 10 volt, right, so we will have a reading error of 0.5%. So that is 10 volt, because I am reading 10 volt, I will have a reading error of 0.5%, that is 0.5 upon 100, that is 0.05 volts, 0.05 volts. Okay, and I will have a count error of 1. What does that mean? So okay, if I have a count error of 1, have they told me what does 3.5 digit is to measure a DC voltage of 10, right? Plus digit. Okay, I will have a count digit of 1. So certainly I will have 0.5 percentage, okay, plus 1 digit of count error, right? So it will be 0.5 plus percentage plus something, but how do I compute the count error? I'm thinking that how do I compute the count error? So total how many digits I have? Total, like how many different combinations I can have? 3.5 digit, right? So this will be 2, 10, 10 and 10. So total I have 2000 different combinations, right? And there is a count error of 1. Okay, there is a count error of 1. So 1 digit can be wrong. So what is the percentage of count error in terms of the full range? That is 1 by 2000, right? So this will be 1 by 2000 into 100 percentage, that is actually 1 by 20 percentage, right? What is 1 by 20 percentage? What is 1 by 20 percentage? So 1 by 20 percentage is simply equals to 0.05 percentage. Okay, 0.05 percentage. So overall 0.05 percentage, right, of the full scale range. But I feel they have not given me the full, what do you call, two options, 0 or 1, right? 0 or just coming 1. I think this question is not complete. Like they have given the answer to be 0.6, but I'm not able to figure out. So what you need to do is, this is the count error, right? So count error is 1. So there can be a gap of like 1 digit can be wrong. Basically the count error, basically by how many counts I am wrong, it is 1. What is the total number of counts? Total number of counts is 2000, right? I can have total 2000 different combinations, correct? So total number of counts is 2000. Am I correct? Yes. Total number of count is 2000. So in terms of percentage, if I want to write, this will be this value 0.05 percentage. Okay, that is my percentage of count error. So overall error should be 0.55 percentage. I don't know why it is 0.6 percentage. According to me, it should be 0.55 percentage. If there is some discrepancy, you can let me know. But I feel overall count error should be 0.55 percentage. But I feel these kind of questions will not be asked in EE, so that's why I'm not giving too much emphasis on these kind of topics, right? Ultimately, measuring instruments, bridges, and your error analysis. These 3 topics are the most important ones. CRO, just that basic formula you should know, and I don't feel instrument transformer, these are so much important. You can ignore these topics as well. So with this, we're done with the measurement part. Now we will start with the electromagnetic field theory part. So let's begin with electrostatics. But before beginning with electrostatics, I just wanted to revise the most difficult thing that I know you will forget is this one, and this will be used in all of electrostatics. That how, so I will not revise everything because that will take a huge time. You can do it on your own. Revision X notes are there. You can download it and revise. What I will do is I will just tell you how can you remember this particular thing, right? So how to perform the divergence, perform the curl, perform the gradient in different coordinate systems. So I know you have watched this table, okay, where UVW is my coordinate axis, right, and H1, H2, H3 are the constants which will be later used in the divergence and curl equation. How should you remember it? I will tell you how to remember it. So for coordinate system, Cartesian coordinate system, XYZ, H1, H2, H3 will be all one. You don't have to worry anything because they are all in length, right? They are all in meters, they will all be one. So sorted. These are most simplest thing, right? Now rho phi z r theta phi. How will you remember for this? Remember this, that for rho, right, what is the arc length, right? If I have a radius of rho, right, if I move a angle of phi, what is the arc length? It is rho d phi. If I move a angle d phi, the arc length would be rho d phi, correct? What is the small length if I move along the rho axis? It is d rho, right? And what is the small length if I move, differential length if I move along the z axis? It is dz. Cool. So the differential length if I move along the phi axis is rho d phi. The differential length if I move along the rho axis, that is d rho, and the differential length if I move along the z axis, that is dz. Okay, and these are my constants. How? So h1 is what? It is the differential length along the rho axis, that is d phi upon d phi. That's all. Got it? Now, what is the differential length along the phi axis? It is rho d phi. So in the top, I will have the differential length divided by the differential of that coordinate axis, that is d rho. So d rho will be cancelled. It will be rho. I'm just telling you how to remember it. This is not the proper method. I'm just telling you how to remember this thing. Similarly, what is the differential length along z axis? It is dz, and I will divide by the dz, that will be 1 only. So this will not, this will be 1. Now I know this is the most difficult part, the spherical. For spherical, how will you remember it? So again, what is the differential length along r? It is dr, right? So it will be dr upon dr, that is 1. What is the differential length along theta? So if you remember in 3D, your r is this, the distance from the center, and theta is from the angle from the positive z axis. So the differential length along theta would be r d theta, right? That is what we're doing. The top is the differential length along the theta axis, that is r d theta upon d theta. Okay, so it is r only. Cool. Now what is the differential length along phi? Phi is x is here, so phi is the angle from the positive x axis, right? How do I compute the differential length along phi? For that, first of all, I will have to project this particular vector on the xy plane. So if this is theta, right, what will be the length of the projection? It will be r cos theta, r sin theta, sorry. This is along the z axis, that is r cos theta. Along the xy axis, it will be r sin theta, right? Now things have changed. Now the radius of the circle that I was rotating about, it is r sin theta, it is not r cos theta. So if I am moving d phi differential length with radius r sin theta, what will be the differential length? It will be r sin theta into d phi. That is what I have written here, r sin theta into d phi. Okay, r sin theta into d phi. This is nothing but rho. If you remember the convergence, rho was equals to r sin theta into d phi. Now simply divide it by the differential of that particular coordinate axis, that is d phi. So this will be r sin theta into d phi upon d phi, that is simply r sin theta. Okay, that is simply r sin theta, right? So this is your simple answer. So and this is your simple table. That is how you will remember the table. Okay, so first of all, if you ever forget, you try to write the results in the table by yourself. Okay, don't remember, write the results by yourself, derive the results. Got your h1, h2, h3. Now the main thing will come. You will have to remember these two formulas. You will have to remember these two formulas. There is no other option. Okay, so the divergence del dot a of in any coordinate axis will be 1 by h1, h2, h3, whatever coefficients you have calculated here, into differential of the first axis, coordinate axis, into h2 into h3, the constants of the other axes, into AU. AU would be basically your vector, the component of the vector that is present in that particular axis. Let's say in this case, if it's r cap, so it will be AR cap, whatever is the vector present in the r cap direction, right? Similarly, you will use it for the other axes as well. Similarly, for curl as well, this will be the formula. So this, you will have to find a way to remember this particular thing. I have already told you how to remember this table, and you are good to go. You will be able to solve most questions from vector calculus as well as from electrostat if they are asking you to calculate the divergence of curl, divergence or curl. How do you calculate the gradient? Gradient is very simple. Gradient is very simple. It will be basically, if you have angle, in the bottom you will always have the arc length. So what was the arc length in d phi? It was rho d phi, right? The arc length was rho d phi. That will come at the bottom. Gradient is very simple. What is the arc length? In this case, in the second case, it was r d theta, that is coming here, r d theta. What is the arc length here? R sin theta d phi, r sin theta d phi. So gradient I have told you, how can you remember, right? Simply remember it with arc length, that's it. Anyways, for the cylindrical, you hardly have to remember, right? It is 1 by rho, like rho d phi, that's all. This is the only thing that is changed from here to here. Okay, spherical, I do agree, you have to remember a bit more stuff like this one. So that I have told you how can you remember it. Okay, so this is the most important part where most of the students fail to remember. I have given you a trick, how can you remember. Other stuff you can revise. Let's start off with the questions. So the static electric field inside a dielectric medium with relative permittivity, this expressed in cylindrical coordinate system, is given by the following expression. Okay, so it's a static electric field, and the expression is this, AR, A phi, these are this. If the above expression represents a valid electrostatic field inside the medium, then the volume charge density associated with this field in terms of free space permittivity epsilon naught will be equals to what? Okay, pretty interesting question. So you have to calculate the volume charge density. Now if you remember this formula, what formula? Your electric flux density, that is D. We know if my electric flux density is D, right? If I integrate, if I do the surface integral, D closed surface integral D dot ds, that will give me the overall overall charge enclosed, right? D dot ds will give me the overall q enclosed. Okay, now this can be further modified. This D dot ds can be, according to Gauss divergence theorem, I can change it to the volume integral of del dot D dot dv, not dot dv, so del dot d of dv. Okay, and your charge enclosed can also be written in that format. How can you write the charge enclosed? Your charge enclosed, like you can write your charge enclosed in multiple formats, right? Either you can write it as surface charge density sigma dot ds integration, surface integration, right? Or you can write it as volume charge density rho v dv, right? So I can write the right hand side as rho v dv. If I write the right hand side as rho v dv, that means I can equate these two terms, right? These two terms. So basically, your del dot d is equals to rho v, but they have not given me electric flux density. They have given me electric field intensity. So we know this relation that electric uh, flux density is epsilon into electric field intensity. D is equals to epsilon into E. So I can replace my D because it is just a constant. It is not even a vector. So this will be sigma delta E, that will be equals to rho v. So is equals to del v upon epsilon. Okay. So actually they are asking me to compute my rho v. Right? They are asking me to compute my rho v, right? Okay, I actually I don't even need to, so I need to calculate this only. They are asking me to calculate rho v, and rho v would be equals to sigma into del dot E. Okay, so they are asking me to calculate the, if you see, they are asking me to calculate the volume, they are asking me to calculate the volume charge density. Okay, and you know your epsilon is equals to epsilon r epsilon naught. Cool. So now what I can do is we have to calculate divergence of my electric field intensity. Now the formula will come in handy. Okay, so do remember, so this is in the, if you see, this is in the spherical, okay, this is not even in the spherical coordinate system, it is in the cylindrical. Don't be scared. Here they have written r, I have told you rho, but don't be scared, right? If this is r, so in our case this is rho, in our case this is phi, and this is z. Okay, don't be scared if this is r or rho. They are telling it is in cylindrical, so don't be scared. They can change the names of the variables, right? Those are just variables. Okay, so in case of a cylindrical coordinate system, h1 h2 h3, what was h1 h2 h3? It was simply, if you remember, what is the differential length along rho? It is d rho. So d rho upon d rho would be 1. What is the differential length along phi? It is rho d phi. So rho d phi upon d phi would be rho. What is the differential length along z? It is dz. So dz upon z would be 1. Okay. Now what was the divergence formula? Del dot E, this will be equals to basically 1 by h1 h2 h3, that is 1 by rho, into derivative with respect to rho or r in our case, right? Let me convert everything into r because everything is written in terms of r, into h2 h3. h2 h3 is what? This, that is rho, into the coordinate that is present, like into the component that is present in the r cap direction, that is 2r. Okay, this is 2r. Sorry, not rho again, it is r, right? So I will write everything in terms of r. Our rho has been replaced with r. Don't be scared. Okay, rho has been replaced with r. So this is r into 2r, the component that is present along the air cap direction. Now dd phi into h1 h3, that is 1, into the component present along the phi cap direction, that is 3 by rho, 3 by r, sorry, plus it is simply del del z, and again it is h1 h2, right? h1 h2 would be r again, right, into the component present along the z axis, that is 6. So this would be 6. Okay. Now I hope it is much simpler for you to solve. Only this part is the difficult part. Okay. So yeah, this will be 1 by r. This will be 2r square. Derivative would be 4r. This would be 0 because it is not a function of phi. This also will be 0 because it is not a function of z. So it will be 4r upon r, that is 4. So del dot E is 4 and our rho v would be 4 into epsilon. Now epsilon r is given to me. The relative permittivity is given to me, that is 2.25, and your epsilon naught is epsilon naught. So 4 into 2.25, that would be equals to 9 epsilon naught. Okay. So 9 epsilon naught is your answer. That is not even present over here. I think that would be option D. That is not written. Okay. So 9 epsilon naught would be your answer for the question. That's how you solve this question. Let's solve this one. So here the vector function is given, represents a conservative field. Okay, it represents a conservative field, and all of it is along the xyz. So you are relieved. Okay, if it is along the xyz, you are relieved. Then they are asking the values of the constants k1, k2 and k3 if it is a conservative field. What does conservative field basically means? Conservative basically means the closed line integration along the field, right? This will be equals to 0. Closed line integration will be 0. Then only your field is conservative. So with the help of Stokes theorem, we can convert this into del cross f, and this has to be equals to 0. Okay, so del cross f is equals to 0, null vector dot, like this I am using Stokes theorem to convert this into the curl format. Okay, so from here we get a condition. What condition? Either del cross f will be 0 or del cross f dot ds vector is 0. If these vectors are perpendicular to each other, then also this can be 0. Okay, but here nothing is mentioned, right? I will not be able to, because no curve is given to me, right? No line is given to me. If no line is given to me, then I will have to take for the condition that del cross f has to be 0, right? Because it is conservative, because for a very particular ds vector, if these two are perpendicular, what is the value? It is this vector times this vector into cos of the angle between these two vectors, right? If the angle is 90, then this will be 0. Okay, but that is for a very particular ds vector. Now they have not given me what along which path they are talking about the conservativeness, so I will have to assume that for all paths this is valid, hence this has to be 0 for the other ds vectors. So if you don't understand anything whatever I said, ignore it. This is a good maths question that can come up. Okay, ultimately what you need to understand, if it is a conservative field, you will equate this with 0, right? If you did not understand whatever I said previously, that is a deeper topic that can be discussed later on. Nothing is mentioned, you will assume your del cross f to be 0, basically curl of the field vector to be 0. So it is in xyz coordinate, so you don't have to worry much. So simply you will compute the curl. So this will be ax cap, ay cap, az cap. Okay, this will be five y minus k1z 3z plus k2 x k3 y minus 4x. This will be coming in the third row, not in the second row, sorry. And here I will have del x, del y, del z. Okay, so this will be equals to so differentiation of this with respect to y, that would be k3 minus differentiation this with respect to z, that is 0. So this Ax cap has to be 0. So certainly K3 has to be 0. Am I correct? No, no, no. I'm differentiating this with respect to z. This is 3z, right? So this will be 3. So this has to be 0. Okay, let me solve this first. And this will be broken with minus ay into derivative of this, that is minus 4, minus derivative of this, that is minus k1, plus az into derivative of this, that is k2, into derivative of this, that is minus 5. So yeah, this will be equals to 0, right? Because the result will be a null vector, right? So all components will be 0. So k3 will be equals to 3, k1 will be equals to minus 4, and k2 would be equals to 5. Okay, hold on a second. K1, this is minus 4, this is okay, already a negative sign is there, right? So this will become plus k1. Sorry, this will become plus k1. Already a negative sign is there, so k1 would be plus 4. So k3 is 3, k3 is 3, k2 is 5, and k1 is plus 4. So option C is correct for this question. So mostly your EMFT questions will be solved with this particular formula. Sometimes extra knowledge is required, I do agree, sometimes it is required, but mostly it will be solved with this particular formulas. So you see, you have been given a electric flux density along the r, phi and z direction. So it is again in cylindrical coordinate. So they are not using rho, they are using r. So don't be scared again. Okay, this is the same as rho. The total electric flux in coulomb emanating from the volume enclosed by a solid cylinder of radius 3 meter and height 5 centimeter oriented along the z axis with its base at origin. So basically they're telling me, if I have a cylinder at x, y and z whose base is at the origin, okay, and with its height oriented along the z axis. So it is along the z axis, its radius is 3 meter. So basically this is the cylinder. Along the z axis, the height is 5 meters and its radius is 3 meters. Okay, so basically we will have to compute the total electric flux in coulomb. Total electric flux in coulomb phi will be the surface integral closed surface integration of d dot ds. Okay, that will be the total electric flux because it is given in coulomb per meter square. So d dot ds will be in coulomb. Now how do I calculate this value? How do I calculate this value? So here we have to first of all see how does my surface look like. So what are the things that are varying? So certainly I can see I am going along the z axis, right? And I am going around the phi axis, but my rho is constant, right? It is a cylinder, right? My rho is constant. Rho is what? Rho is always 3 meter. The distance from the z axis, it is always 3 meter. So that is the surface of the cylinder. So rho is constant, but the other two variables are changing. That is, z is going from 0 to z2 equals to 5 meter, and your phi is going from 2 pi to 0. Correct? So that is what we will replace. So what will be my ds vector actually? What will be your ds vector? So this is very interesting, right? What is your ds vector? So your ds vector has 3 surfaces. If you look closely, the surface that I mentioned here, this surface is the curved surface that you see here. But you will have to also consider the top surface and the bottom surface. Correct? So there is a surface 1. Let's say this is my surface 1. This is my second surface, the curved surface, and this is the third surface. Okay. So I have three surfaces, right? I have three surfaces, right? Now how will I solve it? How will I solve it? Right. Uh, yeah, sorry for the noise. Okay. So for the first surface, let's say for the surface 1, what is varying? Do you know what is varying? For the first surface, it is a disk, right? It is a disk, correct? It is a disk. So if it is a disk, what are varying? My rho is varying. Rho is going from 0 to 3. So because it is a disk, I hope you have watched the revision X notes. There all these are mentioned. Because it is a disk, rho will vary from 0 to 3 meters. Your phi also certainly will vary from 2 pi to 0. But your z is constant. Z is equals to, in the first surface, z is equals to 5. Similarly for the second surface, right? This is the first surface. The second surface, everything is same. Only your z is equals to 0. That's all. Okay. Now, how do I define my surface ds vector? Ds vector would be whatever parameters are changing. Rho is changing, so it will be d rho. Phi is changing, so how to define phi? How to define change in phi? It will be rho d phi, right? The change in phi will be defined with rho d phi. Okay, the change in phi will be defined with rho d phi. I hope you remember, right? How to represent small change in phi? It is rho d phi. This we have discussed in the starting of today's lecture. So everywhere that concept will be used. So your surface vector is actually equals to rho d phi, rho d rho d phi. I do understand they have given r here. Don't worry, we will change everything in, we'll change here whatever is written in terms of r. Okay, we'll do that. Now this is just the magnitude of my surface vector. How do I compute the direction of my surface vector? Surface vector, direction of surface vector will always be outside of the surface. If you see here, the direction will be outside of the surface, that is here. Direction of the surface vector will be outside the surface, that is along the az cap direction. Okay, so the direction of the surface vector would be along the az cap direction. Okay, it will be outside the direction of the surface. Similarly, everything will be same in this case. What will be difference? The difference would be direction of the surface vector will be here, it will be outside the surface, right? That is in the minus az cap direction. So this will be minus. Okay, and yeah, so this is the direction of the surface for the second, for the third. This is not the second, sorry, for the third case. Okay, third surface. What about the second surface? For the second surface, what things are varying? So your rho is constant, so z will be dz, phi will be rho d rho. Okay, so this will be rho d rho dz. What is the direction? Direction is coming outwards of the surface, that is along the rho cap direction. So this will be a rho cap. Okay, got it? Cool. Now we will finally solve surface by surface. Your overall charge will be along all these surfaces. So overall charge will be addition of these three fluxes. Sorry, overall flux will be addition of phi 1 plus phi 2 plus phi 3. Okay, that is what your overall flux is equals to, right? So let me first compute phi 1. Phi 1 would be integration of this, right? So this is, remember, I will convert this into rho cap. I don't like this. I will convert this first of all into rho cap. So rho cap, this will be 15 a rho cap plus 2 rho, r is converted into rho, a phi cap minus 3 rz Az cap. So this I will use here. Dot this ds cap vector, right? So simply I will only consider the z cap direction. Obviously other components will be 0, other dot will be 0, right, because they are perpendicular. So simply this will be integration of, okay, why have I written here r, this will be rho, right? Sorry, this will be rho. Okay, this will be rho. So this will be converted as minus 3 rho square into z d rho d phi. Okay, and what is varying? If you see what is varying, rho is varying from 0 to 2 pi, sorry, rho is varying from 0 to 3, phi is varying from 0 to 2 pi. Okay, so we can so z is constant, right? What is the value of z? Z is simply 5 in this case. So this will be, z can come outside, it is just a constant number 5. I can solve this individually, right? So this will be d rho integration would be 2 pi and d phi integration would be minus rho cube by 3, minus 3 is multiplied, so this will be rho cube by 3, right, and this will be cancelled, and rho cube will go from 0 to 2, right, that is the radius, rho cube, sorry, 0 to 3, 0 to 3, 0 to 3. Okay, so this will be equals to 10 pi, negative sign is there, and this will be minus 27. Okay, so this will be minus 270 pi. Okay, that is the flux in the first surface. Now in the third surface, actually interestingly, because your z is 0, so this z is 0, right, everything is same, just the sign is different, but z is 0. So your in the third surface your phi 3 will be 0 because z is 0. What about the second surface, phi 2? Phi 2 will be, I will copy this, dot ds vector, right? ds vector is what? ds vector is this. Okay, in the second surface. And what are the, so let me first compute this. So this would be equals to 15 is only this will be non-zero dot product, right? Other dot products will be 0. So this will be 15 and rho d rho dz. So rho d rho dz. So your rho is going from, okay, rho is constant, that is 3. Rho is constant, that is 3. So this also will come outside. So this will become 45 into, okay, hold on, how is it d rho? Oh, sorry. So this will be rho d phi, right? Because your phi is changing and your z is changing. Sorry. This will be d phi. Okay, made a mistake. This will be d phi. Okay, just one small change. This will be d phi. D phi dz. So this would be equals to 45 into 2 pi into dz. Dz is, so what is the change in z? Z is going from 0 to 5, right? So simply it will be z going from 0 to 5, that is 5 minus 0, and this actually is 2 pi minus 0, right? 2 pi minus 0, 5 minus 0. So that is equals to 90 pi. 90 pi into 5, that is 450 pi, right? So this is your phi 2. So overall flux would be phi 1 plus phi 2 plus phi 3. So phi 3 is 0, phi 1 is minus 270, minus 270 plus 450. So that is equals to 30 and 80, 350, 180. So overall flux is 180 pi. That is what your overall flux is equals to, right? 180 pi coulombs. So this is your answer. Option D is your correct answer for this question. 180 pi. Okay. So so next question is this one. So 1 microcoulomb point charge is being held at origin in the Cartesian coordinate system. If a second point charge of 10 microcoulomb is moved from this point to this point, right, and then subsequently to this point, then the total work done would be equals to what? What is the total work done? So I'm moving the point. This is my initial position. This is my final position. So sorry, I'm moving my charge from this position to this position, right? What is the work done? So do you know what is the work done? So work done is simply equals to delta W is simply equals to charge of that particular charge, okay, into charge of that point charge into the change in voltage, okay, into the change in voltage. Okay, so into the change in voltage. Yeah, so I will have to calculate the change in voltage. I know the charge is 10 microcoulomb, right? All I need to calculate is the change in voltage. So what is the initial potential of the charge? Do you remember what was the formula? So the formula was Q upon 4 pi epsilon into R, okay, the distance from the origin, 4 pi epsilon into R. This was the formula for potential, right, if you remember. Like this, few more formulas we have. It's better if you can remember them. That another formula is there which relates the potential and the voltage at a point. So your E is actually equals to negative of the gradient of voltage. Okay, if I take the negative of gradient of voltage, that will give me the electric field intensity. In 1D you can derive it. Now your potential energy between two charges, right, that will be K Q1. K is basically K is 1 by 4 pi epsilon naught, if you remember it, and your epsilon naught is equals to 8.854 into 10 raised to power of minus 12 farad per meter. This also, if you remember, would be great. U, the potential energy between two charges, would be Q1 Q2 divided by 4 pi epsilon naught into R. Okay, 4 pi epsilon naught into R, or 4 pi epsilon into R. One more formula was there, force, right? So force, it is dependent between two, I'm talking about between two charges. So force in the vector format, okay, F21 will be equals to your 1 by 4 pi epsilon naught, this will be there, 4 pi epsilon, this will be there, into Q1 Q2 upon 1 to 1 magnitude of 1 to 1 whole square into A to 1 AR to 1. Okay, so simply this AR to 1 is nothing but the direction coming from 1 to 2, and this is the magnitude of the distance between 1 to 2, the point 1, if I have a point charge in 3 dimension, right? So this is my, let's say this is my 1, this is my 2, and this will be the AR. So this will be the vector R21, and AR to 1 will be the unit vector along the same direction. Okay, that's all. So don't be scared with this formula. And your electric field intensity for a charge, right, at a point, right, with respect to another charge, would be 1 by 4 pi epsilon into Q divided by the same, like this formula will not change. Just if I am measuring the effect, the electric field intensity due to the second point charge, right, that would be equals to this value divided by Q2. If Q2 is present here, what is the electric field intensity due to point charge 1? It is this value. Okay, these are few basic formulas that I think yeah, you can remember. right? I think that's it. And the charge is quantized, and a single charge, right, single charge is equals to 1.6 into 10 raised to the power of minus 19 coulomb. That is a charge of a single charge. Okay, single point charge. So these are the few things that you can just remember, right? Capacitance also has some formulas. We will come to the capacitance formulas later. Yeah, so let's come back to this question. So ultimately we'll have to find out the initial potential. I am computing the potential with respect to, so potential is always computed with respect to a reference, right? So my reference is at infinity, that is when this distance goes to infinity, that is 0. So it does not matter. So your potential at point I with respect to reference would be this, okay, would be this R1, magnitude of R1. So what is the distance in the first case from the origin? It is 10, right? Distance from the origin is 10. So this actually your Vi Q upon epsilon into 10, okay. And subsequently, if I am now, what is the final distance? Final distance V final is equals to Q upon 4 pi epsilon into, what is this? The distance, right, from origin in the final case is 5, right? So basically your work done would be delta Q would be, so delta W will be Q, there is a point charge here, right? So I am moving this charge, okay, the potential at point, this point, due to this point charge, right? So this distance is nothing but the distance between the 2 point charges, okay. I hope you get the point. This is nothing but the distance between the 2 point charges, okay. So this Q is nothing but 1 microcoulomb, okay. This Q is 1 microcoulomb. So capital Q is 1 microcoulomb that is present in the origin. So potential due to the charge that is present at the origin would be the distance from the point here, right? Initial potential, and this potential would be distance from the origin again, because the charge is present at the origin, okay. So your delta W would be equals to, delta W would be equals to Q. Now Q is what? The energy stored in the 10 microcoulomb. So this Q is 10 microcoulomb, okay. So this is 10 microcoulomb into Q, that is 1 microcoulomb, upon, okay, I can take the Q common, right? I can take the 4 pi epsilon also common. 4 pi epsilon, epsilon is 8.854, which is 1 by 4 pi epsilon is nothing but 9 into 10 raised to the power of 9, okay. So like what is my final expression? Final expression, delta W is Q into Q upon final potential, that is 4 pi epsilon 5, minus Q upon initial potential, that is 4 pi epsilon by 10, right? So what I am doing, I am just taking this whole part common, Q upon 4 pi epsilon, I am taking this as common, correct? If I take this as common, this will be this value, this will be 1 by 5 minus 1 by 10. So this would be 10 raised to the power minus 12, 10 raised to the power minus 3 into 90, 90 into 10 raised to the power of minus 3 into 1 by 5 minus this. So 10 minus 5, 5 by 10, that is half. So it is 45 into 10 raised to the power of minus 3. This is the amount of work done. What have they asked? They have asked in millijoules, right? So they have asked, if they have asked in millijoules, the amount of work done would be half of this. Sorry, 45. Correct. 5 magnitude. 4 pi, it is 9 into 10 raised to the power 9, right? Okay. Epsilon r is given to us. It is free space, right? If it is free space, that should not matter. But I'm thinking what am I doing wrong? So 90, it is 45 millijoules. It should be 45 millijoules. I'm just thinking, what am I doing wrong? Let me think here. 10 minus 5, that is, sorry, 10 minus 5, this is upon 50. What am I doing? Upon 50, right? Okay, sorry. So this will be 9 into 10 raised to power minus 3, that is 9 millijoules. Okay, so 9 millijoules will be your answer for the question. Again, how have I solved it? Again, I will say, simply, if you have to compute the work done, right? So for calculating work done, you will use this formula. The change in work done on a particular point charge, it will be Q into the charge value into the change in the potential. That will be the overall work done on that point charge. Okay. So change in potential will be initial voltage minus final voltage, right? What is the initial voltage with respect to R equals to infinity, with respect to a reference, right? So potential at this point on this point charge due to the 1 microcoulomb charge is this value. Basically, the 1 microcoulomb charge upon 4 pi epsilon naught into the distance from the origin of that particular charge. Okay, this is the initial potential, right? And the final potential, again you use the same formula. So ultimately, after solving all this, you'll get back to this answer. Okay. Okay, let's now solve this question, which seems like a capacitor question. Okay, so consider a large parallel plate capacitor. So I have a parallel plate capacitor, large parallel plate capacitor. Okay, and the gap between them is D, and it is filled. The plates are initially so permittivity, relative permittivity between the dielectric slab is 5. The plates are initially charged to a potential difference of V volts. Okay, so there is a potential difference of V, and then disconnected from the source. Okay, so still they have some potential difference between the plates, that is V. If the dielectric slab is pulled out completely, then the ratio of the new electric field to the old electric field. So if the dielectric slab is removed completely, what will happen, right? So how do I calculate? So ratio of the new electric field to the old electric field. So it's very easy actually. So we know this thing, right? The electric flux density will not change. Whatever was the previous electric flux density, that will be same in the case 1 and case 2, right? And what is the electric flux density in the case 1? It will be epsilon 1 into E1. That will be equals to epsilon 2 into E2, because in a parallel plate capacitor, right, the field intensity is like this. So hold on, starts from plus, goes to minus, right? So this will be same. So from here I can directly say that in the first case, what was my epsilon 1? Epsilon 1 was 5 into epsilon naught into E1. In the second case, I have air, so it is only epsilon naught into E2. So what are they asking? They are asking me the ratio of E2 upon E1. E2 upon E1 would be simply equals to 5. So 5 would be your answer for the question. Not much to debate over here. Okay, let's solve the next question. So this is the next question. An infinitely long line, the uniform positive charge density lies along the z axis. Okay, so basically I have an infinitely long line, lies along the z axis, right? So if it lies along the z axis, now what I can say, what are they asking? They are asking me the direction of the electric field. So it's a positive charge density, right? The direction of the electric field would be along what? Which coordinate? Do you see which coordinate is this? it is the cylindrical coordinate along the surface of the cylinder, right? So that is aero cap. So direction would be along the r cap direction. Okay. So if it is a cylindrical coordinate system, in our case always they are defining r, phi and z. Okay. So our rho would be here r. So the direction would be r cap direction. Cool. Now, what if this was negative charge? Can you tell me what would be the direction? If it was negative charge, it would have been inside. So the direction would have been actually minus r cap if it was negative charge. Because it is positive, it will be plus a r cap. Okay, cool. Let's solve the next question. So this is the next question. Let E be this, the value of this where V is the volume enclosed by unit cube will be what? So it is simple xyz coordinate and they are asking me the del dot E dot dV, right? So what is del dot E? Divergence of this function, that would be equals to divergence, right? Simple xy coordinate system. So that will be 4x plus 5 plus 3 dV volume integration. Okay. So x is going from, so it's very simple, right? Dv would be dx dy dz because it is a cuboid. So x is varying from 0 to 1, y is varying from 0 to 1, z is also varying from 0 to 1, correct? I don't think there is much debate how to solve this integration. This would be equals to x square by 2, x is going from 0 to 1, so this will be 2x square, that is 2, plus this will be 8 into 1 basically, so this will be 10. So 10 would be your answer for the question. I don't think I have to explain how to do the integration and stuff. You can do it. Let's solve this question, right? Okay, this question is pretty interesting. This question is difficult. Okay, so they are asking me, as shown in the figure, two conducting spherical shells are given. Okay, cool. And the potential at r equals to c is V1 and the potential at r equals to d is V2. Now they are asking me derive the expression for voltage in this region from r equals to c to r equals to d. So let's see if we can eliminate options, okay? Because deriving this will take us huge amount of time. I don't want to do that. Okay, I don't want to do that. So yeah, if I see that if I put r equals to c, the voltage that I should get here should be V1, right? So if I put r equals to c, this will be CD V2 minus V1 upon d minus c into c minus V1 into c plus V2 into d, V1 into d, d minus c. Okay, so this will be cancelled. So this is cancelled. This will be d into V2 minus d into V1 minus, so because d minus c is common in the denominator, V1 into c plus V2 into d minus 2V1. Okay, hold on. Okay, 2V1 into d. Okay, so can I eliminate some stuff here? So d into V2, d into V2, this will be 2d into V2 and d into V1, and this is minus 3d into V1. Okay, I'm getting weird stuff. Okay, V1 into C minus V1 into C and plus, that's it, 3 terms. So things are not getting cancelled. So certainly this will not be my answer. This will certainly not be my answer. Okay, so we have eliminated one option. We have eliminated one option. Let's see option B. So in the option B, if I put r equals to c, so here if I put r equals to c, this will be cancelled, right? This will be d into V1 minus V2, d into V1 minus V2 divided by d minus c, and the right hand side would be minus V2 into d minus V1 into c upon d minus c. Okay, so if I solve this, this would be equals to what? So I see that V2 into D is not getting cancelled. Okay, V2 into D is not getting cancelled. This is negative, right? Sorry, this is plus. So this is not minus. Okay, now it is fine. V2 into D will be cancelled. This will be D into V1 minus C into V1 upon D minus C. So ultimately this will be basically V1 only, which is correct. Okay, which is correct. Let me check for other options so that I can eliminate more. Then I will check for the next part. Okay, let me see here. In this case, like let's do it from here itself, right? If I put R equals to C, this will be cancelled again, and here I will have D into V1, I will have V1 into C. So certainly D minus C is there, and here I will have minus D into V2 and minus C into V2. So what will I have? I will have, after eliminating, this will be D into V1 minus D into V2 minus C into V1 minus C into V2. Okay, that is interesting. So hold on a second, hold on. V1 V2 V1 V2. So what I can do, I can take common D minus, I can take V1 common, that will be D minus C, and then from here also I can take minus D common, that will be D plus C, right? So that will be not some, okay, this is already negative, so this will actually become plus. Sorry, this will actually become plus. So if I take minus V2 common, this will be D minus C again. So ultimately your answer here, it would come out to be, if I am dividing by D minus C, this will be V1 minus V2, V1 minus V2. So certainly this will not be my answer. Okay, again let's check it for this one. Okay, all I am doing is eliminating the options. Okay, that's all I am doing. So if I check it for this one, at R equals to C, again this will be cancelled. Right? This will be D into V2 minus V1, and this will be, so D V2. So if I take V2 common, this will be D minus C, right? And if I take minus V1 common here, this will be D minus C again. So again the answer would come out to be V2 minus V1, which is not correct. My answer is actually V1 itself, right? So option B is correct. Okay. So I eliminated all the other options. Option B will be certainly correct. In exam hall, you will do it a bit faster, but you don't need to derive it. If you want to derive, you can use the Laplacian equation, that is del square V equals to 0, that you can use, but don't use it. Okay, don't use it. Yeah, so option B will be correct in this question. Let's solve the next question. This is the next question, where we have a capacitor that is constructed using two concentric spheres and air as the dielectric medium. Okay, the radii of inner and outer sphere is A equals to 10 and 15. The capacitance in picofarad will be equals to. So this you will have to use the formula. So I will just quickly show you what is the capacitance formula for, just let me go there, for a spherical plate. Okay, for parallel plate you already know, but for spherical plate, what will be the formula? Okay, this is the formula, right? For a spherical conductor, okay, this is the formula, and for cylindrical conductor, this is the formula. So this you will have to remember. Unfortunately, this you will have to remember. Okay, so this will be 4 pi epsilon upon 1 by r1 minus 1 by r2. So 4 pi epsilon okay, and where epsilon would be the dielectric, basically medium permittivity. So it is simply the dielectric medium is air. Okay, so this would be 4 pi epsilon, that is this would be simply 4 pi epsilon is nothing but 1 divided by 10 raised to the power 9 into 1 by r1. R1 you have to calculate in picofarads, right? So you have to write everything in SI units. So 1 by r1 would be the lower value, okay, the lower value, that will be 1 by 10 minus 1 by r2, that is the higher value. So all these should be the radius. They have given me the radius only. So 1 by r1 is the radius of the inner sphere, 1 by r2 would be, sorry, r2 would be the radius of the outer sphere. So 1 by 10 divided by 1 by 15. And of course you have to write this in SI units. These are in centimeters, right? So I will have to multiply 1 by 10 raised to the power minus 2 to convert this in meters. So this was 10 centimeter. How to convert this in meters? Multiply it by 10 raised to the power of minus 2. So now I am in my proper format. So this will be 1 by 9 into 10 raised to the power of 11, and this will be 15 minus 10, that is 5, and 150 will go at the top. 150 into 5, right? And this is in farad, okay, but they have asked me in picofarad. So if they have asked me in picofarad, I can multiply this by 10 raised to the power of 12, right? So this will be 30 divided by 9 into 10 raised to the power of 11 into 10 raised to the power of 12, right? This will be in picofarad. So this will be 10 3, this will be 100 upon 3, that is 33.3 picofarad. Okay, simple formula. You will have to just apply formula. This will be asked in iron, these type of questions. I am not expecting these kind of questions to be asked in your EE, but still you can remember the formulas. Okay, I also don't remember most of the formulas. We'll have to revise. So in XYZ coordinate system, the point charges are located in space like this. The value of alpha such that the electric field is 0 at 0.5. Okay, electric field is 0 at 0.5. What shall be the value of alpha? They are asking me. So how do I compute this value? Just give me 1 second. Yeah. So so point charges are located like this. So one is located in the negative x coordinate is -1. Okay, this is my q. This is my y, right? Negative y is here. So one point charge is located here, one point charge is located here, that is alpha into q, and minus y, and one point charge is located here, and they are telling me the electric field must be 0 at this location, that is 0.5 at this location. Okay, so electric field is a vector quantity, right? So we can use this for our advantage. Do you know what is the electric field at a point, particular certain point, right? That will be equals to k q, where q is the charge of the other particle, other point charge, right, upon magnitude of r 21 into ar 21. Okay, so what is r21? I will explain. So r21 is just the position vector. So let's say this point is what? This point is 0.0 comma 0.5 comma 0. Okay, so your what is your r21? What is your r21, right? R21 would be equals to, so let's calculate the electric field due to this charge. R21 will be nothing but final position minus the initial position. That's all. That is what my R21. Basically, it is the position vector. Okay, so this would be equals to final position is 0.5 j cap, right? Because it is in the y cap direction, y direction, minus initial position. Initial position is here for the first charge. Okay, this is the initial position, that is minus I cap, right? So minus of minus I cap. This is R21, that is 0.5 j, that is j by 2 plus I cap. Okay, that is what your R21 is equals to. right? Yeah. So yeah, j by 2 plus I cap. Now yeah, we got our R21, right? So I can actually I will do that. I will do the calculations later, but just let me keep it. This is my R2. Let me mark the positions. Okay, so let me mark this as 2 position. Let me mark this as 1, this is 3, this as 4. Okay, so this is my R21. What about R23? I am computing the electric field at point 2 due to point charge 3, right? So this would be equals to, again, final position, that is 0.5j, minus the initial position. Initial position is this time I cap. So this will be I cap. So this will be equals to 0.5j minus I cap. Okay, that is j 0.2 minus I cap. Now what is the final position vector? R24. This would be equals to, again, initial position, that is j by 2, j cap divided by 2, j cap divided by 2 minus uh, the final position. What is the final position here? The final position here is this, right? Minus j cap. Sorry, initial position, that is minus j cap. So this will be actually 3 by 2 j cap. Now interestingly, what is happening is my overall electric field would be electric field on the second point charge due to first point charge, plus electric field on the second point charge due to the third point charge, electric field due to the second point charge due to the fourth point charge, right? So all these things are, I hope, self-explanatory. Okay, now obviously we will not compute the electric field due to its own charge. Okay, that we will not do. Interesting point to note here, I see when I will add these components, right, these two components, interesting thing will happen. There will be plus I cap, minus I cap. So automatically the I cap component will be gone. Only these j cap components will be added. Okay, j cap components will be added. So what will happen here, just to reduce my calculation, right, this will be k into q upon R21. R21 and R23, both this distance, if you observe properly, right, these distances are same. Okay, what is the distance? It is simply the magnitude. Magnitudes are same. Magnitude of R21 is equals to 1 by 4 plus 1, that is 5, that is under root 5 by 2. And here also, if you see the magnitude, R23 is under root 5 by 2. Okay, so it would be under root 5 by 2. So this will be same, right? So okay, so this will be k q upon magnitude of r, that is under root 5 by 2, and I can add all these things up, right? If I add, because these two components, if I add, this will be j by 2, this is plus I and plus j by 2. I am talking about only these two components. Most things are same, only the directions are different. Okay, minus I cap. I am just solving the question. You can do it in a more in-depth manner. Okay, plus, now it is interesting, plus k, what is the charge of the third point charge? That is alpha into q. It is not q, it is k into alpha q, divide by what is the distance, right? Magnitude of R24 is simply 3 by 2. Okay, so this is 3 by 2. Oh, sorry, this will be squared, right? Sorry, this will be squared. I forgot, this will be squared. Okay, if I mentioned everywhere, if it is not squared, I was wrong. So this will be squared, right? This will be kq upon r square, squared. Okay, I'm sorry, this will be squared into the direction is 3 by 2 j cap. Okay, one thing is wrong here. this should be the direction vector, right? But is this a direction? No. Direction vector is a unit vector. So again, we will have to divide by the magnitude as well. That is root 3 by 2. Here also I will have to divide by the magnitude, that is 3 by 2. So its direction is simply j cap. Okay. So ultimately, you don't need to. Do we need to worry? I think you do need to worry. So ultimately, your electric field will come out to be 0. That is what they are telling me, right? So what shall be the value of alpha? That is what they are asking me. So this is the direction vector, right? So how to compute the direction vector? So your direction vector AR21 cap would be your R21 vector upon the magnitude of R21 vector. That's it. Okay, that's it. Now what you can do, K, Q, all these are going to 0. This is getting cancelled. So this will be J cap. So only the J cap component is there. KQ is getting cancelled. This will be actually equals to 5. Sorry, this is not root 3. This is root 5 by 2. Okay. So this will be 5 by 4 into root 5 by 4, that is 8 into 5 root 5, and here also this will be plus. So plus alpha into 4 by 9. Okay. So this has to be 0. So what shall be the value of alpha? That is what they are asking. What shall be the value of alpha? Okay. Let me solve this. Just give me 1 second now. So if I solve for this, of course I will get some value. Let me solve. So this will be 9 into 8 divided by 4 into 5 into 5 under root, that is minus. So your alpha will come out to be minus 1.6. I do agree, but lengthy question. Okay, but these are the things that you already know. All I was doing is I was solving the questions, and few things I think which you may forget, you are able to remember it. Okay, that's what I'm doing. So minus 1.6 will be your answer. Simply you will have to write the vectors properly. You will have to write the unit vectors properly. So this is my unit vector and this is my distance whole square, right? This is the formula for electric field. Okay, let's solve the next question. This is the next question. So capacitor is shown has parallel plate, each plate having an area A. The thickness of the dielectric materials are D1, D2 and the relative permittivities are epsilon 1 and epsilon 2. Assuming that the fringing effects are negligible, epsilon naught is the permittivity of the free space. If D1 is decreased by delta D1, the resultant capacitance becomes what? So if D1 is decreased by delta D1, right, then certainly I know the overall distance in D1, it will be what? D minus delta D1. I only see that in option 1. In any other option, I never see I have a D minus delta D1 term. So basically the overall distance in the air gap should be D minus delta D1, right? I only see that in option 1. I don't see that in anywhere else, right? Here everywhere I see D plus delta D naught. This is D2 minus delta D2. From where I get the delta D2? Delta D2 is not even present. This is showing there is no change. This is simply D2 plus D1 upon epsilon 2. Okay, epsilon 2 is the like solid dielectric permittivity. Certainly it will be option A. Okay, if you want to have more comprehensive understanding of this, you need to watch my capacitors lecture. There I have done multiple questions like this and solved it. Okay, so I will not explain it here because we have other things to solve. So simply you see only one option has D minus delta D1, so only we will choose this option. Okay, let's now solve the next question. This is the next question, right? So the capacitance formed between two concentric metal metal shells having radii x and y will be what? So simply it is asking me what is the formula for capacitance of spherical for spherical cells, right? So we already know the formula. It is 4 pi epsilon upon 1 by r1 the inner radii minus 1 by r2 the outer radii. They are telling me that y is greater than x. That simply basically means that y is the outer radii, x is the inner radii, right? So this will be equals to 4 pi epsilon upon 1 by x minus 1 by y. If I rewrite this properly, this will be 4 pi epsilon into xy upon y minus x, that is present in option A. So option A would be your answer for the question. Simple formula based question. Okay, they are not asking you something out of the blue here. They are asking you simple formula based question. So let's solve this question, right? So the wire of circular cross section has the current density as shown. They are asking me what is the total current through the wire. So if the current density is shown, right, the total current would be J dot ds surface integration would give me the closed surface integration would give me the total current through the wire. Now how do I compute J dot ds? So J is given to me, right, that is K square, where S is the radial distance. So S is nothing but my rho, radial distance from the center. So S is nothing but my rho. Now what is ds? Ds is the surface, right, disk surface. So in ds what is varying? My rho is varying from 0 to a. If you see, rho is varying from 0 to a, the radius, and my phi is varying. Phi is going from 0 to 2 pi. Z is constant. In this surface, Z is constant. Okay, I just need to calculate the current. So very easy. So what will be the differential surface ds vector? Ds vector would be equals to rho. So it will be d rho due to this, and it will be rho d phi due to this. Okay, now what is the direction? Okay, so if you see, right, the current density is given here, no direction is given to you, right, no direction is given, so you solve it without any directions. Okay, if no direction is given, they should have actually properly given the wire of circular cross section is shown, the current density is this, where K is the constant, S is the radial distance from the axis, the total current is. If nothing is given, right, you assume everything in the normal format. So you assume everything like in normal format, no vector. Okay, so it will be simply J into ds. Ds is this, right? So don't assume any directions. So J is K S square, that is basically K rho square, right? And this would be rho d rho d phi. Don't assume any directions because no direction has been mentioned. Don't assume any directions, just solve in scalar format. So this will be equals to rho is going from 0 to a and phi is going from 0 to 2 pi. So this will be K into rho cube upon, so this is rho cube, right? And if I integrate with respect to rho, this will be rho raised to the power 4 upon 4, and rho is going from 0 to a, and your phi is going from 0 to 2 pi, right? So it will be phi 0 to 2 pi. So this will be basically 2 pi into K rho raised to the power of 4 upon 4, sorry, this is rho cube upon, yeah, yes, 4 upon 4. So this will be basically pi K rho raised to the power of 4 upon 2. So pi K rho raised to the power of 4 upon 2, so not rho, sorry, this will be A, right? This will be changed to A because I am going from 0 to A. So pi K A raised to the power of 4 upon 2, that is present in option A. So option A is certainly correct for this particular question. Okay, now let's solve this question. This is the next question. Which one of the following represents the radial electric field distribution ER caused by a spherical cloud of volume charge density rho equals to -3 rho naught? Rho naught and A both are positive. R is the radial distance. Okay, and R is between 0 to, so the spherical cloud has a radius A. Okay, spherical cloud of electrons, this, and this is equals to, for R equals to 0 to A. Okay, so the spherical cloud has radius this, right, that is the charge density, and rho equals to 0 for outside this spherical cloud, that is after outside this radius the volume charge density is 0. They are asking me what is the electric field due to this volume charge. Okay, so certainly this is negative, right? If this is negative, of course the electric field will be coming towards it, correct? So electric field also will be negative, it will not be positive. If I'm moving from origin to outside, so it will be negative, it is coming towards me. So certainly positive answers you can anyways eliminate. So there are two options in the negative answer. One is this one is this one. How do I compute the electric field at point A? Okay, electric field at point A. Electric field at point A. How do I compute the electric field at point A? Okay. So we can use this basic formula, right? What is the basic formula? D dot ds, surface integration of D dot ds is equals to my Q enclosed. This is the most basic formula. Okay. Now we can change this, right? Like we have already learned this. If I use the Gauss law, del dot D dot dV volume integration would be equals to rho v dot dV. Okay. So from this I can directly say what is del dot D, that is equals to rho v. Okay. But will this help me? I'm just trying to figure this out. Will this help me? Okay. Electric field at a surface. Okay. But this will not help me actually, because this will not help me. This will just help me compute the D del dot V. This will help me compute the rho V, right? But rho V, I already know what is my rho V. Rho V is minus 3 rho naught. Okay. And that actually will help me. So if rho V is minus rho V is what? Rho V is minus 3 rho naught, correct? And what is your del dot D? So if you see, your electric field will only exist along the radial direction. Okay. So your electric field will only exist in the radial direction, that is AR cap. So it will be some dr into AR cap. That's all. Your electric field will not exist in any other direction. That you can see from the graph itself, right? So what will be the del dot D in the spherical coordinate system in this case? Because everything is spherical, right? This is spherical. So what is del dot V? So del dot V, if you remember, this was the simplest one, right? It is simply okay. So what is my H1, H2, H3? H1, H2, H3. So for the first one it is R, then it is theta, then it is phi, right? So this is del R. So del R upon del R is 1. Now this is R d theta. So this will be R d theta upon d theta R. This will be R sine theta into d phi. So this will be R sine theta. Now your divergence was equals to 1 by H1, H2, H3, that is R square sine theta. For the first term it was del R into H2 H3. H2 into H3, that is again R square sine theta. Okay. Into obviously dr. Am I correct? This will be the divergence. This will be the divergence. Now as sine theta is not a function of R, right? This can come outside. So sine theta will be cancelled. So your divergence would be basically 1 by R square into del R into R square dr. Okay. But will this help me? That is what I am thinking. This certainly will help me. This certainly will help me. So if you see in this graph, what is my ER? ER is equals to minus of what is the slope? Slope is dy upon dx. So dy is this, dx is this. So slope is actually minus rho naught upon epsilon naught. Okay. So what will be my dr? Dr would be epsilon into ER. that is basically minus rho naught. Okay. It is minus rho naught. That is a constant. Okay. And what is my rho v? Rho v is 3 rho naught, right? Rho v is 3 rho naught. I'm just thinking how to solve this. So del dot v is r square delta. So dr cap, this is my dr cap direction, right? This is my ar cap. So this is minus rho naught. Minus rho naught will come outside. Okay, minus rho naught will come outside. But here it is telling me it is varying. How is it possible? It is varying with respect to distance. Oh, sorry. I'm sorry. This was the slope, right? So what is the function? The function is this into r. Correct? That is the function. Okay, sorry. The function is like, as I will move along the r axis, the values will change. This was the slope. Yeah, sorry. This will be r. Yeah, rho naught into r. Okay. Now we are making some progress. Rho naught into r, but still we not rho naught into r. Okay. Okay, yeah. This is rho naught into r. Okay. This is rho naught into r. So you can solve, you can put the value here, right? So this will be 1 by r square into del r. It will be r square into rho naught minus rho naught into r, right? So this will be equals to so rho naught is a constant, minus rho naught can come outside. The differentiation of r cube would be 3r square upon r square. So this becomes minus 3 rho naught. That is equals to my rho v, which is exactly what is given in the question. Right, you can solve using the Gaussian theorem. Okay, using Gauss law, basic Gauss law, you can solve. You can check this is matching. So this will be my answer, and certainly your option D will not be your answer. You will see that you are getting some other charge value, okay, which is not matching. So certainly your option C will be your correct answer. So use basic laws and you can solve it. So let's solve the next question. This is the next question. Let AR be the unit vector in the spherical coordinate system for which of the following values of n the divergence of the radial vector field Fr is independent of r. So basically the divergence is independent of r for what values of n. Simply you have to compute the divergence, right? This is AR cap. So we have just derived the divergence formula. So I will not derive it again, okay? We can, right? Just in the previous question, I will directly use this result, okay? Directly I will use the result. Because we have just derived it, I will directly use the result now. Okay, so this will be basically 1 by r square, because it exists only in r cap direction, del r into r square into dr. Dr is 1 by r raised to the power of n. So into so this would be equals to 1 by r square into r raised to the power of 2 minus n, right? So the derivative of this would be r raised to the power of 1 minus n. Sorry, derivative of this, right, will be 2 minus n into r raised to the power of 1 minus n. Correct? I hope I am not wrong. Yeah. So this needs to be 0, right? For what values of n this will be 0? So certainly for n equals to 2 this is 0. Okay, that is certainly true. N equals to 2 this is 0. Is it 0 for any other value? I am trying to think. Ha. If you closely check for n equals to 2, certainly this is 0. Yeah, n equals to 2, certainly this is 0. N equals to 2, this is 0. Okay. Any other value? I'm just trying to think. Any other value will it be 0? N equals to 2, it is 0. What about any other value? They're telling me for, okay, for what value, okay, sorry, not 0, sorry, not 0. For what value the divergence will be independent of R, okay? It must be independent of R. So at n equals to 2, it is simply equal to 0, so certainly it is independent of R. And if I rearrange this properly, okay, this will be 2 minus n into R raised to the power of minus 1 minus n. Okay, now if this power is somehow 0, right, then this will become 2 minus n, correct? So if the power is 0, this will be minus 1 minus n equals to 0, so n is equals to 1, right? So if for, sorry, n equals to minus 1, so for n equals to minus 1, right? For n equals to minus 1, what will happen? For n equals to minus 1, this will be 0, sorry, this will be R raised to the power of 0, which is 1, which is independent of R, right? Which is independent of R. So if it is independent of R, then this also is a valid solution. N equals to minus 1 is also a valid solution, right? So this divergence also will be independent of R, because when n is equals to minus 1, this will be 2 minus n, that is 3. So 3 is also independent of R and 0 is also independent of R. So these are the two values, n equals to minus 1 and n equals to plus 2. Let's solve the next question. This is the next question where you will have to, so they have given you some cylindrical capacitor. Okay, so what is the formula of capacitance for a cylindrical capacitor? It is 2 pi epsilon by ln b by a, and they are telling you that the initial capacitance is equals to, sorry, 2 pi epsilon into L, right, length of the cylinder, 2 pi epsilon into length upon ln b by a. You can also verify the units as well. Okay, so initially the capacitance of this particular structure is C naught, inner and outer radii are B and A and B. Now what they are doing is, in order to increase the capacitance, a dielectric material of relative permittivity epsilon r is inserted 50% of the annular region. Okay, the value of epsilon r, for which the capacitance of the capacitor becomes 5 C naught. So this is my C naught. Okay, now if they are inserting a dielectric in the annular region, is this in parallel or this is in series? So this will be this would have been in series if something, a structure like this would have happened, right? If the dielectric is inserted throughout phi, then you would have commented that this would be the C1 capacitance, this would be the C2 capacitance. You can compute the capacitance according to the radii, and then you can comment that this will be in series. But here this will be certainly in parallel, and they have mentioned they want to increase the capacitance. So certainly you will have, these will be in parallel only, then only the capacitance will be increased, otherwise the capacitance would have reduced. Cool. Now if they are inserting the dielectric 50%, right? So what is the capacitance of the 50% of the remaining part without the dielectric? It will be C naught by 2. If the whole capacitance was C naught and I am only filling up 50%, the other 50% capacitance will be C naught by 2. Very easy, very simple to understand. Okay, now plus, if you see in the other half, other 50%, all you are doing is just changing the epsilon r. So this, previously your epsilon r was 1, now your epsilon r is epsilon r. So in the other half it will be C naught by 2, because previously your epsilon r was 1, it was C naught by 2. Now your epsilon r is epsilon r, so this will be C naught by 2 into epsilon r. This was the capacitance, this is the capacitance of the other half. As these two are in parallel, so I will add the two capacitances, and this will be equals to my overall capacitance, that is given as 5 C naught. So this will be 5 C naught. So your C naught will be cancelled. Your epsilon r would be equals to, this will be 10 minus 1, that is 9. Okay, so epsilon r would be equals to 9, that is present in option C. So bit of intuition is you need to solve this question, otherwise this will go very lengthy. Okay, let's solve this last question that came in GATE 2025 in iron paper. So they're telling me that a uniform sheet of charge is present. The medium surrounding the sheet has a relative permittivity of 10. Okay, so relative permittivity epsilon r is 10. What are they asking? The electric flux density at a point P would be equals to what? Okay, so basically I have an infinite sheet of charge placed at z equals to 0 pin, right? Now I am measuring the electric field intensity at z equals to point P, which is z equals to 5. So what will be the electric field intensity? So do remember, actually this is not proper, right? Your electric field intensity actually will be equals to rho upon epsilon. Okay, rho upon 2 epsilon. If you remember, the electric field intensity due to a charge of sheet is rho upon 2 epsilon. So this will be equals to rho is 10 coulomb per meter square upon 2 into epsilon. Okay, relative permittivity is 10, right? 2 upon epsilon. Hold on a second. Uh, what was the electric field? This was constant, right? Due to and that was rho upon, what is it, rho? Yeah, area. It is half. So it was rho upon epsilon. Yes. Okay. Density. Okay, they are asking. Oh, sorry. They are not asking me the electric field intensity. They are asking me the electric flux density. They are asking me the electric flux density. So this was the electric field intensity, right? So electric flux density D would be simply equals to epsilon into E. That is equals to rho upon 2. So this will not change. This will be just rho upon 2, right? In the AZ cap direction, right? In the AZ cap direction, because this is a infinite sheet of positive charge. So electric field will be outward from the surface. So in the top surface, right, at z equal to 5, it will be outward. In the bottom surface, it will be minus AZ cap. In the top surface, it will be plus AZ cap. So this will be equals to rho upon 2, that is 10 upon 2, that is 5 coulomb per meter square. This is the electric flux density that is given in option A. So option A will be your correct answer for this question. Now we will solve magnetostatics. Let's begin with magnetostatics. So this is the first question. I hope you have revised the magnetostatics from the short notes. There are a few formulas that you must revise, like this one, right? The Ampere's law, H dot dl equals to I enclosed, right? This can be further derived using Stokes law, del cross H dot ds will be equals to, what is I enclosed? I enclosed can be written as surface integral of J dot ds, right? So from this we can say that our del cross H is equals to J. This is one format. Another thing is that your magnetic field will always be solenoidal in nature. That is del, like that is the divergence of your magnetic field will always be 0. Similarly, your curl of electric field will always be 0. And of course, from magnetic field you can say your D is what? Your H is mu into B, right? H is a mu independent parameter. So simply also your D is epsilon into E, right? So the same thing can be written for H as well and E as well. Sorry, and D as well, right? So you will get the point. Yes. So yeah, these are few things that you must remember, right? And any other stuff I will say, if you have to remember, like one very important relationship, that the EMF induced is minus d phi by dt. Okay, how to compute the flux? Flux is basically the uh, surface integral of B dot ds, right? Magnetic flux is the surface integral of B dot ds. That's how you compute the flux. Cool. Yeah, so these are few things that you must remember for magnetostatics. Let me put it all in a single formula. And there are few more things that you can go and have a look in the notes, but mostly these are the things that you must remember. Also, the magnetic field, let's say due to a current carrying wire at a distance, current carrying wire of I, it is carrying a current of I at a distance x, right, would be equals to, B would be equals to mu I upon 2 pi x, the distance between it, right? So this you will have to certainly remember. Okay, so yeah, mu I by 2 pi x. These are a few things that you must remember. Mu is mu naught, mu is mu naught into mu r, correct? And your mu naught is 4 pi into 10 raised to the power of minus 7 Henry per meter, right? Okay, let's start. A conducting square loop of side length 1 meter is placed at a distance of 1 meter from a long straight wire. The wire is carrying a current of 2 ampere. The mutual inductance in nanohenry between the conducting loop and the long wire. So what is, okay, yeah, one more thing I forgot to tell you. What is the formula for inductance? Inductance formula is, so it is L phi will be equals to Ni. So it is L phi by I, whatever is the total current. Okay, actual formula is L phi is equals to N into I, where N is the number of turns, right? But of course, if I assume the total current, total loop current, then that will be I only. Okay, like N into I is I, basically the total loop current. Here I have only a single wire, so it is only 2. If I had loops of 2 and 2 amperes, then it would have been 2 into 2, that is 4. Cool. Now what is mutual inductance? So this was the flux due to its own current, right? The flux due to its own current. The mutual inductance would be, M would be equals to the flux due to the other current, this current, right? And the current divided by that value. Cool. Okay. So yeah, only one current is flowing, that is this one, right? So the flux that is present in this particular loop due to the current in the other coil, mutual, right? That is what mutual inductance is. So we will have to actually calculate this. Mutual inductance would be the flux present in the coil, in the loop due to the current present in the straight wire. So how to calculate this? We know, right? Flux is equals to, I've discussed, it is B dot ds, closed line integration. Don't forget it is a closed line integration. Okay, so how do I write my B vector? So if I assume it to be in the cylindrical coordinate system, so it is in this direction only, right? What is the direction of the, so how will the magnetic flux direction be? So magnetic flux direction will be somewhat like this. It will be circular in nature, right? This will be the magnetic flux direction, like this. Sorry, not magnetic flux, magnetic field, right? And it will cut the cross section, correct? So what is the direction of the magnetic flux? If you see, it is pointing outwards. It is pointing outwards of the surface, right? And what will be the direction of the surface vector itself? It will also be pointing outwards of the surface. So suddenly both of them have zero angle, so B dot ds will be cos of 0. I can solve this in the non-vectorical format. I have already assumed the direction, I can see the directions, I can solve it in the non-vectorical format. So this will be B dot ds, BDS, okay? We don't need to think of the directions because I can see the direction of the surface vector and the direction of my magnetic field, both of them are same. Okay, now how do I calculate the magnetic field? Okay, so what is the magnetic field at a distance x from the wire, it will be, because nothing is mentioned, I will assume magnetic field at a distance x from the wire would be mu naught into I, whatever is the I current, that is 2 amperes upon 2 pi x. Okay, correct, upon 2 pi x. Now how do I compute this? How do I compute this? I have to compute the inductance, right? Now if I consider a small strip like this, consider a small strip like this, right? So in this region, you see the magnetic field is like the y coordinate is constant, it is 1. I just have to compute what is the x coordinate magnetic field, right? So if I consider this small strip, so what is the area of this strip? It is a into dx. Let's say this distance is dx. This distance is dx, right? So what is the basically flux in this small magnetic strip? It will be bx into, so d phi, right? Small flux in this particular strip. What will be the overall flux cut in this particular strip? It will be d phi into bx into a, right? A, where a is 1, basically the height of the strip, into dx, correct? Because where dx is the width of the strip. So it is, this is simple area and this is the magnetic flux, correct? So from this we can compute our overall flux. So what is our x? So if I vary my this small strip from x equal to what, this is x equals to 1 to x equals to 2, right? I will get my answer, I will get my overall flux. So your a is 1 into dx, x is going from x equal to 1 to x equal to 2. So this will be, so I can integrate, right? 5 here, there is no flux, right? X equal to 1 there is no flux, and x equal to 2 there will be all the flux. So this will be 5 will be equals to 2 mu naught, 2 has cancelled, mu naught upon pi. Actually we don't need this, ultimately this is mu naught I, right? We need 5 upon I, so I can take this I on the other side, 5 upon I, that is my m. This will be equals to mu naught upon 2 pi into ln of x. So ln of x would be ln of 2 upon ln of 1, right? Yes. So it is basically ln 2, that is your answer, right? So what is mu naught? Mu naught is 4 pi into 10 raised to the power minus 7, that is 10 raised to the power minus 7 into ln of 2. ln of 2 shall be equals to 0.639, right? And yeah, so 4, it is 4 pi, right? Mu naught is 4 pi into 10 raised to the power minus 7, so there is another 2 multiplied into 0.693 Henry, right? So this into 2, it is into 10 raised to the power minus 7. We have to compute in nano Henry, right? So what I will do, I will multiply this 1386 into 10 raised to the power, I will multiply 10 raised to the power 9. So this will be 10 square nano Henry, right? So your answer would be 138.63 nano Henry. Okay, that is the answer of this particular question. Let's solve the next question. 1 coulomb of point charge moving with uniform velocity this enters into region x greater than 0 having magnetic field this. The magnitude of the force acting on the charge. Yeah, one more formula I forgot to mention. the Lorentz force, right? The overall Lorentz force. So the force on a particle would be, if it is a charged particle, it will be Q V cross B. Okay, that is the force experienced by a charged particle when it is moving in the magnetic field. Now there is another force. This is called as the magnetic force, and there is Q into E. This is the electrostatic force, right? So these are the two forces that you must remember. The force on a charged particle, like this definition, right, of E. If definition of E comes from force only, I have to remember. So the overall force on a charged particle would be Q V cross E plus Q into E vector. Okay, so yeah, these things you have to remember. So for if the E field is 0, that means your force will be this. If the B field is 0, or V cross B, V is the velocity, is 0, that means then you will have only electrostatic force. So this V is velocity of the charged particle. So this formula also you can remember, right? So basically it is a 1 coulomb of charge. Velocity vector is, like, Q is 1 coulomb, velocity vector is 10 x cap, having a magnetic flux density of B of this, so magnitude of the force. So your force would be equals to Q, that is 1 into V cross B. So yeah, this will be only, so this cross product will certainly be 0, right? This AX cross AX is 0. So AX cross AY would be, X cross Y will be Z cap, right? So this is 10 into, so they are asking me at x equal to 0 plus. If x is equal to 0 plus, this is 0, right? This is 0. So this is actually 0. X equal to 0 plus, this is 0. Only this is the component that is left. And obviously x cross x is nothing but 0. So x cross z would be minus y cap, right? And it is 10 into 10, that is 100. So your answer would be 100 Newton. Magnitude they have asked, so 100 Newton would be your answer for the question. Okay, let's solve the next question. This is the next question. Which one of the following vector functions represent a magnetic field B? So basically, if it represents a magnetic field B, then certainly your magnetic field will be solenoidal, that is divergence of magnetic field must be equals to 0. So if I compute the divergence in the first case, this would be 10 plus 20 10 plus 20 minus 30, that is 0. Cool, first one is fine. Next one is 0 plus 0 minus 10, so which is minus 10, which is not cool. This is certainly not true. This one is again 0 plus 0, so this is 0 plus 20 plus 0, so again not cool. This is not 0, right? Again this is 10 plus 0 plus 0, again this is not equal to 0. So only option A is correct, which has the divergence to be 0, right? So let's solve the next question. If the magnetic field intensity H in a conducting region is given by the expression this, the magnitude of the current density. So yeah, I told you earlier, right, this one, that Ampere's law is this, right? This is my Ampere's law. So from this we can derive what is my current density using the help of Ampere's law. Okay, so current density would be equals to del cross H would be equals to J, correct? So we can easily compute the current density. So yeah, we have to just take the cross product of this. So let's take the cross product. So this is I cap, J cap, K cap. X square, X square, Y square, X square, Y square, Z square. X square, X square, Y square, X square, Y square, Z square. So this, right, would be del Y, that is 2y x square z square minus 0. Yes, this is I cap minus j cap into this, sorry, into this, that is 2x y square z square minus this, that is 0 only, plus k cap into this, that is 2xy square minus 0 again, right? Now you have to compute at x equal to 1, y equals to x equal to 1, y equals to 2, z equals to 1. So z and x are 1, y is 2. So this will be z and x and 1, y is 2. This will be 4i minus this will be z and x and 1, y is 2. This is 1 into 2 square, 4 into 2, that is 8j plus 8k. So what are they asking? They are asking me the magnitude of the current density, right? So magnitude would be 4, I can take common, under root of 1 square plus 2 square plus 2 square. So it is 4 plus 4 plus 1, that is under root 3. So 4 into 3, that is 12. That is the magnitude, right? So 12 ampere per meter is the current density, basically. Ampere per meter square, right? So ampere per meter square, 12. Option B is the correct answer for this question. Pretty straightforward, pretty simple. I don't have anything any inputs here. So yeah, let's solve the next question. This is the next question. The long conductive cylinder having radius b is placed along the z axis. The current density J is this. For the region R less than B, where R is the distance in the radial direction, the magnetic field intensity for the region inside the conductor is what? So they are simply asking what is the magnetic field intensity inside the conductor if the current density is given to us. Okay, so we know this certainly, right? We know our H dot dl is equals to I enclosed. Okay, so current density is given. Through a long cylinder. Current density of radius b through a long cylinder is given to me. Okay, for current density is this for region R less than b, okay, where R is the distance in the radial direction. So R is this distance, right? This one is given along the AZ cap. Okay, so current density is along this direction, AZ cap direction. Now they ask me what is the magnetic field intensity. So I'm just thinking, how can I calculate? Okay, so we can so what we can do, what is H dot dl? So I can take a Amperian loop here, right? Let's say I take a Amperian loop. Let's say I take a Amperian loop at a distance of r, right? So what will be my H dot del in this distance from center, right? If the current density is going in this direction, in the z direction, right? So this will be constant. Whatever I compute here, H will be some constant value, right? That I can calculate in this Amperian loop, because the current inside it, I enclosed inside it, is some constant value. I inside it is some constant value. So H I can certainly compute. So let's take an Amperian loop along the direction that is given for the current. So this is the current density direction. Current also will be in the same direction only. So I will take the Amperian loop in the, according to the right hand rule, I will take it in the clockwise direction. This will be the direction of the Amperian loop, right? This will be my DL cap. So H dot DL, what is DL? It will be 2 pi into R, the length of the Amperian loop. So H into 2 pi R. Cool. Because in this Amperian loop, the I enclosed is constant. So H also will be constant here due to the whatever current is enclosed. Now what is the I enclosed in this Amperian loop? The I enclosed in this Amperian loop is double integration of surface vector, current density dot ds. What ds is, what kind of surface? Ds is this surface, right? This one. So which is basically a circle. So now we will solve this in the cylindrical coordinate system. So ds is a circle whose radius is going from 0 to r, rho is going from 0 to r, its phi is going from 0 to 2 pi, and its z is some constant z. We don't know exactly what z, but it is some constant z. Okay, z can be any constant, it does not matter. In our case, it does not matter. Okay, because ultimately what you will do, what is your ds vector? Then your ds vector would be also in the same direction, because your like current density is also in the same direction. Ds vector would be, because it is rho is varying, so it will be d rho, and phi is varying, so it will be rho d rho, and the direction would be same as the current density direction, that is z cap. Okay, so this will be equals to double integration, what is j? J is this, right? That is ja. Now remember here r is our rho. Okay, don't be scared, r is a radial distance, that is our rho. So I will replace r with rho cube, that's it. So this will be d5. Okay, and your rho will go from rho equal to 0 to r, your phi will go from 0 to 2 pi. So this will be rho raised to power 4 by 5, right? So this will be ja. If I do the integration properly, this will be rho raised to the power of 5 by 5 into 2 pi, correct? So 2 pi ja r raised to the power 5 by 5, this is equals to 2 pi r into h. So h would be equals to 2 pi will be cancelled, r will be cancelled, ja r raised to the power 4 by 5. Okay, ja r raised to the power 4 by 5, that is present in option C. So option C will be correct. All you have to do is just to pick a proper Amperian loop, and just think that okay, your h will be constant if the I enclosed is constant here, right? There is some constant I enclosed within this particular Amperian loop, then you can easily solve it. I do understand, not that simple, but not that difficult either. Let's solve this question. This is the next question. A conducting semicircular loop of radius r has 0.1 meters of diameter with the centered at origin. So if you see, this is the conducting loop that has 0.1 meters of diameter with center at origin. Okay, now what they are doing is it rotates with a constant angular speed of omega as shown. The magnetic field B is 2 Tesla, normal to the xy plane, exists on region x greater than 0. If the loop has a resistance of 2 ohm, this loop has a resistance of 2 ohm, the negligible inductance, the peak to peak current in milliamperes shall be equals to 1. So if I see that this is constant magnetic field here, right? When this circular loop, sorry, semicircular loop is inside the magnetic field region, it will develop some flux. it is cutting some flux, right? This is a conducting semicircular loop, so this is a proper semicircular loop. It will develop some flux, correct? Some flux will be changing here, okay? So we will have to consider that. So basically what happens in this loop, a EMF will be induced. That will be due to what? Now we don't care about the sign because they have asked the peak to peak. So magnitude of the EMF induced will be d phi over dt, okay? And your flux is equals to what? Flux is equals to b dot a, right? In this case our magnetic field is constant, but our area is changing, okay? Area is changing. So your d phi dt would be equals to b is constant, it is dA upon dt. So we have to find out the relation between area and time, okay? How do I compute the relation between area and time, right? Like how much area am I cutting when, let's say I am in this position? Am I cutting any area? No. When the loop is in this position, half of the loop is cutting all the flux, right? When I am in this position, just hold on, when I am in this position, all the area is cutting the flux. Again I am in this position, none of, like half of the area is cutting, right? Okay, how do I calculate that area? So its omega is 20, so it is rotating with 20 radian per second, right? So if I see, basically it depends on the theta. So here when it was here, this theta was 0, but when I am here, the theta is something else. So how much angle have I rotated by? How much angle have I rotated by? So your theta would be equals to omega into t, right? Where omega is the angular speed and t is the time. So how much angles have I rotated in time t? That is omega into t. So your theta goes from theta equals to 0 to theta equals to what? Whole 180, correct? So it was previously here, now it rotated and came here, right? So it theta totally rotated by 180. Okay, so your theta is equals to omega into t, right? If I know the theta of this particular thing, what is the area? Do you know? If I know the, basically if I know theta, right, what is the area crossed? How do I compute the area? Area of a sector. How to compute the area of a sector? So if the whole area is pi r square, whole area of this circle would be pi r square, correct? And if I am covering only theta area, right, it will be divided, that is this will be theta divided by 2 pi, correct? Theta divided by 2 pi. If the whole area of this circle is pi r square and I'm only covering theta angle, that means I can do the linear linear relation, that if I'm covering theta, the area covered, this area would be theta divided by 2 pi. If the whole area is pi r square, for 2 pi angle the area is pi r square. For theta angle, what will be the area? Pi r square into theta by 2 pi. So the area covered as a function of time would be basically pi r square into theta by 2 pi, but theta is simply omega into t. So this will be actually r square omega into t divided by 2 pi. So divided by 2. Okay. So simply your area covered would be r square omega into t divided by 2. Okay. Where r is the simply the radius, right? R is some constant. R is capital R in this case. Okay. I will replace r with capital R. Right. Now we can easily compute what is our d phi by dt. Our d phi by dt would be r square by 2 omega, that because I am differentiating it with time. I am differentiating the area with time, and B is there, constant magnetic field. What is the constant magnetic field value? Constant magnetic field value is 2 Tesla. So this will be 2. Okay. So this is my d phi by dt, this is my E. Now you see that your induced EMF comes out to be constant, but there is a twist. So at the moment I start entering the loop, the flux increases, right? So your d phi by dt, actually your E in this formula, right, is minus of d phi by dt. Okay. So your d phi by dt is positive. That means your E induced would be negative. The moment I reach half of my xy axis, the moment I reach here, right, what happens? The flux, the moment I reach here, till this point, the flux only increases. The moment my loop reaches here, what happens? The flux reduces. So for 1/2 period, that is 1 pi period, the flux is always increasing, right? And when the flux is always, we assume d phi by dt to be positive, then this is the value. This is the E induced. Actually, E induced is negative. Okay, if I directly take the proper sign, it is negative. Okay, and this is from omega t. So the angle goes from 0 to pi, right? When the angle, so this is my 0 degree angle, and this is my, so this is my 0 degree angle when there is no angle intersection, and this is my pi angle, right? Now when my angle goes from pi to 2 pi, when my angle goes from pi to 2 pi, then what happens? Then we see that our flux reduces. If you see here, if I'm here, right, yeah, that the drawing that is shown here, so I'm going here, the phi, so this was phi equal to 0, so phi is increasing. So if I'm in this region, if you see, the flux is reducing. Here there was total flux cut, here the flux is reducing. So here the flux is reducing. If the flux is reducing, what will happen? Then your d phi by dt will be negative, your E induced will be positive. So actually your E induced graph, because E induced magnitude is coming out to be constant, right? Because omega is constant, it is coming out to be constant, but it will be a square wave like this. So omega t equals to pi, this will be negative, omega t equals to 2 pi, this will be positive. It does not matter, I don't know what is the direction exactly, but I can get the sense of it. This is the induced. So they are asking me what is the peak to peak current, right? Peak to peak current. Okay, they are asking what is the peak to peak current in milliamperes. So here I will have minus E and plus E, right? Whatever is the E value here, magnitude. So your peak to peak current I would be 2E upon R. Okay, so what is your E value, magnitude of E value, like 2 magnitude of E into R. So magnitude of E would be equals to R square, capital R square. Capital R square is given as 0.1 and omega is 20. So 0.1 whole square into 20, that would be equals to 0.2 volts. So this will be equals to 0.2 into 0.2 divided by R. R is 2 ohms. Okay, yes, R is 2 ohms. So it is 0.2 amperes, or I can say 200 milliamperes. So 200 milliamperes would be your answer of the question. Pretty good question actually, pretty beautiful question. So 200 milliamperes will be answer of this question. Let's now solve this question. Now this question was interesting because this question, I know what they tried to do, but they were not able to do it. This was MTA. So what happened in the figure, the electric field E is shown, the magnetic field B is shown, XZ directions are shown, all have constant magnitudes. A positive charge Q is placed, released at rest from the origin. Which of the following statements is true? The charge will move in the direction Z with constant velocity. So we know, right, if I have a positive charge, then the force acting on the charge due to the magnetic field is V cross B, and the force acting on the charge due to electric field is Q E. Now the direction of force, right, initially the charge is at rest, so velocity initially is 0. So initially the charge will go along the direction of the electric field in this direction, but as soon as the charge will move along the direction of the electric field, what will happen? The velocity will increase, right? Velocity will be non-zero. As soon as the velocity is non-zero, what is the direction of the velocity? It is az cap, and what is the direction of the B field? It is ax cap, right? So az cross az, basically your, this is my x, this is my y, this is my z, right? So ax cross ay, Ax cross, so this is the relation basically. So if I do z cross x, I will get y. So Az cross Ax would be Ay. Yeah. So here, of course, the charged particle will have basically two forces acting on it. One will be along the Ay cap direction, another one will be along the Az cap direction. Now let's read the question. The charge will move in the direction z with constant velocity. Certainly no. The velocity will always increase because there is a constant force. This is incorrect. The charge will always move in yz plane only. Certainly true. It will move in the yz plane only because it has force in the y and z plane only. The trajectory of the charge will be a circle. The trajectory of the charge will be circle. No, it will not be circle because it is always increasing. It will be something like this, right? It will be always, so this z cap force is always increasing and then it will move. Yeah, the charge will progress in the direction of y. This statement is all seems correct. It is progressing in the direction of y, but it is progressing in the direction of z as well, right? So yeah, this was MTA during the examination because there was something wrong with the option, but I hope you get the point. It will have force both in the AY cap direction and in the AZ cap direction, constant force. So there will be constant acceleration in both the directions. Okay, I hope you get the point, right? Okay, so hold on a second. Due to the charge moves along with the z direction, if it is moving in the z direction, experiences a force b, that is v2 vz into moves towards y. If it is moving towards y, what is happening? If it is moving towards y, then vy over, sorry, okay, now okay, one point to note here is, so it will experience a force in the z direction, right, due to this electric field. This will be constant, this force will be always constant. Now as soon as this velocity is non-zero, it experiences a force in the y direction as well. So now your v component, right, has two components. One is along the z direction, like velocity has two components. One is along the z direction, one is along the y direction as well, because it is moving in the y direction. Now if it is moving in the y direction, so due to the z direction, we certainly know what is the force. Force is along the z direction, so force is along the y direction. What is the force when it is moving along the y direction? Okay, so if it is moving along the y direction, what will happen? So force would be, I'm just taking care only of the y directional velocity, so it will be ay cross b. B is ax cap, so ay cross ax is actually minus az. So the force developed due to the y cap velocity will be minus in the minus az cap direction, and the force developed due to the electric field is plus az cap direction. So what will happen if this force is greater, right, than this one? So this will try to oppose the z. So the one, if the charge was going up, now it will try to go down if given that this force due to the magnetic field is greater than the electric field. So if this force is greater due to the magnetic field than the electric field, then what will happen? It will follow a helical like shape. Okay, all of it depends, right, what is the value. So the rough shape will be helical depending on the force value. So they have not given us the force values, then actually you certainly will not be able to comment here. Okay, if the electric field force is much greater than the magnetic field force in the z direction, then certainly it will always be in the yz plane, but we don't know, we cannot comment, we need the values here. Okay, we cannot comment, so that's the problem. That's why we cannot comment on this question. That's why this question was actually given MTA. Although this question was pretty good, the standard way to is this, it will follow a helical shape, but you cannot comment here, certainly you cannot comment. So MTA is correct, you will need the values. So this is another question, very basic question. If we have an infinite surface linear current density exists over the xy plane, as shown, the magnitude of the magnetic field intensity H at 1 would be. So whenever you have infinite sheet of charge, right, what is the electric field intensity? If you remember, it was sigma by 2. Similarly, for magnetic field intensity, if you have infinite sheet of current, right, linear current flowing, current density, it will be K by 2. If it is in this direction, it will be in this and in this direction, right? That's it. So K by 2 is 2.5. Magnitude you have to calculate, it will be simply 2.5. That's it. So your answer is 2.5 ampere per meter. Don't have to worry about anything else. So perpendicular to the plane, the magnetic field intensity will be just half of the current density. That's it. Remember this very basic relation. It's good to remember. So 2.5 is the answer. Let's now solve the next question. This is the next question. The force per unit length between two parallel conductors. Okay, so this is another very important formula. I would love to go back to that particular slide and show you because this relation is pretty important that I have derived as well. So don't you forget this relation. Okay, where is this relation? Yeah, this was the magnetic field due to a infinite sheet of current. This I have told you there as well, right? Okay, so this you can remember. I just want to boundary conditions you can remember on your own. Okay, where is the force due to where is that? This self-inductance, amount of charge, Lenz's law, force. What is force between two conductors? Ampere's law. Where is that, man? Oh no. Yeah, this one, right? Very important, most important thing. So force between two parallel lines. This is again a very important relation that you must remember. Okay, so I will actually copy and paste it over there in the first slide. So this I will paste in this first slide. So in the first slide, the most important things are there. So whatever you must remember it. So do we have space here? So force is basically force between two parallel conductors if the current is flowing in the same direction is this mu I1 I2 L by 2 pi d. हेलो हेलो हाँ हाँ आ गए अब आर यू हियर हाँ यू कैन कम I will share in here WhatsApp. It's just fine. It's in fourth main fourth course road. I will share in WhatsApp. Fourth main fourth course ACS layout. Yeah, 11 ohms. Yes, 11 ohms. K5. Yeah, house number. Yeah. 1093. K5 flat number. K5 is in the second floor. Yeah. Okay. Fine. The force would be attractive in nature if both the currents are in same direction. That is mu I1 I2 into L. L is the length of the parallel lines upon 2 pi d. If it's of infinite line, then we can only comment about force per unit length. Okay. If the L is infinite, we can only comment about force per unit length. Force per unit length would be mu into I1 I2 divided by 2 pi d. But d is the distance. So their force is inversely proportional to the distance between the wires. This thing you have to remember, right? So the magnitude of force per unit length between two wires is mu into I1 I2. Force per unit length is 2 pi d. Okay. If the force per unit length between two infinitely long conductors with a gap of 2 cm is 10 micronewton per meter, when the gap is doubled, right, what will be the force per unit length in micronewton per meter? If the gap is doubled, certainly your force per unit length will be halved because it is inversely proportional. So this will be 5 micronewton per meter. So 5 micronewton per meter will be your answer for the question. Let's solve the next question. This is the next question. The given equation represents a magnetic field in r, theta and phi in spherical coordinate system. The value of P if it is a valid magnetic field. So of course we know if it's a valid magnetic field intensity, that del dot H must be equal to 0. So I have to compute the divergence, right? So again in spherical coordinate system, if I write H1, H2, H3, my r, theta and phi. So we know in r cap direction it is dr only, so dr upon dr it is 1. In theta it is r d theta, so r d theta upon d theta is r. In phi it is r sin theta into d phi, so r sin theta d phi upon d phi, it is simply r sin theta. So this is my h1 h2 h3. So the divergence would be h1 h2 h3 del of del r. So I see only I have two functions, right? I will only care about two functions, that is theta cap and r cap. Okay, so del r del of del r into h2 h3 into whatever is my component in the a r cap component plus del r del theta into this will be h1 h3 into whatever is my theta cap component. That's it. I will not care about the other one because other one is anyways there is no component there, that is 0. So h1 h2 h3 is r square sin theta del del r. h2 h3 is again r square sin theta into ar. Ar is p cos theta, p cos theta. This plus del del theta into h1 h3. h3 is r sin theta, r1 is 1, h1 is 1, a theta is sin theta, right? A theta is simply sin theta. Okay, so this, right, if I solve this, this has to be 0, correct? So how do I solve this? So this will be, if this has to be 0, r square sin theta can go on the other side, that will be 0 anyways. So this will be sin theta is, so theta is a constant in this particular differentiation. So this will be, I don't know what is r square p, but del del r of r square p, I don't know p can be, okay, p is a constant integer, right? P is just a constant integer because they have asked the value of p. So p is certainly a constant integer, so I can take p outside as well. So this will be 2r p, and sin theta and cos theta are anyways functions of theta, so it won't matter, plus r is again constant here, and the differentiation of sin square theta, that will be 2 sin theta cos theta. Now this has to be equal to 0. So all I am doing is just differentiation. So what is the value of p? P has to be minus 1. If p is minus 1, then this value, then this divergence would be equals to 0. Am I correct? Just give me a second. This is r sin theta, sin square theta 2. So this will be 2r. R square will go on that side. Just thinking whether I'm making any mistake or not. Just give me a second. Oh, sorry. There is a 1 by r cube as well. Oh, I'm extremely sorry. There is a 1 by r cube. Okay. Just be very careful, okay? Just be very careful. There is a 1 by r cube as well. That's what I was making a mistake. Don't make this kind of mistake. You will totally, your exam will go away. So be very, very careful, extra attentive, pay extra attention. Right now this is different, right? So this will be differentiation sin theta cos theta can go outside, differentiation of p sin theta cos theta can go outside, differentiation of 1 by r, that is minus 1 by r square, okay, plus this is the differentiation of sin square theta, again 1 by r square is at the coefficient, this would be sin square theta would be 2 sin theta cos theta, this is equals to 0, right? So r square will be cancelled, sin theta cos theta will be cancelled, so p would be equals to 2. So this is your answer. So be very careful with the differentiation and divergence. I hope I don't need to explain much, you can easily calculate. So let's finally solve the this last question, okay? So a 60 volt source is given, right? 60 volt DC source with an internal resistance R internal equals to 0.5 ohms is connected to a switch of an infinitely long rail separated by L as shown in the loop in the figure. The rails are placed with a constant uniform magnetic field as shown, directed into the page. It is going into the page. A conducting bar is placed on these rails, is free to move, okay? It is moving with a in the x cap direction. If you see, what are they asking? At the instant of closing the switch, the force induced on the bar is what? So the moment I close the switch, what is the force induced? That is they're asking, right? The moment I will close the switch, this particular bar is present over here. So what is uh, the force, right? So there is some current in the switch the moment I close the switch. What is the current? I is equals to voltage upon resistance, that is 60 upon 0.5, that is 120 amperes. So 120 amperes of current is flowing through the wire, right? 120 amperes of current is flowing through the wire. Now what is force? Force, this is a derived formula, it is BIL sin theta for a current carrying wire. So here if you see the angle between the current and the magnetic field is 90, right? It is going into the base, angle between the current and the magnetic field is 90. So theta is 90, right? What is the length? So length they have already given me, right? So length length is separated by 1 meter. So this is the particular conducting rail that is moving in the magnetic field, and it has a current of what? Current of 120 amperes. It is moving in this direction. If it is moving in the constant velocity, I don't care. So if it is moving here, what is the length? Length is 1 meter. So what is the magnetic field? Magnetic field is 0.5. So we can use all these values. 0.5 into current, that is 120, into the length, that is 1, into sin theta, that is 1 again. Sin 90 is 1. So your answer is 60 Newton. So now what will be the direction of the force? So I see 60 Newton. There are two options, right? 60 Newton in the direction of x, 60 Newton in the opposite direction of x. How to calculate the direction of the force? So force we always calculate with the Fleming's left hand rule, right? So what you can do, if you assume your, so we are assuming for a motor, right? For a motor we compute the direction of force. For a motor we compute the direction of force. So for a motor we use Fleming's left hand rule. For a generator we will always use the Fleming's right hand rule. So this is kind of a motor, right, where this is the motion. Okay, I want to calculate the direction of the motion, so I will use Fleming's left hand rule, where this thumb gives me the direction of the direction of the force. Your forefinger gives me the direction of the magnetic field. So magnetic field is going inwards, your current is going downwards. Your current is going downwards, your magnetic field is going inwards, right? And your thumb will give you the direction of velocity. If you see, it is right hand side, so it is in the positive x cap direction, right? So your answer would be 60 Newton in the positive x cap direction. This again you can revise and go, all this has been taught in the short notes. You can see it. Okay, so yeah, so option A would be your answer for this question. With this we are done with the electrostat and magnetostat. So we are done with all the subjects of EE core and almost everything of EC. So if you have enjoyed this video, hit the like button. I will see you in the next lecture, and all the best for your upcoming examinations.